Hi, my name is Ray and welcome to Master Electron. Presumably you're here as you've already heard how Electron can help you build amazing desktop applications for both Mac, Windows or Linux using a single JavaScript API. For the longest time, building desktop applications has been reserved for developers using languages such as C or Java, and it's been nothing short of difficult. Sure, in recent years, building native desktop applications has become a lot more flexible, but you still need to learn separate languages and develop using very specific tools for each target operating system, Mac, Windows or Linux. Electron solves this problem by allowing developers like you and me, with knowledge of HTML, JavaScript and CSS, to use these web technologies to build a single application and then compile that application for both Mac, Windows and Linux. And besides having to build and maintain only a single application, instead of multiple platform-specific apps, we also get to use our favorite frameworks and libraries to do so. Electron already boasts many popular apps such as Slack, Hyper, and even Microsoft's own Visual Studio Code, all built using flexible web technologies. So what exactly will you learn in this course? We'll start by covering the course structure, getting the project code to follow along with, and look at some important tasks to help you get the most out of your development workflow. Then we'll dive into the Electron API, understanding the function and purpose of almost every module in the Electron API. And once you're familiar with this entire API, we'll cover some useful Electron features, take a look at security considerations, and finally put all this new knowledge to practice by building and packaging a fully functioning real-world app, ready for release. Also, as I'm constantly working on updating and adding to this course, we have two new sections. The first covers the entire process of implementing auto updates to the project that we'll be building for both Mac and Windows. And the second shows you hands-on how to integrate the Mac touch bar into your apps. All my courses are meticulously planned and structured for maximum learning efficiency, with concise and engaging lessons. So please go ahead and watch the free preview lessons and also be sure to read some of my reviews. Thank you for taking the time to watch this introduction, and I really look forward to helping you learn Electron. Before we get started, let's cover in brief what you'll be seeing throughout this course, or more specifically how I'll be writing and running the Electron projects in the course lessons. First up, the project code I'll be using. For this, I've created a very simple boilerplate project based on Electron JS's own Quick Start project. The main difference being a reduction in code comments to better follow along on video, and a few code changes in preparation for upcoming changes in the Electron API. We'll cover getting this project code set up in the next section of the course, however. Then, to edit project code, I'll be using the Atom editor, an editor that happens to be built using Electron. Any editor will do and no extensions or configuration is required, although ensuring basic JavaScript and HTML syntax highlighting will be useful. I've linked to the Atom download page in the lesson resources. To run the project code, any command line tool will do. I'll be using the Hyper terminal, again built using Electron, but the native Mac terminal or Windows command prompt is perfectly suitable. The only prerequisite here being to have the latest version of Node.js installed. You can find the link to the Node.js downloads page in the lesson resources. I'd also encourage you to check each lesson's linked resources throughout the course, as you'll find any valuable references to that lesson there. So with that said and knowing what to expect, in the next section of the course we'll get started installing Electron, getting our project code set up, and running that boilerplate project for the first time. In this second section of the course, we'll start with installing Electron, getting the course code ready, and covering key concepts for developing with Electron. First up, on the Electron homepage, we see that Electron is installed as a local development dependency, meaning we need the project code first. As mentioned, I've created a GitHub repo for the course code, so over to github.com/stackacademytv/masterelectron, link in the lesson resources. From here you can either download the project or clone it using Git. I'll do the latter, so copy this URL, over to the terminal, And in my home directory, not that this location matters too much, git clone that URL, cloning into a new directory called Electron. All done, so change into that project repo. And there we have it. Everything we'll need to work with throughout the majority of this course. I'll open the project in my editor. We have this main.js file, which will be the main entry point of the application, although we'll cover the project structure in the next lesson. And here, package.json, this being where we define the project dependencies. I have two development dependencies, Electron itself and NodeMon. Again, we'll cover this NodeMon module in the next lesson. Notice, however, that this entry marking Electron as a development dependency is exactly what we saw on the homepage. Here, npm I for install with a D flag, the latest stable version of Electron. This D flag simply telling npm to save this as a development dependency in package.json. Exactly as we already have it here in the project code. Then, back in the terminal, we can install all of the project dependencies listed in package.json by running npm install. That downloads, builds, and done. List our project's installed modules, npm list, with a depth of 0, meaning only show top-level modules, not their dependencies as well. Enter. And as expected, we see Electron version 5 and NodeMon version 1.18, matching what we have here. So with our project dependencies installed, we're ready to run the app. I've already mentioned that main.js is the application entry point, which we're telling Electron here on the main entry. And then in the npm scripts section, I've created a few convenient scripts for us to run with npm. The first being npm's start command, which will call Electron in the current directory. We're only specifying the current directory as Electron will know to look for main.js from this main entry here, but Electron main.js will do the same. We'll cover the remaining two later. Try that first command. In the project directory, run npm start. And the app launches. Quit the app, head back to the terminal, and the process is killed. Notice, however, when I run this Electron command directly, leaving npm out of the equation, we get command not found. This simply being as npm will look for the executed command in the local project modules first. In fact, we can see the script made available by the Electron module to do this. In node_modules.bin, so a hidden bin directory, Electron, which is symlinked to the cli.js file in the Electron module. Don't worry too much about why or how this happens, but simply know that having Electron installed as a local project dependency is best, hence it being the way Electron tells us to install it. That said, we can also install and use the Electron command line tools globally. Again, using npm, we can say npm install with a G flag for global, Electron. I'll forward through this a bit. Done. And now with Electron installed globally, the Electron command is available in the terminal. Run it on its own, and we get this built-in demo app. Or, as before, run Electron in the project directory. Our app launches. So, two ways to run Electron applications for development, but we'll stick to the first using npm as the initiator. Before we move on, I want to point out that whilst Electron was installed at version 5 in this lesson, the first half of the course was created using version 4. This simply being as Electron has a very fast release cycle, just something to be aware of when seeing version 4 in the preceding lessons. That said, every lesson in the course is already up to date for versions 5 and 6. In the next lesson, we'll go over the project code itself and get a better understanding of the structure of a typical Electron app. With our project code ready and running with all its dependencies, we can now go over this app's structure and get a better understanding of how an Electron application works. I'll start the application to better demonstrate. Now, Electron essentially operates with two different types of processes. First being the main application process. This is a Node.js process which we can see running here in the terminal, and will only ever have one of these. This main process then creates instances of the Chromium browser, which is where our application's front-end code will run, HTML, CSS, etc. This process being referred to as the renderer process, and is what we see here, a complete instance of Chromium with the Chrome DevTools open. So main, Node.js, and renderer, Chromium. Now, depending on how many windows your application has, a single application can have multiple renderer processes, or windows. In a more traditional sense, you can think of the main process as being the back-end, or server side, and the window process being the front-end, or client side. Don't worry if this sounds a bit complicated, it's pretty straightforward and I'll demonstrate in a second. First up, the main process. Starting back in package.json, we already know that when Electron is called in this project directory, it checks this package.json file for the application entry point, being this main.js file specified here. Electron then launches the script as the main application process, a Node.js process. So in main.js, first thing that happens is the Electron module is required, using some destructured assignment to reference a few of its submodules. One being the app instance itself, and the other the browser window module, which we use to create a renderer process, or window. We'll cover each of these in detail later on. The app instance automatically gets created, so all we do once the main process has started is listen for the app instance to be ready, at which point we call the createWindow function. We have to always wait for the app to be ready before attempting to create a renderer process. The createWindow function then creates a new renderer process or browser window instance with a width of 1000 pixels and a height of 800, assigning it to this main window variable, which, very importantly, gets created in the global scope of main.js. Remember, main.js is being run as a Node.js process, so having a reference to the main window or any other renderer process here will prevent it from being garbage collected. Just a small but important technicality to how an Electron app runs. Okay, so back to having this new browser window, or renderer, which is of course a Chromium window. We can then proceed to load some contents into that browser window, calling loadFile index.html, this index.html file here. I'll open that, and we see the contents of what the app is currently running. Very importantly, note that in this renderer process, we can still access all of the Node.js APIs from the main process. You might have noticed when creating the renderer, this option here, Node integration set to true, but we'll cover that later. This simply saying integrate Node.js into the renderer process. With Node integration, we can also include separate JavaScript to run in the browser window using Node's require function, renderer.js being a simple JavaScript file which will run in the browser window, no different to any JavaScript in a standard browser, except for having access to Node.js. So that's the basic structure of an Electron app. A main process, running with Node, and one or more renderer processes, being Chromium browsers, run by that main process. Now, when developing Electron apps, we'll be making constant changes in both these processes. So first, the renderer. I'll change this H1 heading to have a bit of styling. Color red. Save that, head back over to the app, and as with a standard web browser, reload with Command R or Control R. There, the renderer updates. We can use modules such as Electron Reload to automate this reload for us when saving changes in a renderer process, but personally I just prefer reloading the window manually in this manner. It at least gives us time to change to the app after saving and observing the changes. Again, same thing for any JavaScript being included in this content. Open the renderer.js file, add a log message, I log out the node process object, save, back to the app, reload, and there we have it in the DevTools. Okay, so how about changes to the main process? In this create window function, I'll log out creating window. Save this, check the terminal where this main process is running, and nothing. Refresh the app as before, still nothing, as that only reloads the browser window content. Now, this part I generally do want to automate for development, as stopping and restarting the app each time we update the main process is a bit unnecessary. To do this, I'll use nodemon. You probably already spotted this in the package.json file as a dev dependency, meaning it's already installed. And in our npm scripts, I have this watch command here. Nodemon execute Electron in the current directory, same as the start script here. Kill the main app process, which closes the app, and run npm run watch, the name of that script in the package.json file. Enter, and the app launches as before. This time obviously having logged that message from the main process as the app restarted. Change the main process again, however. I'll remove the log message and change the browser window width to 1600. Save, and immediately nodemon restarts the main process, which takes us straight to the app with those changes. So removing the need to manually restart the app each time. Hopefully you now have a much better grasp on how an Electron app works. So in the next lesson we'll dig a little further into using Node.js as part of your app and see how to add third-party Node modules from the npm registry. In this lesson we'll see how to use native, meaning compiled, Node.js modules with an Electron app by building them for the specific version of Electron used in the app. Now, whilst on the subject of using Node modules, I want to stress the importance of what we covered in the previous lesson with regards to the main application process being a Node.js process. I very often get asked how to use a particular technology with an Electron app. For example, how would I implement a SQLite database in my Electron app? The obstacle in trying to figure this out is that we are not trying to implement anything in an Electron app. Rather, we're implementing it in a standard Node.js app, as the main process is simply that, a Node.js process started by and using the Electron module. In other words, we can use pretty much any Node module from the npm registry in the exact same way we would any other Node app. This is a very important abstraction to make and remember, as it will allow you to think in the correct context. So let's see an example. On npmjs.com, I'll install this colors module, a simple Node module for producing colored output in the terminal. Back in our project directory, install the module with npm I colors. That's done. So now in main.js, require that new module with const colors equals require colors. Logging out with the colors module in rainbow colors, hello world. Save. Start the app, which I'll quit, and there we have it. So a random Node module used in a matter of seconds right inside of our Electron app. The main purpose of this lesson, however, being to show you how to use native modules. A perfect example of such a module being the bcrypt password hashing library. I'll copy the most basic example of hashing a password from the docs. Replace this log and colors module with that, not forgetting to also require the bcrypt module. Bcrypt equals require bcrypt, which we still have to install. And all we're doing here is calling bcrypt hash. I'll make this a string, so hashing the password my plaintext password with 10 salt rounds. And in the callback, bcrypt will provide us with a hashed password, which I'll log out. Save this. Install bcrypt locally. And at this point, we see the module being compiled automatically by npm for my version of Node.js's V8 engine. All done without any problems. Clear this, start the app, and it breaks. Electron quit unexpectedly, meaning the app crashed. So what happened here is that Electron is using a different version of Node's internal V8 engine than the version on my machine, meaning at the moment bcrypt was compiled for the wrong version and crashes. Now, there's a number of ways to fix this, and if you check the very last archives section of this course, you'll see one of the earlier, more manual ways of doing this, should you be interested. A much simpler way, however, is using the Electron rebuild command line tool. This again comes in the form of a Node module, so I'll install that globally this time, npm install g electron rebuild. I'll forward through this. Done. So now, having Electron rebuild available on the command line, rebuilding the already installed bcrypt module for our version of Electron is as simple as running electron rebuild bcrypt. Rebuild complete. Start the app again. This time it launches without issue, so quit. Check back in the terminal, and there. As expected, we see the hashed password being logged out in the terminal. Being able to debug your Electron application is critical for building reliable apps. And having covered the initial application structure, you've probably already figured out how the renderer process will be debugged and inspected. This line here, main window being that main application window we're creating, web contents, open DevTools. This method basically opens the Chrome DevTools for the window it's called on, as soon as it's created, resulting in this window here, a completely standard version of the Chromium DevTools, exactly the same as you're familiar with in your desktop browser, allowing us to debug any code run inside of the web contents of this window, so the loaded HTML, JavaScript, and CSS. That's pretty straightforward then. But let's now see how we can debug the main process instead. Everything here in this main script and its dependencies. Or, in other words, the node.js process. Now, there's a number of ways to inspect this process, including using Visual Studio Code or a similar IDE, and I've linked to the relevant documentation explaining that in the lesson resources. For our purposes, however, I'll once again use Chrome. Chrome DevTools provide excellent JavaScript debugging, so it's a perfect fit for this. Step 1 is configuring Chrome to listen on the port we'll be debugging the app. Node essentially creates a WebSocket connection on a local HTTP port for debugging. So to start the app with debugging enabled, we can run electron with an inspect flag equal to the port we want to use. Anything above port 1023 should do. I'll make this port 5858, running in the current directory, same as our npm start command, enter, and the app launches as normal. But in the background, we now have the node debugger listening on port 5858. As mentioned, we'll be using the Chrome inspector, so in a new Chrome window, navigate to Chrome://inspect. Which brings us to this DevTools Devices menu. Keep in mind that this page might look different on newer versions of Chrome. Click on Configure and add that new debugger session as a target, localhost 5858. Done. And immediately our Electron app shows up under Devices, where we can now inspect the main process for this target by clicking this Inspect link, launching a new DevTools window for our app's main process. Click into the Sources tab. There, main.js being listed as a resource. Okay, so with the Chrome inspector configured, let's see how to trigger breakpoints and debug our code. Close this, back to main.js, and to demonstrate, I'll add a simple breakpoint in this main window's closed event, meaning the callback that runs when we close our one and only app window. Debugger, being the standard breakpoint trigger. Save, restart the app with the inspector. Now, back in the Chrome window, we have to relaunch the inspector for this target. There. We see the debugger statement, so go ahead and close this window. and the breakpoint is triggered, stopping the window from being closed and jumping us straight into this point in the code. Resume code execution here, and the window continues to close. So this is about as simple as it gets for triggering breakpoints in the main process. But as we have to relaunch this inspector window for each new session of the app, we might sometimes need to execute an immediate breakpoint as soon as the app is started, allowing us to step through each part of the app startup. I'll remove this breakpoint, back to the terminal, and now to break on launch, we can run, instead of just an inspect flag, inspect brk, or break. Same port, enter. This time nothing happens as the main process gets halted before it can create main window. Switch over to Chrome and relaunch the inspector. We see the app being halted on the very first line of init.js, being the script Electron uses to start the main process, where we can now step over, into, and out of code right from the start. Very useful, especially for debugging functions in the main process that happen on launch. For example, this bcrypt hash that gets logged out. If we don't break prior to this running, we'll never get to open an inspector window fast enough to see it. So instead, add the desired breakpoint, right before this log message, break on start as before. We get no window, of course, as it's all halted. Relaunch the inspector, but this time with the inspector ready and the breakpoint set, simply allow the app to continue execution. Here, click, and the app breaks where we specified, in that bcrypt callback, where we can inspect the value of this hash in real time. Continue again, and the app launches. So, as you can see, once configured, debugging the main process is pretty simple. If you would like to learn more about debugging with Chrome DevTools, I've linked to some resources. In the next lesson, we'll see how to reset our project before getting started with the Electron API. We're nearly ready to get started with the actual Electron API, but as we've been adding bits of code throughout this first section, we can very quickly reset the project to its original state with the third and final npm script in package.json. This reset script, calling getReset hard. This being one of the reasons why using the cloned version of this project over the downloaded version is preferable. As a quick reference, we're expecting these package.json dependency entries to be removed, and in main.js all of this bcrypt code. Back to the terminal, execute that script by running npm run reset. That's done. Check back in package.json, and those added entries are gone, leaving package.json exactly as it was when we first cloned it. Same for main.js, no more bcrypt code. Check our installed dependencies, npm list depth 0, and same, bcrypt and colors have been removed. That's basically all there is to resetting the project. So throughout the course, if you see me starting from scratch when demonstrating a new part of the API, this would be how to get your code back to that point. Also, don't worry about losing lesson code. Each lesson's final state will be in the lessons directory here. We're finally ready to start exploring the Electron API. Now, you might have noticed that the next 3 sections of the course is split into individual sections of the API. The main process API, the renderer API, and lastly, shared API modules. This breakdown of different API modules is very important, as trying to use an API module for the renderer process won't work in the main process, and vice versa, with the exception of a handful of shared modules, which, as the name implies, will work in either process. Electron makes this very clear in its documentation also, and to get a better breakdown of which modules belong to which process, we can navigate from the Electron homepage to Docs, API Reference, where we see each and every one of the Electron modules with its designated process. Main, renderer, or main and renderer, also referred to as a shared module. Throughout the next 3 API sections, we'll mostly cover these individual modules in a very specific manner, meaning we won't necessarily be building anything, but rather seeing how to use a specific module. Having the fundamentals of the API covered this way will allow us to build real-world apps incorporating all of Electron's functionality in the later sections of the course without the need to first cover individual modules. So with that said, let's get started with the first and most important module in the Electron library, the app instance. Now, we've already looked at some of the very basic workings of the app instance, and very importantly, this will be the only module where we won't be creating an instance of the module in order to use it. Electron does that for us when the app is launched. And as the Electron documentation states then, on this instance we control our app's event lifecycle. Things like quitting the app, relaunching, etc. The very first of these events being the ready event, here. This fires as soon as our app instance has been created and is ready for us to use. At the moment we simply pass create window as this event's callback, but to better demonstrate I'll change this to an anonymous callback function, logging out app is ready. After which we can call create window to create our app's browser window. I'll start the app with that automatic main process reloading, npm run watch. The app launches, and if we check back in the terminal, we see that log message on the main process. App is ready. We can also perform a manual check on the app instance to see if it is ready. This time, right in the global scope of this main.js script, not waiting for the ready event to fire, log out checking ready, appending app is ready. Save, which relaunches the app, check the terminal, and there, before the app's ready event fired, we checked and got false. If, however, we were to wait a couple of seconds with this check, I'll create a timeout, logging that same message after 2 seconds. Save, check the terminal, and this time, as the check was run after the app was initialized here, we got true. This method of checking your app state can be particularly useful when working with external modules outside of this main script. Okay, so that's always going to be step 1 of our app's lifecycle, knowing when it's ready. Equally, we can control the end of the application's lifecycle by listening for this before quit event. Let's see an example. I'll get rid of this timeout, add a new listener on the app instance, listening for before quit, pass a callback in which we'll log out app is quitting. Save, the app relaunches, and in the terminal we have only this app is ready message from the ready event. But quit the app with Command Q or Control Q on Windows, head back to the terminal, and there we have it. App is quitting, right before NodeMon logs a clean exit, meaning the app has been terminated gracefully. I'll just restart this. So, knowing when the app is being quit, we can go one step further and actually prevent this from happening. Electron provides us with an event object as this callback's first argument. I'll call it E. And on that event object, call prevent default, the standard JavaScript method name for preventing default event flow. Save this, hit Command Q again, and nothing. The app simply does not quit. Check back in the terminal, there, preventing app from quitting. No matter how many times I try, each attempt is stopped. This might seem like a trivial bit of functionality, but let's say you quickly want to save a user's work before quitting, this would be the perfect solution. Listen for before quit, stop the app from quitting, write the user's data to a file or database, and then proceed to manually quit the app as the user intended by calling app.quit. Okay, before we take a look at more examples, I want to point out these platform-specific notices in the docs. For example, this open file event. This is Mac-specific as it's something you can only do on a Mac, being when you drop a file onto the application icon, implying you want to launch the app with that file. giving you the file path in order to read it or do whatever else you wish. We'll cover platform detection later in the course, but it's just important to be aware of the platform restrictions throughout the docs. I'll skip over these. Here, some more cross-platform events. Let's see these window focus events: browser window blur and browser window focus. I'll change the before quit listener to browser window blur. Logging out app unfocused. Duplicate that for browser window focus. App focused. Save. The app relaunches, which brings it in focus, so firing the browser window focus event. And now, before switching to the terminal to see that log message, notice that in doing so, we'll be unfocusing the app, or blurring it, and thus expect a second log message from the browser window blur event. Switch, and there. The app's browser window was focused immediately after the app initialized, and then unfocused when we switched to the terminal. Back to focus, unfocus, and 2 more logs as before. These events allowing us to know when a user moves away from our app or when a user clicks back into it, like so. Potentially useful for displaying an important message as soon as the user engages with the app, or updating some data, etc. We have a lot of these events covering pretty much anything happening with the application. But further down, we can also manually trigger some of these events or actions on the app. Here, app instance methods. I've already mentioned app.quit in the context of preventing an app from quitting for some final tasks and then quitting manually. So let's try that. Get rid of browser window focus. I'll reuse this blur event. Set a timeout, calling app.quit. After, say, 3 seconds. We could actually write this a bit nicer, passing app.quit as set timeout's callback. There. So as soon as the app loses focus, wait 3 seconds and then quit. Save. The app launches in focus, so click out of this main window, and 3 seconds later, gone, with NodeMon reporting a clean exit as before. We also have variants of quit, like restarting the app or even forcing an immediate exit instead of a graceful quit. Further down, we see that isReady method we used earlier, focus to manually bring the app back into focus, and some Mac-specific show and hide methods. A way to get the full path to the app on the user's machine, and very importantly, the getPath method. This is going to be our go-to for knowing how to interact with the user's file system, providing us the paths to any of these common file system locations. Let's see a couple. I'll get rid of this blur event, and in the ready callback, I'll log out app.getPath for desktop, another for music, the app's assigned temp directory for temporary resources the operating system can remove at will, and the all-important user data directory. This path returned here should always be the default location to store data associated with your application. This can be anything from files, JSON data, or even a simple SQLite database. Just be sure to store app resources here, as that will ensure you have consistent paths without running into permission issues or locations that don't exist. Not to mention that Electron will automatically provide the correct path for the user's operating system. Save this. I'll just restart this. And there, each of those locations, unique to my app, with the user data path being a common Mac directory specifically created for my app. Again, an important method to know and use. Of course, as with the events, we have many more methods, too many to cover in this one lesson, but they are all very well documented. Getting or setting your app's name, getting the current version, and so on. You should now have a good understanding of what the app instance is used for and how to use it to its full potential. In the next lesson, we'll see arguably the second most important part of the main process API, the browser window module. Over the course of the next few lessons, we'll be taking an in-depth look at the browser window module. This of course being the module with which we'll create renderer processes, or windows, for our app. Now, we've already covered some of this when looking at the structure of an Electron app, but to reiterate, let's step through this in a bit more detail. Inside of our create window function, we assign to this global variable, main window, a new instance of Electron's browser window, for which we require the module from Electron here. We configure this browser window with a couple of parameters, setting its width to 1000 pixels and its height to 800, and we tell Electron that we do want Node.js integrated into this renderer process by setting node integration to true on the browser window's web contents. This web preference parameter being for configuration options on the web contents, another topic we'll cover in detail later. This giving us access to Node.js from our browser windows, things like using require, etc. Then, once we have a new browser window, or renderer, we can load some HTML into that Chromium window, calling load file with the HTML file to load, index.html. Another important point here, in both the documentation and older examples, you'll see index.html loaded with the load URL method instead. This again is outdated, and load file is the correct way for newer versions of Electron, but we'll see an example of this in a second. Then open the dev tools of that web contents in the browser window with Open Dev Tools, this being for development only of course, and finally register a listener for when this window is closed, to unset the browser window instance. Okay, on the subject of load file versus load URL, let's see the difference. When loading content into a browser window, we use load file for any content local to our app. For example, this index.html file. This simply checking for a file in the current directory. But keep in mind that this browser window instance is essentially a Chromium browser window, so we are by no means limited to loading content from local files. In earlier versions of Electron, we would have used load URL passing a file path with the file protocol, meaning that method still exists for the purposes of loading URLs, not files. Let's see an example. We don't need dev tools, so comment that out. I'll duplicate this, comment out the load file version, and instead call load URL loading over https google.com. Save. I'll start the app with the watch command. Takes a second as the content is being downloaded, and there. The HTML from google.com loads into our main window. So simple enough. But as you probably noticed, loading remote content isn't all that graceful and should be avoided wherever possible. We want our desktop apps to be fast, so local files is definitely the way to go, avoiding the initial blank window whilst the content is loaded. That said, we still get some of this blank screen flicker when loading a local file. I'll change this back to load file for index.html. And to make it a bit more obvious, let's change the background of index.html to have some color. Add a style tag in the head element, setting the body to have a background color of Dodger blue, or the corresponding hex code, and the body's height to 100%. Again, just for demonstration. Save that, which of course doesn't reload the app as we're editing content in the renderer process. And now, immediately as I save main.js, which will reload the app, I'll switch over to the app so we can see it appear and look for that flicker of a blank window. Save. There, index.html is loaded almost instantly with that blue background. But we definitely do get to see a somewhat nasty flicker. This will of course not be a problem for every app, but in case of a full color interface like this, it will be noticeable. Again, the aim here is to make our Electron apps feel like native apps, so this should be handled more gracefully. Back in the docs, we have a small section on doing just this, showing window gracefully, with two ways of achieving this. First, we can use the browser window's ready to show event, hiding the window until all of its content is loaded. Let's see this. Back to main.js. Start by setting the browser window to be hidden initially, passing a new configuration parameter when it gets created, show false, meaning we won't be able to see the window. Then add a new listener on this browser window instance, main window on, ready to show. But seeing as this event will only ever fire once, the better alternative would be to listen once, just telling Node to discard this listener after it's been triggered, saving a bit of system memory. And as this event's callback, we'll pass it mainWindow.show. So call the show method on mainWindow when this fires. I'll manually go to the app before it launches again to better observe this. Save. And there. Still a very slight flicker, but that has more to do with the CSS being processed than the content being loaded. The downside of this first option to show the window gracefully is that it can delay the perceived launch of the app a bit. So as a simpler alternative, we have a second option, changing the color of that initially empty window. I'll get rid of this listener, and instead of the window hidden initially, I'll set its background color to the same main color used in the content, Dodger Blue. Save. And this time we can't see any trace of a white flicker as the actual content loaded in seamlessly over that blue background. So, two different approaches based on what will work better for your app. Next up, we'll see how to create multiple windows and set them up as parent-child configurations. We now know how to get started creating a browser window instance and load some HTML content into it. So in this lesson, let's take that one step further and see how to create parent and child windows. Still on the main browser window documentation page, scroll down a bit. Here, another dedicated section on the topic. But before we start creating these links, we'll need a second browser window. Remember, we can create multiple renderer processes, being instances of the browser window module running Chromium, from a single main process. Over to main.js, declare a new global variable to reference the new window, secondary window, duplicate this main window instantiation, this time assigning the resulting browser window to that new variable, secondary window, with a width of 600 and a height of 300, just so we can tell them apart. I'll load the same index.html file into the new window for now. We don't need DevTools, so comment that out. And finally, duplicate this closed listener in order to unset the secondary window. Done. So doing exactly the same as we did when creating main window. I already have the app running with a watch command, so save. And the app launches with those two windows, main window and secondary window. The second appearing on top as it was created and shown last. In this state, they behave as you would expect, completely independent of each other. You can even close one of them. So, simple enough, but let's say the secondary window was created as part of the main window. For example, you click something in the main window, which then launches secondary window. In such cases, which is going to be most of the time when dealing with multiple windows, you're going to want to make the second window a child of the main app window. So, let's see this. I'll change the content of the secondary window also, duplicate index.html, secondary.html. Change this main heading to secondary window, and in the style tag set the body to that same style as we had it in the previous lesson. Background color Dodger Blue, with a height of 100%. There. This will just make the separation a bit clearer when demonstrating. Update load file with that new HTML file, secondary.html. And now, with that done, we can make secondary window a child of main window by setting its parent option to main window. So this window's parent is main window, meaning it can only exist alongside of main window. Save. That launches exactly as before, this time with the new content. The child window can still be moved around freely, but being bound to this main window, its parent, when I move the main window, it follows along. Notice how it also does not get blurred to the back of main window. Back to the child window, resize it, move it, and so on. We can even close the child window as before without it affecting the main window. But as soon as the main window is closed, they're both gone. So a simple one-way relationship. This can be done slightly differently by making the child window a modal window also. Still a child of main window, but of type modal. Again, in the secondary window's configuration, set modal true. Save. And this time we get an attached child window that shares the same top bar as its parent. This of course being a great option for forcing the user to this child window, as you cannot interact with the parent window until this is gone. But not having a close button for this modal makes it a bit tricky also. So the idea here is to display the modal to a user, and once they've performed some action inside of that modal child window, you close it programmatically within main.js, or wherever you created it, allowing the user back to main window. I'll demonstrate a basic version of this using some timeouts. In order to show the modal window then, we'll want to first hide it. On secondary window's configuration, show set to false. Then, in a timeout, have the callback execute secondary window dot show, with a second timeout immediately after to start the countdown to close it. Keeping in mind that in order to close this child window, you don't have to get rid of it completely. You could instead call hide, meaning at a later time you could bring it back by calling show again. Alternatively, if you're definitely done with it, close, meaning the reference to the window can be destroyed as well. Secondary window equals null. We still need the timeout durations, show after say 2 seconds, and hide 3 seconds after that. I'll also remove this closed listener for the secondary window as that's redundant now. Save. 2 seconds later the modal is displayed, and another 3 seconds later it retracts in the same way, rendering our main window usable again. That's it for basic parent-child windows, but I want to point out that the standard behavior for parent and child windows, especially modals, can vary quite a bit depending on the platform, so it's definitely worth reading through the platform notices in this section. In this lesson, we'll take a quick look at creating frameless browser window instances. Electron provides a dedicated page to this concept, which I've linked to in the lesson resources. Now, by default, and certainly for the majority of use cases, an app window will contain the native user interface elements of the operating system. On Mac, for example, the top bar and window control buttons, close, minimize, and maximize, similar to Windows and Linux. But in some cases, the content being presented in an app window might be better suited to not having these elements. A perfect example being something like the QuickTime video player interface, keeping in mind that this will require alternative ways of interacting with the window. Let's see the most basic example. In the main window constructor, set frame to false. I'll get rid of the dev tools again, save, and there. The exact same app window as before, but this time round without any native window elements. As I mentioned though, with this being HTML content, we no longer have any way to interact with this window. For example, we can't drag it around freely. This wasn't as apparent before, as the top bar allowed us to grab and move the entire window, but instead what happens when I click and drag is I'm selecting the HTML content. Not a great look for a native app. So to fix this, we can essentially specify exactly where we want to allow dragging and selecting within our app. Back to our code, and very conveniently we can achieve this with some CSS selectors. This might seem a bit odd at first, but keep in mind that what we are interacting with inside of a browser window is nothing other than the web contents of that window, HTML. And CSS's main purpose is that of styling such HTML. Styling of course includes behavioral styling such as selection, etc. In index.html then, I'll give the body element a style tag. A style tag in the head would have worked also. Setting the WebKit user select property this WebKit prefix being how you'll see it written in the docs, but it's not actually required. This tag has been standardized and can simply be written as user select. Either will work though. None, meaning nothing in the body element is selectable. Save and manually reload the browser window content with Command R. Try selecting again, nothing. But we still cannot drag this frameless window, which is what we originally set out to do. So back to index.html, and now to also make this entire body element a draggable region, set WebKit app region to drag. This being a non-standard tag, so the WebKit prefix is required. Save this, and main.js to trigger a reload. And now, keeping in mind that our body element does not have 100% height, it's around the content here. So click, drag, and the app moves as expected. Of course, it's not always going to be as simple as making everything in the body tag not selectable and draggable. Some of the user interface elements will still have to behave normally. To demonstrate, I'll add a couple of breaks with a new input element of type range, this being an HTML5 range selector. Name can also be range, with a minimum value of 0 and max of say 10. Save that, reload the window content, and now when I try and adjust this slider, the window drags instead. That's because this element inherited the behavior from its parent, the body tag. So, depending on your app's content, you'll have to specify where the user can and cannot interact, drag, select, etc. I'll fix this range slider, give it a style tag, with the same property causing the trouble from here, but instead setting it to no drag. Save, try again, and this time it works, while still being able to drag the frameless window on the body element. Overall, a much better experience with a more native user interface. That's the basics of creating a frameless window. But again, be sure to take note of the platform notices in the docs, as there's different options and styles for such windows depending on the user's operating system. I'll show one last example of this. Let's say instead of hiding all the user interface elements, we simply want to hide the title bar. We can set title bar style to hidden. I'll add a bit of padding to the top of the body tag, as the content will now push up behind the window buttons. Save both files, and there. Same frameless window, but we have those native window buttons floating over the content. Having covered a few key concepts of working with the browser window module, we're still left with an enormous amount of properties, methods, and configuration options to help create exactly what you need. In this lesson then, let's go over some important and interesting properties and methods of this module. First up, configuration options. When we create a new browser window instance, we can define a number of different options to customize it with. All of these here. For example, the minimum width and minimum height. At the moment, with only an initial width and height specified, when I resize the app window, main window, I can keep going to the point where this no longer makes any sense. If a user ever requires a window to be this small, it might as well be minimized, as it's no longer usable. This is where min width and min height comes to the rescue. Back in main.js, we can set on this main window constructor a minimum width of say 300 and min height of 150. These values will of course depend on the content of your own app. Save, resize that window back down as before, and it sticks at those minimum dimensions. We can do the same for maximum width and maximum height, but this is less of a problem as the user will always be restricted by the available screen space. Again, should the content specific to your app require the maximum size to be limited, the option is there. Equally, we can change the default window behavior, like disabling resizing of the window, the ability to move it around, or even minimizing and maximizing it. The list goes on. There's an option for pretty much anything you would ever want to change on a window. Next, we get to the instance events for the browser window. Much like the app instance we looked at first, this allows us to listen for key events on the window instance. For example, focus and blur, like the app instance, but specific to a given browser window. I'll demonstrate. Add a second window, sec window. Duplicate the main window, but assign the browser window instance to that sec window variable. Change the dimensions a bit to differentiate them. Load index.html into sec window. And get rid of the DevTools, with lastly a listener to unset this new window instance when it's closed. There. With that done, I'll add focus listeners for each window. Main window on, focus, pass a callback, which logs out main window focused. Same for sec window, second window focused. Save this. Those two windows gets created, and now in the terminal, I'll bring it over so we can observe. We see a message second window focused, which happened when the app was launched. Click back into that second window, we see another similar log, meaning this window came into focus. Click the main window, and that fires its focus event, and so on. So window specific. Very importantly, note that the app instance will fire its browser window focus event every time one of these windows come into focus. I'll add that listener, app on browser window focus, which if we look at the naming here is essentially a trigger for any of these focus events from a browser window. Logging out app focused. Save. There. The app instance fires its focus event, not caring which window came into focus, and with that being the second window, we see its log also. With this happening every time a browser window is focused. See this by switching to the main window, the app event fires, then the browser windows, back to second window, and so on. We also have the usual events like show, hide, etc., all very self-explanatory. And a bit further down, static methods. These being methods unrelated to a specific window, but rather useful utilities for managing and working with individual window instances. For example, getAllWindows, a way to get references to all of the existing browser window instances. So, being a static method, on the browser window module, call getAllWindows, which I'll log out. We're expecting two instances, main window and sec window. Save. Check the terminal. There. GetAllWindows returns an array with those two browser window instances. So, pretty simple. We can also instead get the window currently in focus, or by a specific window ID. And again, a bit further down, now in the Instance Properties section, we see that getting a window ID is as simple as checking the ID property of a window instance. So, for example, mainWindow.id will be the ID for our main app window. With finally the browser window instance methods. These all being very similar to the corresponding app instance methods, but specific to a browser window instance. Close, focus, blur, checking if a window is visible, and so on. Let's see a basic example. I'll comment out all of this. Listen on sec window for when it's closed. Call on the main window instance maximize, meaning when sec window is closed, this event fires, which then calls the main window's maximize method. Save. These two windows load as normal. We can switch, focus, and so on. But the second I close sec window, main window is maximized. So, whilst an arbitrary example, you can see how using a combination of browser window events and methods, multiple windows essentially become part of one app, having linked interactions and behaviors. As before, we have many of these instance methods. Things like checking if an app is running in full screen mode, changing the window's background color, and many more. I'd encourage you to have a quick look through these just so you're aware of what is available. When we get to the project section, we'll start implementing some more real-world use cases for these. In this final short lesson on the browser window module, let's see how to manage your Windows state in between app launches. For example, with the app open, I'll resize this main window and move it to the top left of my desktop. Quit. Then, to relaunch this from the nodemon watch command, we can simply type rs. Enter, and there. Our last window size and position is completely forgotten, with the window returning to its original size of 1000 by 800 in the center of the screen, which is the default position. This is to be expected as it's how we are creating the window. So to add state management then, I'll turn to a simple npm module, Electron Windows State, link in the lesson resources, which states a library to store and restore window sizes and positions for your Electron app. Install this module, npm install, saving as a production dependency, which npm will do by default anyway, Electron Windows State. Stop the watch command, enter, and done. I'll restart the watch script. There. We now have this module available for use in our app. So, going by this very simple example configuration here, let's add some basic Windows state management on our single app window, main window. First up, we'll need to require the module itself. Const Windows State Keeper equals require Electron Windows State. Then, in our create window function, we can create a new Windows State Manager from the module. Let winState equals Windows State Keeper, passing in a configuration object. So this winState instance will be responsible for managing the state of our main window. And as part of its instantiation, we have to tell it the default position and size of the managed browser window, should a previous state not exist. Default width, same as our window's initial width, 1000, and default height, 800. And in turn, we can set the browser window to be created with the width and height provided by the Windows State Keeper, setting its width to winState.width and height to winState.height. That takes care of our window size, but as part of the previous state, we'll also want to supply an x and y coordinate of where to create this window. X being winState.x and y winState.y. We don't need to specify defaults for this x and y coordinates in the Windows State Keeper constructor, as this will default to the same center as the browser window. Comment out the DevTools as well, don't need that. And finally, the very last step being to tell winState which window state it will be storing, calling winState.manage main window. That's it. I'll save, which relaunches the app in its original state, as it's only started to be managed as of now. Change this default window state with a resize and moving it to the top right corner. Close this window, as only closing a window or quitting the app will persist its state. Save main.js again to reload the app, and this time it relaunches back where we left it and in that same position. In this final lesson on the browser window module, we'll take a look at the web contents property of the browser window module. Very importantly, the web contents property is a module in itself, despite being a property of browser window, hence it having its own dedicated lesson. The best way to think of a web contents instance then is that it represents the content loaded into a browser window. So the browser window is where our content gets loaded into, being a Chromium browser instance, and then that very content being the web contents. As we'll be working with the web contents of our main window in this lesson, I'll start by creating a reference to that property. Let wc for web contents equal mainWindow.webContents. Saves us having to reference the full browser window.webcontents each time. Comment out the DevTools for now, and log out this new web contents variable. For the remainder of this lesson, I'll bring my terminal window onto my desktop to avoid switching. So to make space for that window, I'm also going to shift the starting position of our main window to the left of the screen, setting on the browser window constructor an X property of 100 and a Y property of also 100, meaning launch this window 100 pixels from the left of the screen, being the X-axis, and 100 pixels from the top of the screen, being the Y-axis. I already have the app running with the watch command, so save. There, we see in the terminal our main window instance's web contents object being logged out, with main window launching 100 pixels into the screen. With our web contents instance referenced, let's jump into some useful functions and events of this module. Again, this is a very large API, but for the most part it's a standard node event emitter, just like the Electron app instance or a browser window instance. And many of the events and functions will be familiar or self-explanatory. To start, we see a few simple static methods listed. Again, familiar: get all web contents, get the currently focused web contents, or get a specific web contents instance from its ID. Now, as mentioned, web contents is a module in itself, despite being a property of the browser window module. So in order to access static methods, meaning methods not related to a specific web contents instance, we'll have to use the web contents module directly. For example, log out webcontents.getAllWebContents, requiring this web contents module as with any other Electron module. Like this. Save, and there, we get the exact same log as before, except this time it's inside of an array, this being as we only have that one web contents instance. I'll clear this, head back to the documentation, and if we scroll down a bit further, the next rather large section is instance events. We've seen a few of these events directly on the browser window module, but here we now get much more detailed events relating to the state of the content being loaded into the browser window. For example, did finish load versus DOM ready. Two similar events but with significantly different uses. I'll log those out to demonstrate. Web contents on did finish load. Pass a callback in which I'll log out content fully loaded. So this event meaning all of our content is ready. Duplicate this for DOM ready. Logging out DOM ready. This time signaling that the structure or document object model of the HTML being loaded is ready. We might still have unloaded images, etc., but the structure is ready to be interacted with. I'll add a remote image to better demonstrate this. Open index.html. Image, using the placeKitten service with a 500 by 500 image. So notice now that DOM ready will fire as soon as all of the HTML is ready, including the image tag. But did finish load will only fire once the image content is also loaded. I'll slow the recording down a bit to better demonstrate. Save. DOM ready fires almost immediately as there's very little HTML. And then as soon as the image content loads in, did finish load also fires. Meaning these web contents events gives us way better control over the exact points of content being loaded. We also have several in-between events like did fail load, did start load, or did stop load. Then a bit further down we have this new window event. New windows being an important topic in an Electron app, as we don't really want HTML links to just create new windows without our permission, especially when working with remote content, which is to be avoided wherever possible. The default behavior then is for Electron to simply create a new browser window instance and load the content for the new window into that window. I'll demonstrate. Duplicate one of these listeners, commenting out our content status events. Change this event to new window, only to observe for now, with the new window event callback providing us the usual event object and the URL that triggered the new window. So using that, I'll log out in an interpolated string, creating a new window for that callback's URL argument. We'll also need a link to test this with. Change the placeKitten image to be a link instead, linking to that same image, with an h3 text link of kitten. Not forgetting the most important part of this link, a target attribute with a value of _blank, instructing the browser, or browser window in our case, to open this in a new window instead of simply navigating to the link. Save this, and main.js, click that new link, and Electron automatically creates a new browser window with that image as its web contents. We also have the log message from the new window event in the terminal, pointing to that link URL. So whilst this is very convenient, we don't have too much control over automatic new windows, which is where the new window event can help us intersect the opening of new windows and handle it ourselves instead, should that be the requirement for your specific app. For example, in this event, we can call on the event object prevent default to instead prevent Electron from following the default behavior of creating a new browser window. Save. Click that link again, and this time nothing happens apart from our log message in the new window event. This way then we can instead use this URL, which would have triggered the new window, and instead load that content into a window of our own, or do whatever else we like with it. Much more control. We also have other events for controlling navigation from standard links. Will navigate for catching a link click before the content navigates to that new link. Did start navigation, which will be immediately after a click, or will redirect for intercepting redirects triggered by links. We can also listen for web contents becoming unresponsive, possibly using this to inform the user of such events with a loader or something, or even when the web contents crash, allowing us to maybe manually reload the contents. Again, remember, the web contents can hang in the renderer process and the main process will remain fine, these events being good additions for distributed applications. Then, a bit further down, we see before event input, a very useful event for capturing user input. Let's see this. I'll duplicate this event again, comment out the old one, listening on before input event, which provides us in its callback the event object and the input object. This input object containing a whole lot of information about the user input captured. For example, I'll log out input.key followed by the input.type. Save. I'll press the A key on my keyboard, and there, two events get logged. First, the A key being pressed down, being called key down, and then immediately after for the same key, key up, being when I released the key. Press enter, and same. So an extremely useful event for checking or even changing a user's input. Next, we see some events for knowing when a user opens the DevTools panel, focuses it, and so on. Note that most apps will of course not enable DevTools in production. This will only apply to hackable apps like the Atom editor I'm using for this course. Some SSL certificate events, and for working with HTTP authentication, we have this login event. For anyone not familiar with basic auth, it's essentially a way to secure HTTP with a simple username and password. I've linked to some good articles explaining it in more detail in the lesson resources. Essentially, when a user attempts to visit a URL with basic HTTP authentication, the browser will prompt the user for a username and password. In an Electron app, however, that's not going to be how we handle authentication. So instead, we can allow the user to load secure content by listening for a login event and then authenticating on their behalf. Let's see a simple example. To do this, we'll have to load some content with HTTP authentication. So comment out our main Windows load file function, adding instead load URL with this HTTP bin URL. HTTP bin is a simple service that allows us to test all manner of HTTP features. This link is in the lesson resources. This URL then requires a username and password, or else we'll get refused with a 401 unauthorized status code. So before actually authenticating this, let's first see a failed authentication. We can get the response code using another web contents event I've already mentioned, did navigate, being the event that fires after a page has navigated, be that via a link clicked or content being loaded. The event provides us a few arguments in its callback: the event object, the URL to which the navigation happened, a status code, and a message. I'll log those out, navigate it to URL with response code, status code, and a second log with the message provided by the response. Save, and we get the unauthorized log as the secure content fails to load. Response code 401 with a message of unauthorized. So let's handle this login event. Web contents on, login, with the callback exposing the event object, the request object, auth info, and finally a callback function we can use to perform the authentication with. I'll log out logging in as soon as this event fires, and then proceed to log in with the event callback's provided function, this callback argument, calling callback with the username as the first argument, being user, and the password as the second, passwd. That's it. This should now fire as soon as the basic auth happens, perform the authentication, and then proceed to load the content, which in turn will fire this did navigate with a success status. Save. We see logging in, and a moment later the JSON from this HTTP bin endpoint loads, showing us a did navigate with a 200 status code. Basic auth being a very unlikely problem for most apps, but should you want to provide your app with some secured remote data, this is a great and simple solution. A bit further down, we see an event for retrieving search results in a content search, this being initiated with the findInPage instance method, and some media events for knowing the state of video or audio in the content. Let's see a simple example of this. I'll comment out these auth and did navigate events, add a video file to the project for us to test with, mgm.mp4, a small mp4 video file. This file is in the lesson directory should you want to use the same one. So what we're going to do here is embed this video in our HTML, index.html, and listen for play and pause events. Web contents on, media started playing, in which I'll add a log message with video started. Duplicate that, this time listening for media paused, logging out video paused. Add that video to index.html. I'll replace the kitten link using a video tag with source current directory mgm.mp4. Don't need these. Adding video controls with the controls attribute and a width of 650. There. We still need to change the content back to loading index.html. Comment out the HTTP bin URL. Done. Save. We see that video loading, and when I start the video, the first event gets triggered. Pause the video, video paused. So a really simple listener for knowing when a user is interacting with media in your app's content. The next very important event I'm going to demonstrate is this context menu event. This being when a user right-clicks on something. Now, as far as actual menus go, we'll cover that in an upcoming lesson, but this is an important event to understand as users quite often right-click for various reasons. First thing to notice is that this event, despite having only 2 arguments on its callback, contains a lot of data on the second, params. I'm going to demonstrate a basic example of accessing this. I'll duplicate one of these events again, comment out these, listening on our web contents instance for context menu. Use the provided callback arguments, event and params. And what I'll demonstrate is how to check, for example, whether a user clicked on a media element, what type of media it is, and where the user clicked in the app, an X and Y coordinate. So log out context menu opened, meaning the user right-clicked, on params.mediatype at X, params.x, Y, params.y. Save. Perform a right-click on that video element, and there. Context menu opened on video at X581 and Y261. These being exactly where the click happened. So a second click on a different point having a different X and Y coordinate. Equally useful, we can also check whether a user selected some content when the right click happens. Change this log to user selected text params.selection text. And should a user have some selected text, are we able to copy the text? Useful for knowing whether to show a user the copy command in the context menu. Again, we'll see how to create these on the right click later. Selection can be copied. params.editFlags.can copy. Save. I'll select this Hello World heading. Right click, and there. User selected Hello World. Selection can be copied, true. So already we're able to access HTML content from the renderer directly in the main process. Back in the docs we have a few more events, with the next section being instance methods, some of which we've already seen, load URL and load file. Of course, we are calling these on the browser window instance, not the web contents of that browser window, but essentially it's the same. With web contents being a property of browser window, a lot of their methods are shared. We can also initiate a download, focus a web contents instance, or reload the content manually. Perform manual navigation with go back and go forward, and an extremely useful instance method, execute JavaScript in the web contents. Let's see an example of this. Let's say we somehow want to make use of this selection text we got in the context menu event, but do so in the web contents. I'll assign the selection to a variable, selected text equals params.selectionText. Calling on the web contents, execute JavaScript with the code alert selection text, meaning on the web contents, so the front end, so to speak, call the browser's alert function with any selected text when a user right-clicks. Save this. Select that same Hello World heading again, right-click, and there, we get an alert with the Hello World text. Another simple example of data crossover between the main process and the renderer. Of course, this web contents object contains many more functions and events, but having seen these few, you'll be able to use all the others easily enough. Things like copy, paste, undo, redo, and many more. As with the browser window module, I'd encourage you to have a look through all the available events and methods, so you know what's available when building your own app. In the next few lessons, we'll be exploring Electron's session module. The concept of sessions in an Electron app is quite often misunderstood. Essentially, a session is an object used for storing any sort of state data related to the web contents of a browser window. This includes the HTTP cache, cookies, web storages such as local storage or indexed DB, and so on. A session being a requirement for any browser window instance created in an Electron app then. Meaning, by default, Electron creates a session for us, which is shared between all browser windows. This session being referred to as the default session. To see the default session, we can access it directly on our main window's web contents. I'll assign to a variable ses equals mainwindow.webcontents.session. Log that out, I have the app running already, so save. Check the terminal. There, an object of type session. So to recap, a session is the store of any web content's data, meaning if we add an entry to local storage in this browser window, that will be part of the current session and get stored in the default session being used by main window. To do this, in the DevTools, switch to the Application tab. We see all the various storage types supported by Chromium here. Open the default local storage table, adding a key name with value Electron. So this entry should now be stored and persisted in our default session. Quit the app, restart by typing rs in the terminal, and there, the local storage entry still exists, this being as the default session is persisted. The second type of session being in memory only, but we'll see that in a minute. Now, I mentioned that the default session gets created by Electron and is shared across all the app's browser windows. So let's add a second window to demonstrate that. I'll get rid of this log, create a new global variable to reference our second window, sec window, duplicate the main window constructor, assigning to sec window, with some slightly different dimensions again, 800 by 600, with a slight offset to main window, just so we can see the two side by side. x200, y200. I'll use the same content, index.html, open the DevTools panel for sec window, and finally duplicate that closed listener. That should do. So with a second window, let's reference its session also and compare it to the main Windows session. Remember, the default session is shared. Let ses2 equals secwindow.webcontents.session with a log message in which we can check if main window and sec window is in fact using the same session, using JavaScript's object class calling is session and session2. This being a simple function for checking whether two variables reference the same object. Save this. And immediately we see that local storage key also exists on sec window, meaning both windows share the same session. Confirm this in the terminal, true. So we now know how to access the default session given a browser window instance. But we can also get the default session directly from the session module. I'll require that module from Electron, session, assigning to default session, session.default session. Same session object as both these. Confirm this, comparing session to default session, save, check the terminal, and again true. If you're working with multiple browser windows and a single default session, which will be applicable for the majority of applications, this session.default session property is recommended as a more logical convention. With that said, you might not always want to use the default session. Instead, then we can create our own session objects and tell a browser window to use this custom session in place of the default session. Custom sessions can have a number of uses, the most common being the ability to get such a session from an external source and have the app contents in the same state as a second instance of the app. Think of syncing an app between multiple devices, for example. In Create window, I'll assign to a new variable, custom session, session, the session module, from partition, with a single argument being the partition name, part1. Think of a partition then as a unit of storage, much like a hard drive partition. In this case, we are creating such a partition to be used for our session object's data. Right now, we're still not using this new session in any of our browser windows, but let's compare it to the default session first. Object is comparing ses or session to custom session. Save. We see both windows are still using the default session as they both contain this local storage entry. Check the terminal, and this time we have false. meaning the two objects compared isn't the same. So let's tell SecWindow to use our new custom session instead of the default one. In this browser window constructor, set on the web preferences object, this being constructor options for the browser window's web contents, session, custom session, this variable. I'll format this a bit nicer. There. Main window is still using the default session, and SecWindow is using our custom session. Save. And SecWindow no longer contains that local storage entry, as it's saved in the default session used here. I'll add an entry to SecWindow's local storage, win name or window name, SecWindow, this being stored on our custom session now. However, quit the app, restart it, and the entry is gone. This being as we have two types of partitions for storing sessions. Persisted, meaning saved to disk, and memory partitions. Memory partitions are only stored in memory and does not get persisted between app restarts, which is what our custom sessions partition is at the moment, whilst the default session uses a persisted partition by default. Again, some apps might have a use for in-memory sessions, but for the most part we'll probably want to save our session between restarts. So let's change this. To make a partition persisted, it's as easy as prefixing the partition name with persist : save. This change having reset the state of our Windows DevTools, back to the Application tab, Local Storage, add back that local storage entry, win name, SecWindow, quit, RS to restart, and there. This time the session is persisted between app restarts. Electron also provides us a shorthand property for creating and assigning custom sessions to a browser window. Instead of first creating the session from a partition like we did here, we can assign and create the session partition directly on the Windows web preferences. I'll delete this. Also comment out this comparison as custom session now no longer exists. And then where we're assigning the custom session to SecWindow, change this to partition with the name of the partition we want to use, persist : part 1. Meaning if this partition does not already exist, create and use it. Save. There. No change. SecWindow still contains that local storage entry. So a persisted session exists and can be retrieved by name at any point after it was created. Again, a possible use case might include having multiple user sessions for a single app instance. But with that, we also need to be able to delete data from a session. A few methods exist for this, but in our case we can call session, so the default session, clear storage data. Storage data being cookies, local storage, IndexedDB, or even service workers. Save that. And this time our name entry is gone from the main window, as all of the storage data on the default session was cleared. Another method exists for clearing the session's HTTP cache also, clear cache. Then, taking a quick look through the docs, sessions allows us to do a few things other than just store data. Again, all related to the contents of the browser window. For example, we can create network emulations, meaning slow the network down, generally good for development. Handle permissions checks for things like using the camera, allowing notifications, etc. Get the user agent string, or clear cached HTTP authentication credentials. And there's a few more we'll cover later on. In the next lesson, we'll take a look at cookies, an important part of the session module. As part of Electron's session module, we're provided a full API for working with cookies. Cookies, of course, being a web-based data store, hence it being part of an Electron session on a web contents instance. So with that said, step 1 is going to be requiring the session module from Electron. And as in the previous lesson, get a reference to the default session on which we'll be storing cookie data. let ses, or session, equal session.defaultSession, on which we can then use the cookies class, session.cookies. Get, the standard getter method for reading session cookies. First argument is an empty object, meaning get all cookies. Second is the completion callback, with 2 arguments, an error object should something go wrong, and an array of cookies, which I'll log out. Save. Check the terminal, and of course we have an empty array, as no cookies have been set. Before we set our own cookie, however, remember that this class is used for managing all cookies, even those set by remote content. Before I demonstrate, I'll turn this getter into a function, just to make it reusable. Let getCookies equal a function, moving that get method with its log message into the function body. Then, to load some remote content that sets cookies, comment out load file, replacing it with mainwindow.loadURL, loading https github.com. Of course, to read the cookies GitHub sets on the default session, we'll have to wait for the content to fully load. So, using an event we've already seen, listen on mainwindow.webcontents for did finish load, with a callback in which we can check for cookies as before by calling getCookies. To recap, we load the content from this URL into main Windows web contents. This remote content will then create a few cookies on the default session used by main Windows web contents, and after it's completely done loading, we get all cookies on the default session and log them out. Save. We see Electron complaining about insecure JavaScript here, this just being due to the project's content security policy. Check the terminal, and there, we have several cookies on our default session. For example, _GA, being Google Analytics on github.com. So let's add our own cookie then. I'll change back to loading index.html and assign to cookie an object with its first property being URL, https myappdomain.com. Then the name of the cookie we're setting, cookie1, giving that cookie a value of Electron. That's our cookie object. So next, let's set it on the default session. Session.cookies.set, passing in this new cookie object. Second argument is a callback that fires on completion, with a single argument containing an error object, should something break. In this callback then, we can log out cookie1 set and read all the cookies on the session again. I'll use this function, copy, comment out the content listener as we'll be reading cookies after the set call, get cookies. Save, check the terminal, and there, we still have all the cookies set by github.com, but also our own cookie1. Very importantly, notice that our cookie has the session property set to true, whereas all the other cookies have false, with an expiration date instead. What this means is that without an expiration date, our cookie is only valid for the duration of this particular session. Not the session object, although that's where it exists, but this very instance of the app being launched. Meaning it's not persisted in the session object as it does not have an expiry. Check this. I'll comment out the set function, logging out all the cookies once the content is loaded again. Save. And gone. We're back to only having the cookies created with an expiration. So to make a custom cookie persist between app sessions then, we can simply give it an expiration in the future. I'll use this expiration time from the octo cookie, this being a simple Unix timestamp, revert back to our set function as before, this time setting on the cookie object expiration date, that timestamp I copied. You can also make this infinite to have infinitely persisted cookies. Save again. We see cookie1 logged out as before, but now containing an expiration date and no longer being marked as a session cookie. Check this persisted by quitting the app manually, this always being best practice for ensuring session data is persisted. comment out the set function, reading on did finish load, save, which launches the app, and in the terminal, cookie 1 is still being logged, meaning it's now persisted until this date here, at which point it will be removed automatically. Next, let's see how to read specific cookies. I'll clear this. And if you recall, I mentioned earlier that passing cookies.get an empty object will return all cookies. So to read a specific cookie only, let's say our cookie 1, we can pass a number of filters to this object. For example, name cookie 1. Save. And we only get that one cookie with the matching name. We can also filter by domain, URL, etc. Finally, let's remove cookie 1. Comment out our didFinishLoad listener, calling session.cookies.remove. First argument being the URL, myappdomain.com, and second being the name, cookie1. This being as cookies with the same name can exist under different domains or URLs. Pass this a callback with an error object, in which we can again get cookie1, or at least check if it exists. Save, switch back to the terminal, and nothing. We get an empty array as cookie1 no longer exists. That's the basics of using cookies in Electron. There's also an event for detecting cookie changes, but for the most part, getting, setting, and removing should suffice. Continuing with Electron's session object, this lesson will focus on a very specific object of the session, download item. The download item object is a result of the session's will download event. You may have spotted this in the session documentation already. Here, the very first instance event of the session. The second parameter of this event's callback providing us with this download item we'll be covering. This object having its own dedicated page in the docs. But first, let's start with the will download event. Remember, the session object manages the state of a web contents instance. So this event then is fired when a download is initiated from web contents, with a reference to that web contents instance also being passed to us in this event callback. So to trigger a download then, we can add a simple download link in our content. Open index.html. I'll get rid of all this. Adding an h2 heading, download image. Linking that heading to a remote image. I'm going to use another image placeholder service. Pick some.photos with an image of 500 by 500 pixels. Close the link. And very importantly, to make this a download instead of a standard link, we can use the new HTML5 download attribute. Without this attribute, we'll simply be navigated to the image, not what we want. Save this, and before we add the will download listener, let's see Electron's default behavior for handling downloads. I'll save main.js to relaunch the app, which is already running. Click that link, and we get prompted to select a location for this download to be saved. So very convenient and most likely suitable for the majority of app downloads. But let's say we want to take full control of this download. That's where the will download event with its download item object comes in. This object providing us with some events related to the progress of the download and a bunch of methods for getting information from the download and managing it, including pausing the download, resuming it, and so on. Back in main.js, start by listening for a download on the main window's web contents. Main window using the default session, so require the session module. And in create window, assign to ses, as before, session.defaultSession. Then, with a reference to the default session, listen for will download, with a callback, providing the event object, the download item we'll be using, and finally the web contents that started this download. I'll add a few log messages to demonstrate this download item. Starting download. The name of the file being downloaded, which we can get with downloaditem.getFileName, and the total size of the download, downloaditem.getTotalBytes. Save. click the download link. I'll cancel this. And over in the terminal, we see those messages. The file that would have been downloaded had I not cancelled, being named download.png, with a size of 1531 bytes. Note that this file name comes from the remote host, but we can save it as any other name as well. Let's see an example of actually downloading this file without prompting the user to save it then. I'll change these log messages to hold the logged out values in variables, referencing the total bytes as file size, and the file name as file name. Then to download this file to the user's machine automatically, meaning no prompt as we got by default, we can simply provide a path to save it to, that being what the prompt is for, calling on the download item set save path. I'm going to save this to the desktop, so if you recall from a previous lesson, we can get the path to the user's desktop with the app instance, calling app.getPath and passing it desktop. Append to this path the file name /filename. At this point, you can also save this under a different file name to what the download is actually called, but be sure to have the correct extension. Save, my desktop being behind this app, so we should see the download appear. Click, and there, the image is downloaded to my desktop without any prompt. Okay, so this way is perfectly fine for smaller files that download in a second or so. But let's say we're downloading a larger file and want to provide the user some feedback as to the progress of the download. We can do this by listening for some progress events on that download item. First, we need a larger download, of course. I'll just change this image to be 5000 by 5000 pixels. That should increase it to a few megabytes at least. Save that. And now in this will download event, so still within the context of a specific download, we can listen on the download item for the updated event. Pass a callback with the event object and a state parameter, state being a string of either progressing or interrupted, should something go wrong. We're looking to get the progress of the download here, so the first variable we'll want to set is the bytes received so far, assigned to received download item.getReceivedBytes. Then make sure the download is actually progressing by checking the state. If state equals progressing, and we've already received some data, so checking whether received is true or not 0. Assigned to progress the percentage received so far. We can get this by dividing the bytes received by the total bytes to be downloaded, times 100. And to make this a round number, I'll run it through math.round. Log that percentage to the terminal for now. Save. Click the download and check over in the terminal. And there, we see the progress percentage being logged up to 100%, with 100 firing a few times as the download is finalized and written to disk. So with that working, let's see a very basic example of displaying this to the client. In index.html, I'll add a progress element, initial value of 0 and max of 100, don't need this text in the tag, with an ID of progress. Again, this being a very rudimentary example, but to make this element accessible in the global window scope of this browser window, or more specifically the browser window's web contents, I'll assign to window.progress document.getElementById progress. So this element. Then over in our main process, we can update this element via its web contents. Remember, we're getting the web contents responsible for this download here. So on that web contents instance, call execute JavaScript window.progress, our progress element in the global scope of this web contents, setting its value equal to progress, this variable here. So to recap, each time this download progresses, we calculate the percentage of the download bytes received and then set the value of the HTML progress element in the download's web contents, which we referenced by its ID in the renderer process. Save. We see the empty progress element here. I'll first delete the image we've already downloaded from my desktop. Click the download link again, and that progress bar fills up as the image is downloaded. A very simple example, but as you can see we have total control over app downloads with the download item. In a production app, of course, you could listen for interruptions, pause the download, and much more. In the previous lesson, we saw an example of a system dialog when being prompted to select a download location. So in this lesson, we'll take a closer look at creating our own custom dialogs for various purposes. The dialog API is a standalone module on Electron. So step 1 is requiring that module from Electron. Dialog, all lowercase. Then, with the dialog module available, I'll create the demonstration dialogs once all of the main window's content is done loading. So as before, main window.webcontents on did finish load, passing this event a callback. The first type of dialog is the open dialog. As the name suggests, this allows the user to select one or more files from their computer. To create an open dialog, we can call on the dialog module show open dialog. Very importantly, before we continue, take note that all of these methods for creating dialogs is blocking, meaning if we were to call any of them immediately after the browser window gets created and before loading its content, the content simply won't load until the user has closed the dialog. Very important to keep in mind. Okay, next, as the first argument of this method, we can pass it the browser window on which to create the dialog, main window. Second argument is an options object, this having a number of options to manually customize the dialog. I'll set the button label to select a photo, and the default path to open this dialog with as my home directory, using app.getPath for home. The third argument then being the callback. That provides us with the selected file paths, which I'll just log out for now. Save this, and immediately as the content is loaded, that open dialog is shown with my home directory being the default path we're presented with, as per the configuration we passed. From this dialog, I can then navigate to my desktop, select this photo from the previous lesson, or just cancel. Before I go ahead and actually proceed to open a file, note that this dialog is presented as part of the main window, almost the same as a child window. This being as we passed main window into the show open dialog method as the first argument, meaning show this dialog on main window. The first argument is optional, however, so to create a dialog as its own standalone window, we can remove the first argument. Save again. And now this is no longer attached to the main window, functioning completely independent, still defaulting to my home directory, which again we can very simply change on that default path parameter. For example, desktop, which opens the dialog to my desktop path. Go ahead and select this photo, click select this photo, which is essentially just a relabeled open button. That dismisses the dialog, and in the terminal we see an array of selections, in this case that one photo. Don't worry about this warning here, you every so often see warnings related to the native system APIs used by Electron, but they get addressed in updates. So being able to get the path to this file is great, but we can further customize the open dialog's behavior by setting some specific properties. In this configuration object, set properties, which takes an array of property values. I'll add multi-select, meaning allow for multiple files to be selected, create directory, a Mac-specific option for allowing the dialog to create a new directory, and having specified some properties, we now also have to explicitly set the default behavior of selecting a single file only, as we just did. And lastly, open directory, to allow us to select an entire directory. Save this. The dialog is shown, this time having a new button in the bottom left, new folder, as a result of setting the create directory option. Click that, which presents us with a new dialog to name the directory we're creating. I'll call it Photos, and we see the new directory appear on my desktop. Duplicate this photo and move them into that directory, where we can now either select the entire directory, like this, or by holding the Command key, select multiple files. Confirm the opening of these two photos, check the terminal, and this time we have two paths in the callback array, one for each photo selected. Okay, the next dialog I'll show is the Save dialog. Comment this one out. Still in the didFinishLoad event, say dialog.showSaveDialog. First argument again being an instance of a browser window, or leaving it empty for a standalone dialog. Then, as an options object, I'll leave this empty also. And a callback, providing us with a file name parameter. Log that out. Save. And we get this very basic dialog to set a file name at a given path. I'll make the file name a new photo.png. Save. Which logs out that save path to the terminal. This always being a single path only, as it's intended for specifying a single resource path. The logic for actually writing the data to this file name being a completely separate task, of course, something we'll have to implement on an app-specific basis. Finally, I'll demonstrate the message box dialog. This being a dialog for either presenting the user with a simple message or to prompt a choice from some custom button options. This time calling dialog.showMessageBox. Same as all the other dialogs, we have the option to assign this to a specific browser window. I'll omit that again. Setting a configuration object with the dialog's title, message box, a message of please select an option, some detail to this message, should it require further explaining to the user, and finally, should you want to provide the user some custom options to choose from, a buttons argument. This being an array of button options or answers. Create that array, const answers equals an array with yes, no, and maybe. These options can be anything, of course. Then, finally, to read the user selection from these buttons, we can pass a callback with the response, being a button index the user clicked. Logging out user selected on the answers array, the button at the index of that response parameter. Save this. We get a simple dialog with those three custom buttons. Note the order of these buttons in the array, being the primary here is the first button in the array, the secondary button in the second array item, and finally any remaining buttons are created here. We only have the one. Select one of these options, I'll say maybe, check the terminal, and there, user selected maybe. That's where we'll leave the dialog module for now. We do have one more option to create an alert dialog, but that's a pretty straightforward message without any interactions. In the next lesson, we'll see how to create system-wide keyboard shortcuts for your app. In this short lesson, we'll see how to register system-wide keyboard shortcuts for an Electron app. Now, in order to understand this, we must first cover the concept of an accelerator string. Accelerators, having its own dedicated section in the docs, isn't a module but rather a standard naming convention for defining key combinations. For example, the most basic of accelerator strings, K, would simply mean when the K key is pressed. Or, in combination form, we could have Shift plus K, meaning Shift was pressed and held, and then K. The order being very important here. So, pretty straightforward then. The second part of registering a system-wide shortcut is Electron's global shortcut module. We use this module to register an accelerator string to an associated function for our app. Let's see this in action. Step 1, as always, is to require the global shortcut module from Electron. Global shortcut. Then in Create window, as we have to wait for the app to be ready before registering an accelerator, call global shortcut register, with the first argument being the accelerator string, make this G for now, and the second a callback to fire when the shortcut is pressed, in which I'll just log out user pressed G. Save this. I'll press G, check the terminal, and there, we see the log message. We could, however, have done exactly this by listening on the web contents, but the whole point of global shortcut is that it's global or system-wide, meaning our app simply has to be running and doesn't need to be in focus. So remaining in the terminal window, I'll press G again, and we get the same log message. This being a truly global shortcut then. Having such access to system-wide key presses does, however, come with a bit of responsibility. You'll have to keep in mind that another application may already be using your accelerator, and unfortunately there's nothing we can do about this, as we are not allowed to know what shortcuts other applications have registered. That would pose a serious security risk. So definitely something to keep in mind. That said, using combination accelerators or key combinations will make your application shortcuts a lot more unique and unlikely to clash with other apps. For example, we can change this accelerator to Command G instead, or if you're on Windows, Control G, which we write as Command or Control plus G. This Command or Control being a cross-platform accelerator string for exactly this purpose. Logging out user pressed G with a combination key. Save. I'll immediately switch to the terminal, hold Command, and press G. And there we have it. The accelerator is matched as soon as the G key is also pressed and logs out the message. So that's essentially all there is to using accelerators with the global shortcut module. We do have access to a few other methods, like checking whether an accelerator is already registered, for our app only of course, unregistering a single accelerator, or simply removing all shortcuts for our app. I'll quickly demonstrate unregister. In the shortcuts callback, immediately after logging out our message, call global shortcut unregister, passing in this same accelerator string. So registering Command G, and then when it fires, unregistering it, making this a one-off shortcut. Save, back to the terminal, press Command G, we see the log message, but when I press it again, nothing, as Command or Control plus G is no longer registered. That wraps up this lesson, a very small and simple module, but very useful. Menus is a crucial part of integrating with the operating system's user interface. So in this lesson we'll see how to create unique menus for our Electron app using two modules, the menu and menu item modules. As the name suggests, an instance of a menu will be populated with menu items. So let's see this with a basic example. As always, I'll start by requiring those two modules from Electron, menu and menu item, both with capital M's as these modules expose classes. Then step 1 is creating a menu which we can fill with menu items. Let main menu equal new menu. Next we can fill this main menu with some menu items. Create a new menu item 1 equal new menu item. This takes an object with properties for this menu item. I'll only set the label for now, Electron, this being what the item will show up as in the menu. Now, before I continue, it's very important to understand the differences between app menus in Windows, Mac, and Linux. The most significant of these differences being that on Mac, the first menu item will always be labeled the name of the application. In this case, that happens to be Electron, as I've labeled it here, but very important to keep in mind. The documentation covers these differences in more detail, and we'll see it when building our first project app in later lessons. Just something to be aware of for now. Okay, we have a menu, and we have a menu item to add to this menu. So the first way of doing this is with the menu's append instance method. main menu, append, menu item 1. And finally, we have to tell our app to use main menu as the main application menu. For this, the app needs to be ready, so in create window, seeing as that is executed on the ready event, call the menu class's static setApplicationMenu method, passing in main menu. Let's recap. We create a menu instance with Electron's menu class, assigning it to main menu. Then we create a single menu item with a label of Electron, this time using the menu item class instead. We add that menu item instance, menu item 1, to the end of main menu. We only have the one though, so end or beginning is all the same. And finally, we tell Electron to use main menu as the main top-level menu for the app. Save this, and there we have it. All the standard menu items we had before is now gone, and instead we have this single item with a label of Electron. Right now, this having no logic attached to it at all. What we generally expect from a top-level menu item such as this then, is to get a drop-down of related menu items when clicked. This drop-down being referred to as a submenu. So let's add one. In the menu item 1 constructor, set the submenu property to an array in which we can now add more menu items. Now, we could again create these menu items with the menu item class as we did here, but instead Electron allows us to specify menu templates. Menu templates essentially being menu item constructor objects, such as this one we're working in. So add an object to this submenu array, this representing a single menu item, with a label of item 1. Duplicate that a couple of times, item 2 and item 3, save. We still only see menu item 1 as that's the top level menu item, but when I click it, we're presented with item 1, 2 and 3 in a drop-down, or submenu. Each of these new menu items being the exact same menu item instance type as our original menu item 1, meaning they can again contain their own submenus. On item 2, set submenu, an array, with a new menu item object labeled subitem1. Save. Click the top level menu item, item 2 now having an arrow to indicate it contains submenu items. Hover on that, and there, another submenu with subitem 1. This can go infinitely deep, but usually 2 to 3 levels is the maximum recommended depth, as things can get a bit confusing. So defining menu items using these object templates is a lot simpler then, and luckily Electron also allows us to do this for top-level items, instead of creating them individually and appending them to the menu instance like this. To do this, we can, instead of creating a new menu instance, use the menu class's build-from-template static method, in which we'll describe the entire menu structure for main menu, exactly as we did here. This takes an array, like a submenu, cut the constructor object for menu item 1, that single top-level item. We also no longer need this append method, and paste into the template array the entire object. This still being the one and only top-level menu item in main menu. But it's much more logical in its structure now. Add a second top-level item in the template array, call this actions, with its own submenu. In the submenu, add a menu item labeled action 1. Duplicate that twice, action 2 and action 3. Save. And now we have that second menu item in our main menu, actions, containing a submenu with 3 more menu items. So the hierarchy and structure of menus is fairly logical then, and using the build from template method, as we've just done, allows us to structure menus very easily. It also allows us to better organize our code. For example, this entire main menu array can now be moved outside of main.js into its own module. I'll create a new file, mainmenu.js, in which we can export the array making up the structure of main menu. We do this by setting on the module.export property, so a standard node module, the main menu template array. cut this, and paste. So now when we require this new mainMenu.js module, we're simply given this array, requiring in the build from template function dot slash, so in the current directory, main menu. No need to specify the JS extension. Node will figure that out. Save, and the menu works as before, but we've made our code significantly more organized. The next logical step then is to add some functionality to these menu items. For example, a function that fires when a menu item is clicked. On action 3, I'll add a click property, which takes a function to call when this item is clicked. I'll use an anonymous function to demonstrate, with a log message of hello from main menu. Change the label to match, greet, save this, and now when I click greet in the actions submenu, we see that logged in the terminal. Hello from main menu. So we can very easily add just about any logic on a menu item. We can also automatically assign this menu item a keyboard shortcut, using an accelerator string as before. Set the menu item's accelerator property to Shift plus Alt plus G for greet. Save. And before I trigger the greet click via the keyboard, notice that Electron has now also automatically added the accelerator string to the greet item's label. Very useful for letting the user know that this can be accessed with a keyboard shortcut. Try that, Shift Alt G, check the terminal, and as before we have that log message. Very importantly, keep in mind that menu item shortcuts are not global as in the previous lesson. Global shortcuts can only be registered with the global shortcut module. For menu item shortcuts to work, the app must be in focus, which is the expected behavior, of course. Another useful menu item property is the ability to disable certain items. I'll disable action 2, setting enabled to false, save, and that item is grayed out and no longer clickable. Useful for menu actions with certain prerequisites. Finally, we have menu item roles. Roles are predefined menu items that Electron provides in a unique way depending on the user's operating system. For example, I'll change action 1 to DevTools with a role of toggle DevTools, nothing else. Save. We see the label with an automatically generated shortcut, Alt-Command-I on Mac, which will automatically be set to Alt-Control-I on Windows and Linux. Click that, and the DevTools is closed, or toggled on and off as the role suggests. Click it again, and it's back. Some roles even going as far as providing us with the label as well, like the full screen role. I'll change the second menu item in Actions to have a single property of role, toggle full screen, save, and there, we get a label, shortcut, and of course the associated functionality, full screen. And back to normal. Electron provides us with many of these pre-configured roles. To see a list, navigate on the menu item documentation page, right at the top here, to roles. There, a lot of standard behavior items, including things like undo, redo, copy, paste, etc. Let's see some of those. I'll add a new menu item in the second position of the main menu, a typical location for the edit menu, which is what I'll label this. Give edit a submenu with a role item of undo, redo, copy, and paste. I'll add a text area to demonstrate on, open index.html, add immediately after the heading text area, save, and also main menu. I'll close the DevTools from the menu to allow us to see the entire text area. And when we inspect this edit menu, notice that Electron also took the liberty of adding a dictation role and access to emojis and symbols, this being a result of the copy and paste roles in this menu. Add something to this text area, some test text, highlight that, copy, then paste, which does what we'd expect. Try undo, and again our paste commands are reverted. Note that we could have also set a single edit menu role to get all of this behavior automatically, so definitely worth having a look through these menu item roles. In the next lesson, we'll take the menus one step further and see how to create context menus on right-click. In a previous lesson, we learned how to listen for right-click events on the browser window's web contents. And now, also knowing how to build menus, we can use the combination of these two topics to create custom context menus for our app. This lesson being a short add-on to the previous lesson, rather than covering a new module. Specifically, the menu class's pop-up method, or instance method. As in the previous lesson, I'll start by creating a very basic menu, this time being a context menu rather than our app's main menu. I'll assign to context menu, require the menu module, which will again build from a template using the build from template static method. Pass this an array with a new menu item labeled item 1 and a second item 2. We now have a menu to show when a user right-clicks, meaning the next step will be to listen for that right-click event. We do this on the Windows web contents, so in create windows, say main window.webcontents on context menu, being that right-click event, the event callback providing us the event object, E, and in this event we can now show our new menu, this context menu, by calling context menu.popup. You can again pass in the window instance on which to create this pop-up or context menu, but omitting it will simply default to the window on which the event fired. Save this, right-click somewhere on the Windows web contents, and there, we get this pop-up of our context menu with those two menu items, appearing wherever we right-click. At the moment, these menu items don't have any purpose, but as we saw in the previous lesson, assigning click handlers or roles is fairly simple. For example, change item 2 to have a role of edit menu. I'll add a text area to the content again. Save both of these files. Close the DevTools for a bit of extra space, adding some text, which I can now right-click on to select, and under Edit, defined by the Edit menu role, we now see all the expected edit menu items, like for example copy, then paste, undo, and so on. Everything working as expected with minimal coding. That's it for this lesson, a very simple but important concept for a fully featured native app. So far we've been working within the confines of an app window, but of course apps can occupy other areas of the operating system as well, the most common being some sort of global icon tray, or taskbar. On Mac we find it here, top right of the screen. Same for Ubuntu Linux, or bottom right on Windows. Electron's tray module then allowing us to add our app to such taskbars. An app has two ways of using the taskbar entry. The first being to attach a menu to it, and the second being to simply listen for various clicks on the taskbar icon. Let's see examples of both. I'll start by requiring the module, this exposing the tray class, so capital tray, and then in order to create and use the tray instance, we'll have to create a global reference to the tray instance exactly as we do for the browser window. I'll add a global variable, tray, and a new function responsible for creating and configuring our application's tray instance, create tray, in which we can assign to the global tray variable, new tray, this constructor taking a single argument being the path to the tray icon. Now, this icon image we pass in here gets converted to a native image object, something we'll cover in a later lesson. But essentially it means we can configure the image just like a native app image by means of its name. For example, if we look at the documentation for Electron's native image, we see appending at 2, 3 or 4x to an image will allow us to provide larger images for high-resolution displays, this being a topic in itself, but I've linked to some good resources should you wish to have a read. Then we can also prefix the keyword template to provide a template image instead of a standard image. Template images basically meaning the operating system will fill all of the available pixels in the icon with the correct color based on the operating system's color scheme. You'll need an image with a transparent background then. I'll add my icon, tray template at 2x, and set the path to that tray icon image. So this name basically meaning display the icon at twice the resolution and make it a template icon. Mac takes a 16 by 16 pixel image for its standard taskbar, so at twice the resolution this image is 32 by 32 pixels. That's all we need to create the tray entry, so test this, not forgetting to call create tray once the app is ready. I'll just do it in create window for now, just easier. Save. And there we see the icon I used for the app tray. If you check the image in the lesson resources, you'll see it's a solid black icon. But being declared a template image, Mac OS has made the icon white in order to fit with my dark theme. At the moment this icon does nothing though, not even letting us know what it is. So let's fix that with a tooltip. To add a simple tooltip message to a tray icon, we can say tray set tooltip, passing it the message to display in the tooltip. Tray details. Save. Hover over the icon. And there, we get that tooltip. Next, we can add some functionality. Remember, I said we have two ways to use the tray instance. The first being using this icon only and listening for clicks, right clicks, or even clicks with modifier keys like Shift, Alt, etc. You can find a comprehensive list of events in the tray documentation, including some platform-specific ones like dropping files on the tray icon. For now, let's add a simple click listener. Tray on click, providing us a callback with the click event, in which I'll toggle the main window visibility each time the tray icon is clicked. First checking if main window is visible, with main window is visible, using a ternary operator. If true, so visible, call mainWindow.hide, else call mainWindow.show. Save. Click the tray icon and gone, with each click toggling main window between visible and hidden. We can also check for modifier keys on any of these click events. If E, the click event, dot shift key, meaning the shift key was pressed down when the click happened, call app.quit. Else, do the visibility toggle as before. So now clicking the icon will do what we just saw, show and hide it, but holding shift and clicking the icon will quit the app. Save. Perform a normal click. That works as before, but hold down shift with a click and gone. The app quits. So that's the first way of using a tray instance, with variations of clicks. The second is to add a menu to the icon. Exactly as in the previous lessons, I'll require the menu module, or class, creating in the global scope a new menu called tray menu. With the menu classes built from template method, calling menu.buildFromTemplate, in which I'll create a menu item with a label of item 1, and a second menu item with a role configuration of quit. Finally, applying this menu to the tray icon with tray.setContextMenu, tray menu. Save. And now when I click this icon, instead of the click listener firing, we see that two menu items, with the quit role giving us this quit master Electron entry, master electron being the name of the app taken from the package.json file. Click, and the app quits. So, as with any menu, the possibilities are endless. Do note though, I purposely left this click listener in place, but with the menu being added, this is now ignored. So, always one or the other. In this short lesson, we'll take a look at the very simple Power Monitor module. Power Monitor allowing us to respond to events such as the user's machine going to sleep or suspending and waking up or resuming. It also provides us a number of platform-specific events, like the computer being attached to an AC power source, running on battery, or even being shut down. I'll demonstrate the first two universal events, suspend and resume. Before I do, however, note that with this module, the module itself can only be required once the app is ready, meaning we'll have to take a slightly different approach to requiring it. I'll start by referencing the Electron library on its own, const electron equals, using this require electron, and then requiring the individual modules from that electron constant. So with this structure, we can now use the Power Monitor module directly from Electron once the app is ready. Try requiring it any earlier and it won't work. Electron.powerMonitor on suspend, meaning the computer is put to sleep, pass a callback with the standard event object, in which we can now do any important tasks like, for example, saving some data just before the computer goes to sleep, which I'll just log out. Then, using a second listener, this time for the resume event, meaning the computer woke up, I'll check if main window still exists and if not, create it. This really only being applicable to Mac. If no main window, meaning it's been set to null, call create window. Same thing as the activate event. Save. I'll close this window, not quitting the app, just closing the main window. Then put my computer to sleep. Wake it back up. And main window is recreated, with the log from when I put it to sleep in the terminal, saving some data. So a very simple module, but worth knowing. Having covered main process modules in the previous section, this new section will focus on modules specific to the renderer process. This means that instead of working in main.js or Node, we'll instead be writing JavaScript for the browser environment, or index.html, the browser window's content. Not massively different, but with a few extras such as the global window object, etc. Now, before we switch over to working in the renderer process, I want to again point out that we've explicitly enabled Node integration in our main Windows web contents, meaning that regardless of being in a browser environment, Electron allows us access to Node.js within the renderer process. This of course allowing us to use require statements or any of Node.js's APIs. In index.html, here we have a JavaScript file required instead of linked in the standard way. We could have also made this a linked script, like so. Same thing. Require really only being of value when writing modules with exports, but I'll leave it like this. Open that file. And as discussed, we have a reminder here that this file will have access to Node.js, given Node integration is enabled, of course. But besides this, we're dealing with a normal linked script. For example, I'll add a log message, renderer log, save, and now we have that log in the DevTools of the browser window, or in the renderer process. So with this in mind, the first and arguably most important Electron module of the renderer process is the remote module. Remote allows us access to any of the modules we've covered in the previous section, so main process modules, directly in the renderer process. Very importantly, however, unlike a real renderer process module, remote simply communicates with the main process from the renderer, meaning whatever main process modules we access using it will still exist in the main process, a very important concept to keep in mind. The documentation also goes into more detail on how exactly these object lifecycles work, and some other important concepts to keep in mind when creating main process objects from the renderer with this remote module. Worth a read if you want to understand this in more detail. To better demonstrate the nature of the remote module, let's inspect it by logging it out in the DevTools. Step 1 as always being to require the module, same as in the main process. Using destructured assignment, say const remote equals require Electron. Logging out remote. Save. We see that object logged in the DevTools, and when I expand it, we see all of the main process modules being implemented as getter methods. So not the actual modules, but rather methods of creating and referencing them on the main process. Referencing being the key word here. It's important to keep in mind that when referencing an object that exists in the main process, that object won't be garbage collected until it's destroyed in the renderer process as well. So pay extra attention to cleanup when dealing with remote. The only objects that don't get referenced from the main process being arrays and buffers. These two data types being copied to the renderer process via the remote module, meaning you cannot update them directly on the main process. Again, something to keep in mind. Okay, on to using the remote module. If we scroll down a bit further in the docs, we get to this module's methods, the first of which is require. This being to require a main process module in the renderer process, the core of what the remote module is for. I'll demonstrate using the dialog module from the main process. We can write this as either const dialog, using destructured assignment again, equals remote, seeing as we are already requiring the remote module from Electron. Or alternatively, change this first statement to require dialog from require Electron dot remote. Same thing, so pick whichever works best for you. Then, to further demonstrate the fact that we're now working inside of a browser window, I'll create a button with which to trigger a dialog. Const button equals an HTML button, which I'll create in a second, document.getElementById, which will be test button. So using native browser JavaScript to access an element on the DOM, create that element, button, adding an ID of test button, and some button text, test it. Back in renderer.js, add a click listener to this button, button.addEventListener, click, with a callback, E being the click event, in which I'll log out testing, just to make sure this works. Save, click the button, and there, we see the log in the DevTools console. I'll also add a break after this button. Okay, knowing how a button works, let's create a simple message dialog from this renderer process when the test button is clicked. In this click callback, say dialog.showMessageBox with a configuration object, setting the message property to dialog invoked from renderer process. Save all. Click that button again, and we get the dialog with that message. Dialog invoked from renderer process. I specifically said invoked from the renderer process here, as of course this dialog was created on the main process via the remote module. Let's see another example. This time using the browser window module, let secWin, or secondary window, equal a new browser window, require the browser window module via remote, passing in a configuration object, with a width of 400 and height of say 350, and then having this reference to a browser window instance on the main process, we can load some content into it. I'll use load file again, loading in the same index.html as our main window, save, click test it, And there, we get a new browser window as configured. And with this having the same content as the main window, it too can create a browser window. Click. There, a second sec window with its reference now being owned by this window here. That's the most important aspect of the remote module covered then, but we do also have a couple of methods other than requiring main process modules. For example, getGlobal. If you're familiar with Node.js, you'll know that Node provides us a global object. In the Node.js docs under globals, this here, global. The explanation here being less relevant to an Electron app, but let's see how to access this from the renderer process using getGlobal. Comment out the new browser window, logging out remote.getGlobal, and the name of the global we want to access, which I'll create in a second. First, however, we'll have to again change the structure of the require statement at the top here, as at the moment we don't have access to remote like this as a module. So instead of requiring our main process modules from electron.remote, make this remote, referencing remote by itself from Electron, like so. Back to getting this global, I'll call it myGlobe. Over to main.js, where we can say global, this global object being available by default, setting the myGlobe key to a variable set in main.js. Save all, click, and there. We log that variable in the renderer after getting it from the main process's global object. Simple enough. As with the global node object, Electron also exposes automatically generated module instances to the remote module. For example, the app instance, which we can access directly on the remote module, like so, or with the structured assignment like all the other modules, on which I'll call quit when this button is clicked. Change the button text to quit app, save, and of course when I click this now, the app quits. So remote essentially provides full control of our main app process directly from the renderer. The last method I'll demonstrate being getCurrentWindow. This and similarly getCurrentWebContents allows us to get a reference to the renderer process we're working in, or the contents of that renderer process when using getCurrentWebContents. Comment this out again, say remote.getCurrentWindow, this now being main window, or this renderer process. I'll reference it here as win, calling win.maximize, which will of course maximize this main window. Save, click the button, and the main window is maximized. That's where we'll leave the remote module. A very simple module, but an important one to understand. In the next lesson, we'll move on to some more renderer-specific modules. In this lesson, we'll take a closer look at managing new browser windows with the Browser Window Proxy class. I say class as the Browser Window Proxy instance is provided by Electron much like the main app instance, and not a module we require ourselves. Now, there's two ways to have Electron create a new browser window automatically. The first being to click an HTML link with a target attribute of _blank. And the second, which is what we'll be using, is to call the browser window's native window.open function. It's this function then on which Electron will return a browser window proxy object. Let me demonstrate. Again, working in index.html, or the renderer process, I'll get rid of all this, adding an h3 element with a link to electronjs.org, so the Electron homepage. Call that new window, and most importantly, to have this link opened in a new browser window instance, add target equals _blank. Save, over to the app which I already have running, refresh the main window, which reloads index.html. I'll go ahead and click that new window link, and as expected, Electron automatically creates a new browser window instance with the content from that link loaded as its web contents. But whilst having this new window created for us is very convenient, we don't have a reference to it in our code, and therefore can't control it in any way apart from a few standard UI elements the operating system provides. This being where we can now instead make use of window.open to obtain a reference to this window. So let's see that. I'll cut this link, change the href to a hash instead, this not being a requirement, but it will just ensure the link still looks and behaves like it should. Adding an onClick attribute, this being the same as listening for a click on the element, in which I'll call new win or new window. Add this function. I'm just going to keep this inline for now, so remove renderer.js. Const new win equals a function in which I'll call window.open with that Electron JS URL. This now being the exact same thing as simply using the link with the target blank attribute. But the reason we're doing this is to have a reference to this new window. Create a global variable to hold that reference, let win, assigning to win the return value of window.open, being the browser window proxy object. Save, close this, reload the window. I'll inspect this link to confirm the code has been updated. There, we have the onClick attribute. Click the link, which works exactly as before. But now we have a reference to this window on the global win variable of the main window. Check that in the Windows DevTools console, win, the name of that variable, which logs out an instance of browser window proxy, with some familiar browser window methods, such as close, focus, blur, etc. Browser window proxy essentially being a limited version of a standard browser window instance. So with that reference available to us, let's see a couple of examples of how we might use this. I'll add a new link, calling close win, label that close window, create that function, const close win equals a function in which we can use this global window reference to close the second window after opening it, win.close. Exactly the same as working with the browser window module. Keep in mind that this will only work after we've actually created new window and have a reference to the new window. Save, get rid of this second window, reload the contents, which adds the new link, open the window as before, and now with that global reference available, click Close Window, which closes the new window from main window where it was created. Again, this being exactly the same as using the complete browser window module. For example, in the docs we also have focus, blur, and for executing JavaScript on a browser window proxy object, eval. Let's see that. I'll add another link, calling style win, label this bad fonts, create the style win function for that link, in which we can now execute some JavaScript code from the main window's web contents in the new window. Win eval. I'll give the web contents of this window some bad fonts as per the label, running document.getElements by tag name, so selecting all matching HTML tags on the document, body, of which there's only one, so narrow it down to the first element on the resulting array, 0, setting on the body element style property, font family equal to Comic Sans MS. Save, reload main window's contents, open the new window, and now regardless of this being remote content, we have a reference to this window, meaning we can control all of its content. Click that new link, and there, we see all the content being changed to Comic Sans. So having a reference to a browser window created with window.open is great, but let's say we want to actually change how that window is created. We can do this as well. Over to the Electron documentation for window.open, we see this takes as the first argument the URL to load into the new window, as we have it in our code, and then two optional parameters being the name of the window, not much use as the HTML title element will overwrite it, and features, these being browser window features or options in string form. If we check the standard browser window docs, not browser window proxy, a bit down the page we get to constructor options for a new browser window, featured being this. Let's see an example. First, I'll set the window title, as that's now required when using the third argument also, _blank, as this isn't used, and then in string form some features. For example, let's say the new window's width equal to 500, comma to separate between options, height equal to 450, comma, and set always on top equal to 1. This being the equivalent of true. The true keyword won't work in this format. Save. Reload the content. New window. And there. This time the new window is created to our specified dimensions, whilst being set to always stay on top of other windows. Bring main window into focus, and as expected it stays behind the new window despite being the actively focused window. So, as you can see, whilst we have the option to use the browser window module directly in the renderer process via the remote module, window.open along with a browser window proxy reference allows us a much simpler solution. In order to understand the web frame module, we must first understand what a web frame is. Much like the browser window and web content modules, web frame represents an element of an Electron app. More specifically, the frame in which the browser loads its web contents. So, a browser window being the renderer process itself, responsible for everything we see when creating an app window, and is controlled by the main process. Everything inside of that, such as the web contents and the web frame, being controlled by the browser window instance, meaning the browser window creates a web frame in which to load its web contents. This is a less used aspect of an app window, but nonetheless it's able to affect the rendering of the window's web contents, so worth going over. If we look at the web frame documentation, this becomes a bit clearer. The web frame being responsible for things like the zoom level of the web contents, managing the spelling and grammar in the window's content, or even checking the resource usage of the HTML content. Let's see a few examples. Back in index.html, I'll start by getting rid of the linked renderer script. I'll just work inline for this lesson. And as always, step 1 is requiring the WebFrame module. Const WebFrame from Electron. Then the first and arguably most used aspect of the WebFrame module is managing the rendered zoom level of the Windows content. We can inspect this in the DevTools console to start with. So make the WebFrame module available on the global window object, window.wf for WebFrame equals WebFrame, this module. Save, head over to the app, refresh to update this renderer, and now, very importantly, the WebFrame module provides us two different units of measure with which to get and set the zoom levels for a Windows web contents. The first being the zoom factor. I'll get the current zoom factor with WF, that global variable on which we're referencing the WebFrame module, get zoom factor, which returns 1. Zoom factor then being the current zoom percentage divided by 100. In this case, the default zoom factor of 1 representing 100%. A zoom factor of 2 would be double this at 200%, and so on. The default limits being between 50% and 300%. The second unit in which we can get or set the content zoom is the zoom level. Check that. wf.getZoomLevel 0, with each increment of one zoom level representing an increase of 20%. Let's see both. I'll get rid of this global, add an image to better demonstrate the content zoom. In place of all this boilerplate content, add https placekitten.com with a size of 450 by 300. Then add some buttons with which to control the zoom, the first having an on-click event attribute calling zoom up, a function we'll create in a second, labeled increase zoom. Duplicate this with an on-click function of zoom down, decrease zoom, and lastly, zoom reset, with the text reset zoom. Add a break after this image to ensure the buttons fall below. Next, we can create the respective functions. Const zoom up equals a function in which we can call on the WebFrame instance set zoom factor of the current zoom plus 1, which we can get as before with webframe.getZoomFactor plus 1. Duplicate this for zoom down, this time removing 1 from the zoom factor. And lastly, zoom reset, which will simply set the zoom factor back to the default 1. Save this, reload the app, we get the image with the buttons, get rid of this for now, click increase zoom, and everything is scaled up to 200%, 2 times 100. Same for decrease. So whilst we're adjusting in 100% increments here, by adding or subtracting 1 from the zoom factor each time, we can just as well use decimals to fine-tune the zoom factor. Zoom level, on the other hand, being much less granular, but uses smaller increments by default. I'll change these calls to zoom level instead of zoom factor. Save and try again. Increase, and this time the jump is less severe, albeit only in 20% increments. With reset zoom, now returning back to 120% zoom, or zoom level 1. The second method of this module that I want to demonstrate is get resource usage. I'll simply log that out for now. webframe.getResourceUsage, this representing external or linked resources of the web contents loaded into this web frame. Save. I'll open the DevTools back up, reload the content, and there, we get a breakdown of style sheets, scripts, images, and more, telling us, for example, this web contents is loading one image with a size of 3,496 bytes. So overall, a very simple module, and honestly not one I find used too often. But should you need to make some content rendering adjustments, or even sandbox some of the content's JavaScript for security reasons, this is the module to use. In this lesson, we'll take a look at the very simple Desktop Capturer module. Desktop Capturer is essentially an Electron module wrapper for the native HTML5 Media Devices API, allowing us to access screens, so monitors, and application windows. This module contains only one method to do that: get sources. Let's see an example. I'll add this to renderer.js, first requiring this renderer module from Electron, const desktop capturer, destructured, equals require Electron. Call that one method on this module, desktop capturer.getSources. The first argument being a configuration object in which we can specify what type of sources we want to get, types. This taking an array, and in this array we can specify either screen, window, or both. Screen and window being the only two available source types. I'll say screen for now, pass a callback, first parameter being an error object should there be any, and the second our sources, or screens in this case, which I'll log out so we can inspect it. Save. And there, in the DevTools we get an array with two entries, being as I have two screens, my laptop's built-in display and an external monitor, screen 1 and screen 2. I'll expand this DevTools pane a bit so we can see all the properties of these objects. There. An ID, name, thumbnail of type native image, which we'll discuss in a minute, and another somewhat generic screen ID. So there's no real way of knowing which screen is which, but the first will always be the primary, in my case my external monitor. The real useful bit of these screen objects being the thumbnails. These provide us an image of the screen when the sources was requested. I'll render this out in the app content to demonstrate. Over to index.html, add an image tag, leaving the source empty so we can manually set it, and giving this tag an ID with which to select it. Screenshot. And to not capture the screenshot immediately as the app is loading, which will be blank of course, add a button to trigger this with. Assigning this an ID as well of screenshot button. I'll copy the ID so we can attach an event listener to this button. Document.getElementById, screenshot button, add event listener, on click, adding a callback to run when this button is clicked, in which we can call this getSources function, like so. This time, however, instead of just logging out the sources, we'll want to set the thumbnail of the primary display, the first one, to be displayed in that new image tag. Select the image tag by its ID, document.getElementById, screenshot, that ID we assigned it, setting its source attribute to the thumbnail of the first item in sources, index 0. Now, as mentioned, this thumbnail image is an Electron native image, something we'll cover in more detail in the shared modules section later on. But basically, an Electron native image is just a convenient instance of a class that allows us to work better with images. For example, to get this thumbnail image in a data URL format, meaning we don't need to link to an actual file, but rather embed the image data directly into the image tag, we can say thumbnail, so that native image instance, calling toDataURL. Save. I forgot to add a label to this button. Just say get screenshot, save again, this time reloading the content manually. There. And what we expect now when clicking this button is to get my two screens as sources, take the thumbnail from the primary display, being this one we're looking at, and displaying it in this new image tag by converting the image data to a data URL. I'll close the DevTools, click, and there, a rather small but nonetheless complete screenshot of my main display, or screen. We can also capture this thumbnail in a larger size. Back to the Get Sources options, set thumbnail size to a size object, an Electron size object being a simple object with a width and height property, same as we use to set the browser window size. I'll make this thumbnail have a width of 1920 and a height of 1080, so capturing a standard 16:9 aspect ratio, appropriate for most desktop or TV screens nowadays. And to stop this image from overflowing our app window, give it a width attribute of 100%. Save, and renderer.js. I'll close the DevTools again, click Get Screenshot, and there. This time capturing the new larger thumbnail size of this main screen. The other source option I mentioned being window, this allowing us to get the same for each open app window on the user's machine. Logging the sources out as well. Save. Click the Get Screenshot button again, this time getting a thumbnail image of the first window in the sources array, and there. We see the main window being captured as that's my primary window at the moment, or the focused window. This one here, the first object. This time around the window name being the title of the window. The other two windows being apps I have open on my secondary screen. So an extremely straightforward module to use. Later we'll cover the native image type in more detail and also see how to get specific details about a display. Having covered modules for both the main and renderer processes, we can now take a look at the very important IPC messaging modules used to communicate between these processes. IPC stands for Inter-Process Communication, and if you recall from the lesson on the remote module, this is what the remote module uses to communicate with the main process from the renderer. The reason I've separated this topic into its own section then is that Electron provides us two modules for IPC messaging, IPC main for handling IPC on the main process, and IPC renderer for use in the renderer process. These two modules relying on each other in order to implement IPC. I'll start in main.js, where we'll be using IPC main. So require that module from Electron, IPC main. This now allowing us to send messages to a renderer process or browser window and listen for incoming messages. If we look at the documentation for this module, we see it's relatively simple, with only a few methods, this very much resembling a standard event emitter module. We can start by listening for a message from the main window renderer process. In the global scope, say IPC main on, which can also be once, should you want to remove the listener after receiving the first message event. I'll stick to on for now, with the first parameter being the channel on which to listen. Channels being unique identifiers on which to send and listen for messages, naming this channel 1. The actual name of the channel having absolutely no meaning, but listening on channel 1, like this, means only messages sent to this channel from the renderer will be received, basically providing a way to identify and organize IPC traffic. This takes a callback to execute when receiving a message, first parameter being the event object, and secondly the data received, args, which I'll log out for now. I have my terminal window on my desktop this time round, so shift main window to the left a bit, setting X to 100 pixels and Y 140, which makes it vertically centered on my display. Okay, now having this listener on the main process, the next obvious step is to send something to this channel. Over to renderer.js, this time requiring IPC renderer, require Electron. I'll execute the IPC send from a button click, so add a click listener. We'll create the button in a second. Document.getElementById, talk, being the ID we'll assign to that button. Add event listener, click, with a callback, E being the callback event, in which we'll send a message to the main process. First create this talk button in index.html, a button with ID, talk, label this talk to main process, and a break to keep this on its own line. There. I'll save this and close it as we won't be doing anything else with this file. And now, having that button hooked up, we can implement an IPC send method to the main process, this time with the IPC renderer module. IPC renderer.send on the channel named channel 1, which is the channel we're listening on in the main process, sending a simple string of hello from main window. Save both files. As mentioned, I have my terminal open here so we can see as the message from the main window is received on the main process. Click that talk button, and it works. We get that logged in the terminal from the main process listener. Now, let's say we want to respond to this message from the main process where it was received. To do this, we have to first understand the nature of IPC. By default, IPC on Electron is asynchronous, meaning this sends the message to the main process and moves on immediately. There's no waiting for a response, no return value, nothing. And this is a good thing, as it essentially never causes any blocking of JavaScript execution in the renderer process. So, to respond to a renderer message from the main process, step 1 is going to be identifying the renderer the message came from. Remember, a renderer being a browser window instance, so we can have many. How we find the sender then is on the listener's event object. e.sender. Sender being the web contents instance of the sending browser window. Calling send, same as we did in the renderer. We need to again specify a channel to send this on. It could be the same channel it was received on, or a different one. Makes no difference really. I'll send this over a new channel called channel 1 response. Message received on channel 1. Thank you. So responding with a confirmation of having received this. Then, being asynchronous messaging, we'll now have to implement a listener for this response in the sender main window. Copy this channel name, listening in renderer.js, exactly the same as in main.js, with IPC renderer on channel 1 response, that channel we're sending the response on, pass a callback, and log out args, the data received. Save both files again, click the talk button, and immediately as the main process receives our message on channel 1, it responds on channel 1 response, which we listen for and log out back in our main window. So really basic sending and listening on both ends. Now, you might have noticed that IPC main doesn't actually have a send method. So how would we send directly from the main process to a renderer then? If you recall, a minute ago I mentioned that this sender is the web contents instance of the sending renderer process, which is exactly what we can use to send directly to a specific renderer then. For example, to send a message directly to the main window renderer, we can do so on the web contents of this browser window instance. But we do have to wait for the web contents to finish loading. So in create window, wait for the did finish load event as we've done a few times now. Main window.webcontents on did finish load, passing a callback, in which we can now send an IPC message to this window with main window.webcontents.send. So essentially accessing the send method from this renderer's web contents. Exactly the same as we do when sending to the main process from the renderer. I'll name this mailbox, sending you have mail. Then, as before, we'll have to listen for this in the renderer. Duplicate this listener, listening on channel mailbox, again logging out args, save, and there. Immediately after the web content is ready, that message is sent from the main process directly to this renderer. Also take note that so far I've only been sending simple strings back and forth, but IPC can send other JavaScript data types as well. For example, change this message to an object with a few properties, email, ray@stackacademy.tv, and an integer, say priority 1. Save, and there, we receive the object in the renderer exactly as it was sent from the main process. Objects being a more likely data structure for communicating via IPC. Okay, so that covers the default asynchronous messages. And whilst this is probably the best implementation for 99% of situations, IPC can also send synchronous messages. These behave significantly different to the default asynchronous messaging. So let's see an example. I'll start by listening for that synchronous message on the main process, using the same listener as with the asynchronous messages. Duplicate this one. This time listening on sync message. Again, just to provide a logical name for what we're expecting on this channel. I'll log the message data out again. And now the main difference here is that when sending a synchronous message from the renderer, that message demands a response and will block the entire renderer process until it's received. So we'll have to handle this a bit differently on the main process. First, I'll implement the send on the renderer. Again, in this talk button's click handler, duplicate the send method, commenting out the asynchronous channel 1 send, this time calling send sync on sync message, with the message waiting for response, which we'll receive, as with any standard synchronous JavaScript code, as a return value of this function. That return value being set by the receiver, the main process. Back in that listener, set on the event object's return value property a sync response from the main process. Assigning the response to a variable in the renderer, response. Log that out. Save both files. And keep in mind what's going to happen here now. When I click this, we'll send a synchronous message to the main process. meaning this entire window will be hanging until we get a response back from the main process, that return value. Click, and there. This obviously happened really quickly, but we received this waiting for response message on the main process, assign a return value to the message event, which allows the renderer to continue execution and log that value out. Keep in mind that the synchronous part of this only happens in the renderer. The main process is simply responding, and of course being Node.js cannot be blocked at any time. To better demonstrate the nature of this process blocking, I'll add a delay to that response from the main process. First though, in the renderer, create a log interval to observe the blocking with. Set interval, logging out I, set I to 1, and increment I after each log, which I'll make 1 second. This is trivial, but will just allow us to see the process blocking. Then in main.js, using a timeout, delay setting this response. I'll also comment out the send to the renderer, set timeout, pass a callback, setting that return value, after say 4 seconds. Save both files. We see the log each second, but when I send the message, everything blocks. Until 4 seconds later, that response value is set, and the renderer can continue executing code. So as you can see, probably something you should avoid using most of the time, but there will be situations where synchronous messaging will be required. Just use it wisely. That's basically it for the IPC modules. We do have a few basic helper functions also, but these are pretty self-explanatory, the ability to unregister channel listeners being the major ones. You'll find IPC messaging in almost every Electron app, so make sure you have a good grasp on this topic. In the next section, we'll explore some shared Electron modules. In this new section of the course, we'll cover parts of the Electron API that get shared across both the main and the renderer processes. I say parts and not modules, as these shared objects often include existing objects from Node.js, with Electron-specific extensions. For example, the first object we'll look at, the process object. As you might know, Node.js provides this process object, and this is mentioned and linked to in the Electron process documentation, here. Process then represents a running Node.js process, in our case the main process. Electron simply adding its own properties and method to the existing object, meaning there's no module to import. Process simply exists in the global scope of both the main and the renderer process. Note, however, process is only available in the renderer process with Node integration enabled. And, if you've noticed in index.html, we already use the process object, here. So with that, let's start by logging out this global object from both processes. I'll just get rid of renderer.js, logging it inline, there. And same for the main process, by adding a log in the global scope of main.js, process. Save both files, and when our app relaunches, we see process logged in the renderer, or the browser window's dev tools, with a lot of properties and methods, some being Node.js's own, and others being Electron's added functionality. Over in my terminal, the exact same object, being shared across processes. I won't be covering Node's native properties and methods, but let's see a few of these Electron additions. For example, a bit further down, we see a number of properties on the process's version property, this providing all sorts of version numbers for software used by our app. In index.html, change this log to now instead log out process.versions. I won't do the same in the main process as it's exactly the same. Save. This time reloading main window manually, and there, an object containing every version from Electron itself, Node, OpenSSL, and even the version of Google's V8 engine this is all running on. Another very useful property is process.type. This tells us the type of process we're accessing the property from. I'll add this to the main process as well, as this time they'll be different. Save both files, and there. In the browser window or renderer process, we get renderer, whereas in the main process, this logged browser, which is what the main process is referred to by Node. Knowing which process we are in is particularly useful when creating shared code, such as the shared modules we'll cover in this section. Other properties include checking whether the app was installed from the Windows App Store, or alternatively the Mac App Store, again useful for displaying specific content or offers to users. Then a bit further down, we get to process methods. Things like checking when the app was launched, CPU usage by the main process, and several other informational getters. The two methods I want to demonstrate, however, being crash and hang. These two methods do exactly what they suggest. Crash or hang the process they're called in. Let's see an example. I'll remove this log from the main process, over to index.html, add a button to hang this browser window with an onClick property calling process.hang. Hang renderer. Break before this button to have it on its own line. And as before, to better demonstrate the renderer hanging, I'll add a simple log interval. Set interval with a callback in which I'll log out I, and then increment it, starting with I equals 1, making this interval execute every half a second, or 500 milliseconds. Save both files to reload the app. We see that log interval, but when I click hang, everything stops, as this window is now in a simulated hanging state. Equally, we can crash the window. I'll remove this log, duplicate the hang button, this time calling process.crash, crash renderer, save. We now can't reload this window with Command R as it's currently hanging, so in the terminal execute a nodemon restart with rs. Click this crash button, and it breaks everything, or crashes. The reason we might want to simulate this being that we can now implement and test handlers for these conditions. For example, in the main process, we can reload a crashed renderer. This of course being a very crude solution, but let's see what this might look like. We can listen for a renderer having crashed on its web contents, which makes sense as that's what's crashed. The window remained, but the contents and the DevTools crashed, in other words, the web contents. So in create window, listen on main window's web contents with on for the crashed event. Pass this a callback in which we can reload the crashed window by calling mainWindow.reload. Or write this a bit better by simply passing this function as the callback, like so. Save this. Crash the window process again, and immediately the window is reloaded with the web contents reappearing. DevTools still being disconnected, but nonetheless. Again, this is by no means a solution you should use in a production app, but it shows how to implement solutions for these events. I'd encourage you to explore this object further as it can provide some very valuable information. And if you're not familiar with the process object in the context of Node.js, that would also be worth a look over. I've added the link in the lesson resources. Electron's screen module allows us to get detailed information about a user's display hardware. This includes screen dimensions, pixel ratio, cursor position, or even events relating to screen changes. Now, as with a handful of other Node modules, the screen module requires a slightly different approach to being used. First, let's look at using it in the renderer process. When used in the context of a browser window, the browser already contains a screen object, which we can access on the global scope, or window.screen, window being the browser's global instance, meaning we cannot import this as we'd normally do, screen being reserved. We could of course assign it to a variable with a different name, but that's just confusing. So instead we'll use it directly on the Electron library. I'll work in renderer.js, require Electron by itself, const electron equals require electron, allowing us to access the screen module by calling electron.screen, which I'll log out. Save. And there, we see that module with all its methods in the DevTools console. Take note that this module consists mainly of getter and setter functions, no properties. This being as screen dimensions, cursor position, and pretty much anything related to a display can change at any time. So getting properties for a display will always be retrieved via a function, ensuring it's current. Step 1 then is actually getting a reference to the user's displays. In the docs, scroll down to Methods. Here, we have this getAllDisplays method to get an array of all the connected displays, or getPrimaryDisplay, which we'll see in a minute. For now though, I'll log out my displays in the renderer with electron.screen getAllDisplays. Save, which logs out an array with 2 display objects, being as I have my laptop's built-in display and an external monitor, so 2 displays in total. And as before, when we retrieved thumbnail images of these displays, the first display object in this array is always the designated primary display, in my case being my external monitor. I'll expand that, and there, my external monitor having a size of 1080 by 1920, with a scale factor of 2, meaning the size, not to be confused with the resolution, is scaled up to twice its size, so a 4K display. These size and bounds properties being extremely useful for knowing exactly what sort of real estate a user is working with. I'll demonstrate, assign these displays to a variable. Then, to get a better understanding of my display layout, I log out a template literal or interpolated string, displays 0 being my primary display, .size .width by or times the height. Copy this, changing width to height. Save to check. There, as before, 1080 by 1920, my primary display size. Add the secondary display, I'll duplicate this, changing to the second display or index 1. Size being the first part of what we need to understand display layout, the second being the bounds or position. Duplicate this, logging the primary display's x-coordinate with bounds.x and bounds.y. Change this x to a comma, copy the line for the second display, displays 1. So size and bounds of the primary display first, and then the same for the secondary display. Save. There, 1920 by 1080 starting at coordinates 0, 0, and 1440 by 900 for my 13-inch laptop display, starting on the x-axis at 1920 and y of 180. This might not make much sense right now, but if I bring my display arrangement into view, we can plot this to better understand these properties. My primary display being this one here, and my secondary display the smaller one on the right. So the display sizes are pretty straightforward, 1920 by 1080 and 1440 by 900. The x and y coordinates being what helps us understand how to apply these sizes and get the layout. The starting point is always relative to the primary display, x0 and y0 at this top left corner. Then, relative to those points, the secondary display's x-coordinate being 1920, equal to the width of the primary display, and its y-coordinate 180, being the height offset as per this arrangement, 1080 minus 900. Should this have been my designated primary display, x0 and y0 would have been here, with this display having an x-coordinate of minus 920, being negative to the x-axis, and a y-coordinate of minus 180. So all based on a simple xy grid relative to the primary display. Another very useful feature of the screen module is the ability to detect changes in display arrangements. In the event section, we have the ability to listen for displays being added, removed, or any display metrics changing. In my case, for example, having an external monitor as my primary display, should I unplug that monitor, both this display removed and the display metrics changed event would fire, as my laptop display would then become my primary display. Let's see this event. Back in renderer.js, listen on the screen module electron.screen.on for display metrics changed. Pass a callback, which provides us with the event object, the display object of the affected display, and an array of metrics that changed. I log those changes out, save. Then, back in my display preferences, I'll rotate my primary display by 90 degrees. Revert the change, and there we have it. A couple of logs for the initial rotation. This might look different for your particular operating system or even version of operating system. And then a second set of logs when reverting the rotation, telling us that the bounds changed, so the XY coordinates of the primary display being the one I rotated, the work area, which is the operating system's calculated screen area, so minus the taskbars and other static UI elements, and of course the rotation. So we can pretty much be aware at all times of what's going on with displays. The screen module will also allow us to retrieve screen-based information such as the mouse cursor position. We can get the mouse coordinates at any time or on a specific event, such as a click. For example, I'll listen for a click on the body element. Document.getElements by tag name, body, accessing the first tag of that selector, having only one body tag, add event listener, click, passing this a callback, in which I log out the current cursor position, electron.screen.getCursorScreenPoint. Save. The body element only reaching to just under the content at the moment, so click up here somewhere, and there, x858 and y201. These coordinates again being relative to the primary display, so using that exact same grid as the display arrangement, meaning we can very easily know if a user is clicking in the primary display or the secondary, and where, with each subsequent click giving us the exact coordinates. Okay, up until now we've only used this module in the renderer, but Screen is of course a shared module, and can be very useful in the main process also. For example, let's see how to create a browser window that fills exactly half of the primary display. Step 1 being requiring the module. This again being slightly different to a standard main process module. In order to require the Screen module on the main process, we must first wait for the app to be ready, this event here. Requiring it immediately like this, as we do with other modules in the main process, will cause an exception and crash the app. So instead, I'll simply access it directly on the Electron library. This will require assigning Electron to a variable, which I'll call Electron, still requiring these main process modules the same way, but now from that new variable, declare const Electron equals require Electron. Then, having create window fire when the app is ready, we can access Screen inside of this function. I'll get a reference to my primary display, assigning to primary display electron.screen.getPrimaryDisplay. Copy this variable, and now, as mentioned, we can use this display object's dimensions to create a browser window that fills exactly half the screen. Set main window's x-coordinate to primarydisplay.bounds.x, so the top left corner of the display, y to primarydisplay.bounds.y, the width to half of the primary display, so primarydisplay.size.width divide by 2, and the full height, primarydisplay.size.height. Save. And there, we get a perfectly sized main window filling exactly half of the display. The shell module allows Electron apps to open resources on a user's machine with the default application for the type of resource, resources being files or URLs. For example, in the methods section of the shell docs, the first and simplest example being opening a URL. We do this with the shell module's openExternal method. And whilst this does provide some platform-specific options, passing a URL will suffice for 99% of use cases. Over to index.html, I'll start by adding a button with which to open a URL from the app. Get rid of all this, as we'll have a few buttons throughout the lesson. Button, with an onClick attribute calling show site, and a button label of launch Electron.js site, with a break after the button. Then, working inline again, get rid of renderer.js. We have to import the shared shell module, const shell with destructured assignment equals require Electron. Create this button function, const show site equals a function with the click event, in which to open a URL with the default browser, call shell.openExternal, requesting to open https:/electronjs.org, the Electron homepage. Save. I'll bring my default browser into view, being Chrome. Click that button, and there, in a new tab, the Electron JS homepage is opened as per that URL we passed. This might seem like a trivial bit of functionality, but having the ability to launch native apps outside of our own is a very important part of being truly native. Not just existing as a secluded app on the user's machine, but being able to interact with it and have things behave as the user would expect. After all, default system apps is chosen by the user for a reason, as they generally prefer them for handling certain resources, URLs being one such resource. We can also do the same with files of varying types. For example, in the project directory, we have the splash.png image. Again, as with a URL, we can very easily launch this in an Electron browser window, but the user would most likely prefer for an image to be opened with the designated system image viewer. I'll add a button, open splash.png, calling open splash, duplicate the show site function, renaming it to open splash, in which to now launch a physical resource such as this image file, we can instead call shell.openItem, passing the absolute path to the item or file, splash path. Define this variable as a constant, splash path equals, using an interpolated string, set this to be __ dir_name, using the global node.js dirname variable to get the directory of this file, index.html, being the same directory as the image we're opening, /splash.png. Save. I'll reload with Command R. There's the new button, so click. And splash.png is opened with the Mac Preview app, which will be the default for most Macs. A way better and preferred image viewer than what we can provide from within our app. So, open item allowing us to open a file with the default application. But another way to open files is with the system's given file explorer. The file explorer, despite really being part of the operating system, is in fact an application in itself, with which to browse the file system. Using that same splash.png file to demonstrate, I'll add another button, calling show splash file, labeled show splash.png, copy that function name, duplicate this one, show splash file, in which to now show this file in the file system, I'll pass that same absolute path to shell.showItem in folder. And before I save and show this, let's also add one more step. The shell module allows us to place a resource in the system's trash. Add a fourth button, delete splash file, label delete splash.png, create the function for handling this, duplicate this one, calling once again on that splash.png file path, shell.moveItem to trash. Keep in mind that moving an item to trash is not the same as actually deleting it. This keeps the final deletion in the hands of the user, and simply allows us to place a file in the operating system's trash directory. Save this, refresh, click the first new button, which launches a Finder window with that file selected. Finder just being the Mac file system browser, a somewhat standalone application as opposed to Linux and Windows. I'll move this to the side a bit so we can see the file when I now move it to the trash. Click again, and gone. Keep in mind that whilst we only worked in the renderer process for this lesson, Shell is a shared module with the exact same implementation in the main process. Electron's native image objects is something we've already seen in previous lessons. Once when creating a tray icon, and again when taking screenshots with the desktop capturer module. So to recap, a native image is essentially an instance of Electron's native image class, allowing us to better work with images inside of our app. Each native image instance then representing a single image. Whenever an Electron module returns an image, it will be of type native image, rather than actual image data. This being a shared module, everything I'll show in this lesson applies in the exact same way when working in either the main or the renderer processes. For the sake of simplicity, however, I'll stick to the renderer for now. Let's start by creating a native image instance to work with. In index.html, require the module as normal, const native image, require Electron. Then to demonstrate, I'll be using the splash.png image already located in the project directory, assigning to splash a new native image instance of splash.png, which unlike we'd normally do, we don't create directly from the class constructor. Instead, we can use one of a few static methods on this class to create the instance. For example, to create it from a file, say nativeimage.createFromPath, passing in the path to this image file, __dir_name, being the project directory, /splash.png. So now having a native image object created from this image file, we can do several things with it. For example, I'll log out splash.getSize. Save this. Reload the web contents, and there, 800 by 526. A simple helper method for determining image dimensions. Or alternatively, we can convert and output this image to a number of different formats. Let's see a couple. I'll get rid of this content in index.html with a heading of convert splash.png. Add a button, giving this an on-click attribute calling toPNG. Label this PNG. I'll duplicate the button with toJPEG instead. JPG. PNG and JPEG being the two most common image formats we can export from this native image instance. Create the click handlers for these buttons. PNG conversion first. Const toPNG equals a function with that click event, assigning the image data, which is a buffer, to PNG splash by calling on the splash native image to PNG. Duplicate this click handler function for the JPEG conversion to JPEG, naming the image data JPG splash, which we get with splash, so using the same splash image instance, to JPEG. To JPEG, unlike to PNG, requires an argument specifying the export quality of the image, this being a range between 0 and 100, with 100 being 100% of the original image quality. So that's our two separate image export types. One to get a PNG version as the original file is, and one to get a JPEG version. But as mentioned, these functions return the actual image data in the form of a buffer. So we'll have to do something with it, like, for example, save it to disk, or more specifically, save to desktop, a function which we'll create in a second. Pass this function the image buffer as the first argument, and the image extension, or type, as the second, PNG and JPEG. Next we can create that function. Const save to desktop, taking the data and the extension. Then step 1 in this function is to get the absolute path to the desktop. I could of course hardcode this for my own file system, but to do this properly, let's get it from the app instance. To do that, we'll have to first require the remote module, calling remote.app, so a reference to the app instance in the main process. Get path, desktop. This should be very familiar from previous lessons, but if not, refer to the app lesson under main process modules, and remote under renderer process modules. Then, to write the image data to the desktop, we can use Node's built-in fs module, or file system, calling fs.writeFile. Require that module, const fs equals require fs. Pass writeFile the file name and path to write this image data to, starting with desktop path, /splash dot extension. That extension we're passing in from either function call. Then the image data, and lastly the required callback function. This callback providing an error object only, so I'll simply have console.log be the callback. Save, reload main window, and now take note that my desktop is in the background here, where the new image files will be written to. Click PNG, and there. We get a PNG image of splash.png written to the desktop. Same as the original image. Try JPEG, and the same, except this time the original was converted to JPEG format, which we can see confirmed by the lack of transparency in this image. The other two options for exporting the image data being to bitmap, not a common export format, and data URL, a very useful format for use on the web. I'll add another button to demonstrate this, calling toTag, being an HTML tag. Label this button show, break to a new line, and to show this data URL in an HTML tag, add an image tag. Leave the source attribute empty for now, giving the tag an ID with which to select it. Preview. We still need a click handler for the show button. Duplicate one of these again. toTag. We're not writing to the desktop this time, so remove this function. Calling splash.toDataURL to get a data URL of the original Splash image. Assigning the URL to Splash URL. Then, to show this image in that new image tag, select it by ID. Document.getElementById. Preview. Setting its source property, that source attribute in the tag, to the data URL, Splash URL. Save this. Reload. Click Show. And there we have it. The image tag's source is assigned the data URL of the original image and displayed as with any other URL pointing to an image. The native image class also allows us to manipulate images beyond simple export formats. For example, this image being too large for the window, we can resize it to say a quarter of its original size. Still in this function, start by getting the original image size, splash.getSize, and then before creating the data URL, call resize. Resize returns a native image instance of the resized image, so we can daisy chain the toData URL onto this, like so. Pass this the new dimensions as an Electron size object, a size object simply being an object with a width and height parameter, setting width to size.width, so the original image width, divide by 4, making it a quarter of the original size, and the same for height, size.height, divide by 4. Save this, reload, click Show again, and we get the resized version of the image as a data URL, at exactly a quarter of its original size. Electron's clipboard module allows us to read and manipulate the contents of the system's clipboard. So, not copying and pasting directly, but the content of such actions. All in all, a very simple module. I'll be working inline inside of index.html again, require the clipboard module with the standard destructured assignment, clipboard, requiring from Electron. Then the absolute most basic function of this module being reading the contents of the system clipboard. I'll log that out, calling clipboard.readText. Save, my clipboard being empty at the moment, so I'll bring over a text editor from which to copy. Say some text from my text editor, select all of this, and copy. This copied text now being stored in the system's clipboard, which we can read from our app and log out. Reload the app, and there, we get the exact text logged out from the system clipboard. So this might be useful for a number of reasons, the most obvious being some form of clipboard history app, seeing as the system clipboard gets overwritten with each new copy. Having access to the clipboard, however, means we can also change its contents. For example, let's see how to transform the existing clipboard content to all uppercase. I'll add a button for this, breaking to a new line first, assign a click handler with onClick, calling make upper, and label this button make clipboard uppercase. Create the make upper function, we don't need this log anymore, const make upper equals a function. Then step 1 in this function is to read the content of the clipboard. Assign to cb text, as before, clipboard.readText. Then, to write back to the clipboard, which will of course overwrite the existing clipboard value, say clipboard.writeText, passing in the transformed content, cbText to uppercase. Save this, reload the app. I'll copy the same text from my text editor again, meaning this is now the content of the system clipboard. So transform it to uppercase, paste it back into the editor, and we get that new value from the system clipboard, as we updated it in our app. So that's basic reading and writing of plain text content. But the clipboard module also allows us to work with different data formats. For example, in the docs, we see those text methods, read text and write text, and additional methods for HTML or images. I'll demonstrate with an image, as HTML is pretty similar to text. Move this click handler function out the way a bit, adding a new button. I'll just duplicate this one, again on its own line. This one calling show image. Show clipboard image. Then, to be able to read and show an image from the system clipboard, we'll also need an image tag, leaving the source empty so we can set it, with an ID to select this tag with, CB image or clipboard image. Add the button's click function, const show image equals a function with that click event object, in which we can read an image from the clipboard, assigning to image clipboard.readImage. As with any image data inside of an Electron app, readImage will return a native image instance for us to use. So select that image tag, document.getElementById, cbImage, setting its source attribute to the data URL of the native image returned by the clipboard. Image, this native image instance, to data URL. Save this. I'll use splash.png from the project again, bring that into view, copy the image, this image now being the content of the system clipboard, refresh the app to get that new button, click, and we get that copied image displayed in our app. This module being shared, we can of course use any of these methods directly from the main process as well. I'll open main.js, require the clipboard module from Electron, and as a very simple demonstration, write to the system clipboard as soon as the app is ready. So in Create window, clipboard.writeText, hello from the main process. This will of course happen before the main window is actually created. So immediately in index.html, we can access that value on the clipboard, logging out as before, clipboard.readText. Save both files, and as soon as the app is relaunched, we see that clipboard value logged in the console, while still being available to the rest of the system as the current content of the clipboard. Paste in this text edit window, and there, same text. So an extremely simple module, allowing us to integrate our apps with native aspects of the operating system. In this new section of the course, we won't be focusing on specific Electron modules, but important or useful implementations of these modules. On top of that, we'll also see how to implement native HTML5 APIs within our app. Remember, when building Electron apps, we're working in one of the latest versions of Chromium, meaning pretty much all of the HTML5 APIs is supported inside of a browser window, something we should definitely take full advantage of. The first topic we'll cover then, not being an HTML5 API but an Electron one, is off-screen rendering. Electron has a dedicated page explaining this concept, but essentially it means to load and render content into a browser window on a separate thread, meaning it's not visible and therefore happens faster whilst using less resources. A perfect solution for, say, rendering a page onto a canvas element or even a 3D context. Off-screen rendering can be run in two modes. By default using the GPU, or the graphics card, or alternatively using the system's CPU only. If you require 3D CSS animations during rendering, you'll want to leave it as the default, so using the GPU. But should your app not require the rendering of animations, disabling the use of the GPU in favor of the CPU only is the preferred faster option. I'll demonstrate the latter. To start, we'll tell our app to disable hardware acceleration, so only using the CPU. In main.js, before creating any browser windows, call on the app instance disable hardware acceleration. Then, to render this main window off-screen, we can set on its web preferences off-screen true. Very importantly, note that we are setting the web contents of this browser window to be rendered off-screen. The window itself belongs to the main process and cannot be run on a separate thread like the rendering of the web contents. This will make more sense in a second. Then, instead of loading index.html, I'll change this window to instead load a URL, https electronjs.org. That's basically it. This main window will now load and render its web contents, the Electron JS homepage, but we won't be able to see it. So to make sure it's working, we can get the window title once it's done loading. Listen on main window's web contents for did finish load, passing a callback in which I'll log out the window title with mainWindow.getTitle. Save this, the app relaunches, and we get this frameless window with its web contents being rendered off screen, as per this message. Check for the title in the terminal, where we see the title of the Electron homepage logged out. We can ignore this Electron warning here. So everything worked as expected. Now, in most cases, we're not going to want this window with off-screen content to be visible either. So let's also hide the window itself. Setting on the browser window options, show to false. Then, not being able to see the browser window itself, we might as well also close it once it's done loading and we've got everything we need. Comment out this close listener, calling after the did finish load event fires mainWindow.close, and setting mainWindow to null. Ideally, we would have probably just quit the entire app here, but with NodeMon running, that doesn't make any sense. Save this to check it still works. Nothing happens now as there's no window to focus to, but in the terminal, we still get that title logged out. Okay, so rendering some content is great, but 99% of the time off-screen rendering will be used to get rendered versions of the content. To do this, we can listen for the paint event on the off-screen web contents. mainWindow.webContents on paint. The event callback providing us with the event object, dirty, which is the size and bounds of the area that was rendered, and lastly a native image instance of the rendered content. Paint, unlike did finish load, fires each and every time the content rendering changes. This happens multiple times when loading the content, for example. So to capture the content loading stages in images, I'll save a screenshot each time the paint event fires, assigning to screenshot, image, this native image instance of the rendered content, .2png, and write that image to my desktop using Node's fs module, fs.writeFile. get the desktop path with app.getPath, desktop, / screenshot_I, which we'll create in a second, .png. The data we're writing to this file being our screenshot PNG image, and to handle any errors, pass console.log as the callback. Create I, a simple number increment for each screenshot, starting at 1, and increment after each paint. We also need to require the fs module, const fs equals require fs. Save this and quickly move over to the desktop, where we get those screenshots as the web contents is rendered, seeing each and every paint from start to finish. A simple but very powerful technique for performing fast content rendering as a background process. Knowing when your app has network connectivity can be very helpful and avoid complicated or unnecessary error handling when trying to perform network requests under offline conditions. So in this short lesson, we'll see how to use the HTML5 Navigator API to check network status. The primary API here being the Navigator online property, but we also have some access to events, which I'll demonstrate in a minute. Navigator, of course, being a global window object as with any other HTML5 API, so this is exclusive to the renderer process. In index.html, I'll start by creating a simple network status indicator. Using this h1 tag, say app is, with an underscore tag that we can select to set the status, using an ID of status. Then, working inline, we can check the initial network status when loading the app. Start by selecting the status element, assigning the DOM node to status node, document.getElementById, status. Then we can set this element's text based on the navigator's online property. Status node.innerText equals, using a ternary operator, navigator.online, which, if true, will set the status text to online, else, meaning navigator.online returned false, will set it to offline. Save this, reload main window, and there, app is online. Now, to test network conditions, we can normally use the Network Conditions tab in DevTools, this one here, setting throttling to offline. But this doesn't work for the navigator's online property. Instead, I'll turn off my Wi-Fi to actually go offline. Refresh the window again, app is offline. Back on, refresh again, and we're back. So this is a simple solution for checking network status explicitly, but we can also implement event listeners to notify us if network changes. I'll create a function to set the status text with const set status equals a function with a single argument of status, this just being a truthy or falsy value. Move that node selector into the function, reusing the same ternary operator, checking instead of navigator.online, the status argument passed to the function. Perform as before the check on load, calling setStatus with the status value being navigator.online. Then, to have any subsequent changes to the network status reported, we can listen on the window object. So window.addEventListener. Online, meaning the app went back online. Call setStatus true. Duplicate this listener for the offline event, calling setStatus false. Save. Reload the window, which does the initial check and confirms that we're online. And now with the events, we can actually use the DevTools to emulate network conditions. Set throttling to offline, the header updates accordingly, and the same when going back online. An important part of a desktop application is the ability to show notifications. And once again, HTML5 simplifies this for us. Now, showing notifications is not to be confused with the ability to push notifications to the app. That is a completely separate topic and doesn't really concern Electron, but rather Node.js. I've linked to some Node push notification libraries and information in the lesson resources. HTML5 notifications then simply allows us to trigger a system notification. The main difference being that when used in a standard browser, we'll first have to obtain permissions to display such a notification, whereas in Electron, we're granted permission automatically. Let's see an example. Again, working in the renderer, as this is an HTML5 API, remove this require statement, calling new notification, with the notification title as the first argument, Electron app, and an options object as the second. This can take a number of options, but to keep things simple, add a body, which is the main message in the notification, some notification info. Note that this body text is restricted to a set number of characters for the given operating system, 200 characters for newer versions of Windows and 256 bytes for Mac. Save this, reload the app, and there we have it. A simple notification with our set title, body, and app icon. In this case, the default Electron icon. The default behavior for clicking such a notification being simply to focus the app window responsible for showing it. We can see this by unfocusing the app, which means we'll have to delay the notification for a second or two to do so. Add a timeout, creating the same notification inside of this timeout after, say, 2 seconds. Save. I'll reload the app this time and immediately unfocus it by clicking on my desktop. Reload, unfocus, click the notification, and the app window is focused. This notification also provides several other events besides a simple click handler. We can access these on the notification instance. So assign its return value to notification. Then to change the notification's click handler, set its onClick property, making that a function with the click event as its only argument, which I'll log out. Save again, reload, which triggers the notification, click, and there. We see the notification's click event, which contains a number of very useful properties, like, for example, the ability to prevent the default behavior of focusing the app, or the timestamp of the click. This notification instance also provides onShow or onClose handlers. So, having access to the notification events, we can directly affect our app with them. For example, let's say we want to actually show our app window when a notification is clicked, not simply focus it. The first thing we'll need is a reference to this browser window instance, main window, which we can get using the remote module. Const remote equals require Electron. Then, to get a reference to this window from the main process, I'll assign to self remote.getCurrentWindow. Check if this window is visible when the notification is clicked. If not, self.isVisible. Self being a browser window instance, call self.show. Save. This time I'll minimize the app after refreshing the window, so reload, minimize the window, and when I click the notification, the app window is shown. So another very simple but powerful HTML5 API for us to use in our Electron apps. In an earlier lesson, we briefly touched on node integration, a very important concept to fully understand. So in this lesson, we'll see how to use preload scripts to access Node.js securely from a renderer without node integration. Now, basically, setting node integration to true on a browser window's web contents is what allows us to access node APIs and require statements directly inside of our renderer process. But allowing a renderer process access to Node.js means it also has full access to the user's file system, which can pose a severe security risk when dealing with any untrusted or remote content inside of a browser window. Electron version 5 disables node integration by default, hence the explicit statement enabling it inside of main.js. Node integration being perfectly safe for apps that use static HTML files as its content, like we do. The real threat, as mentioned, coming from remote content. So let's say you're building an app that requires remote content and you can't enable node integration. What exactly will happen? I'll set node integration to false on main window, false being the default anyway, save, and the app reloads with a bunch of errors. Process is no longer defined, and same for require, both Node.js integrations. What Electron allows us to do then is run some code on the Windows Web Contents before loading. We do this by means of a preload script. We can set the location to this script on the web contents, preload, setting it to __ dir name, so this directory, / preload.js. Create that preload file. And if we look back at those errors, we can solve them by providing the missing variables. In this case, process or process.versions, being the versions for Node and Electron. Easiest being to set these values on the global window object of the web contents. So instead of accessing them on the global Node process object, change this to versions.node and versions.electron. Also get rid of this require statement as we can't really provide this. Define those versions in preload.js, setting on the window object versions equal to an object, with properties node being process.versions.node. Remember we have access to node in this preload script, and versions.electron being equal to process.versions.electron. Lastly, Electron version 5 also enabled context isolation inside of browser windows. So to allow preload.js access to the Windows context, set context isolation to false. So to recap, we're now executing preload.js on the main Windows web contents, allowing it to access the context of that web contents. And in preload.js, we are setting both Node and Electron's versions from the Node process object, which we're printing here, as before. Save all of this, and our versions are back, with no more errors. We've added these two values now, but we can also provide limited and safe access to Node.js APIs using this preload script. For example, let's say we want to allow our app to write some content to the user's machine. I'll create a text area to input the content to be saved. Give this an ID of content, break, and a button to trigger the write. ID save, with a label of save content. Check this, reload the window, and there. What we want now is to type something into this text area, click save, and have that content written to a plain text file on my computer. I'll start with the save button's click handler, const save text equals a function, in which we can go ahead and get the content of the text area. Select that text area node, document.getElementById, content, accessing its value. Then, this being the bit we'll have to provide from the preload script, call write_to_file this text. Also not forgetting to set an onClick property on this button. OnClick, save text. Right, that should be all for the renderer. So over to preload.js, start by requiring the remote module to give us access to the app instance. We'll need this to get the desktop path. As before, remote equals require Electron. And to perform the write, Node's fs module, const fs equals require fs. Get the path to the desktop, which is where I'll have the text file written to, setting desktop path equal to remote.app.getPath, desktop. The final step being to create this global write_to_file function. Assign to window.write_to_file a function with a single argument of text, writing that text to a file with fs.writeFile. First argument being the path or file name, desktop path, app.txt. The data to be written being this text argument, and lastly have console.log handle any errors. So we're essentially injecting this function into the main Windows web contents, the window property being available as we're sharing the same context as the web contents, using that context isolation property. Should you not require access to the Windows context, you could also leave context isolation enabled for even more security. Save, that reloads. I'll type in here some content from my app, click, and app.txt appears on my desktop with that exact content. Preloads is a very important concept and one you should really make sure you understand, as it will really help you create much more secure apps. In this lesson, we'll see how to create a simple native progress bar for our app. This being a function of the browser window module and not a standalone API, but nonetheless it's a very useful feature. So, being a browser window function, I'll start by demonstrating directly from main.js, calling on the main window instance setProgressBar, with one argument being the progress. This progress ranges from 0 being empty to 1 being full. So to set this to say a quarter or 25%, I'll pass in 0.25. Save. And there, on the app icon we get this native progress bar indicator set to 25%. This will of course look different on each operating system, but on Mac it will show on all instances of the app icon, like for example in my tab bar. A progress bar like this can be useful for a number of reasons. For example, displaying the progress of a download, an export, or pretty much any other long-running task. Despite being a function of the main process module, most often this will be suited to the renderer process. And as we've seen before, we can very easily access this using the remote module. I'll cut this over to renderer.js, start by requiring the remote module, const remote equals require Electron. Then we'll need a reference to the main window instance to call the progress bar function on, assigned to self remote.getCurrentWindow. Self now being the main window instance, on which we can call exactly as in the renderer self.setProgressBar, making it 0.75 this time, or 75%. Save, and there, exactly the same, but now run from the renderer. Of course, having a static progress bar like this isn't much good, so let's create a mocked progress. I'll cut this again, starting with an initial progress value on a progress variable, 0.01 or 1%, and then using an interval we can increase this to 100%. Set interval with a callback, in which I'll set the progress as before, but this time passing the progress variable. Next we can check if this has reached 100% or it's still in progress. If progress is less than or equal to 1, meaning we still need to set the value, 1 being the final value, increment progress by 0.01, so 1 extra percent. Else, meaning we've already reached 100%, remove the progress bar by assigning it a negative value. Not 0, that gives us an empty progress bar. It must be negative for the bar to be removed. -1. And once the progress bar has been removed, stop the interval. Clear interval, passing progress interval. Create that progress interval reference. Let progress interval equal this interval. We still need an interval time, I'll say 75 milliseconds. Save this, and when the app reloads we see that progress increasing, all the way to 100%. Where it's removed. So a very simple function that can provide valuable information to the user. After covering the Electron API and looking at some additional features and techniques, we're now ready to build an Electron app using what we've learned. Of course, we won't be able to use every single module we've covered in the course, But the simple project I've prepared for this section does cover all the key modules and will allow you to use them in a more practical real-world application. This then being the single most important section of the course. So be sure to follow along, and should you get stuck anywhere, the relevant lesson's final code will be linked in the lesson resources or in the project code repo. Okay, so with that said, let's take a look at what we'll be building. The project I've prepared is a simple bookmarking app that will allow us to save links and read them directly from the app. This is extremely simple, but rather than build a big complicated app, this small application will cover a lot of very important techniques for putting all the Electron modules together. We'll also spend a significant amount of the project refining basic features to make the app integrate with the desktop environment perfectly. The starting point for our app is, as before, the Quick Start project we've used throughout. Note, however, that I will be using plain JavaScript and CSS only. No helper libraries or frameworks. Picking a JavaScript framework or CSS compiler will simply detract from the project, not to mention the sheer number of frameworks there is to choose from. Chances are my framework of choice isn't yours, so we'll stick to vanilla code, which will allow you to pair what you've learned with your own framework of choice. To begin then, I'll clean up a few of the files and directories in this starter project. Remember, the app we're building will be packaged in the next section, so we don't want to leave anything unnecessary. First file we can get rid of being the splash.png image, the readme, and this lessons directory, keeping in mind that you'll find the final code for each of these project lessons in this directory, so maybe keep a copy for yourself or clone a new copy from the repo. Then, in terms of the project's directory structure, I'll again keep it very simple. Everything related to the main process will reside in this root project directory, and everything related to the renderer process will go in a subdirectory called renderer. We can create that directory, moving into it index.html and renderer.js, the only two files we have relating to the renderer process right now. I'll also rename these files to fit the app structure a bit better. Make index.html main.html, referring to being the content for the main window, by no means a requirement, just my own logic, and renderer.js to app.js, as this will contain the main app logic on the renderer side. We can also add a style sheet for this main content, main.css. Next, we can update the references to these files in main.html. Open that file, changing first this require statement to now include app.js instead of renderer, as we've renamed it. No need to actually include the extension. Get rid of these versions. Change the title of this main window to read it, the name of the app, and link your new style sheet, main.css. We've also renamed this file from index.html to main.html, so update the main process to load the new file as the main window's content, main window load file, renderer/main.html. Let's make sure all our changes are working, save this, and the app loads without any errors. Now, being a production app, one of the very first things we'll want to add is state management for this main app window. Right now, it's being launched at those specified dimensions in the center of the screen every time. So, to have the window keep its size and position, we can add and configure the Electron window state module. We've already covered this in an earlier lesson, so I'll run through it a bit faster. Install the module as a production dependency with npm I Electron window state. Electron will add a module as a production dependency by default if it's not explicitly stated. That's done, so restart the watch command. And if we check in package.json, there. Always good to make sure the package is listed, as this will get bundled when we eventually build for release. Back to main.js, start by requiring the window state module, const window state keeper equals require Electron window state. Copy this module export, And right at the start of the create window function, we can configure our state keeper. Let state equals window state keeper, passing in an object for the default window size and bounds. I have of course already built this app in preparation for these lessons, so I have some sizes that will work well. Default width set to 500 and default height to 650. No need to specify default X and Y coordinates, as this defaults to the center of the screen anyway. Then, to use the persisted states when the main window gets created, set the window's X coordinate to state.x and Y to state.y. Width being state.width and height to state.height. So we're using the default X and Y coordinates initially, being the center of the screen, but then once they change, we still want to keep the new window position, hence adding the state bounds here, X and Y. I'm also going to enforce some limits to the size of this main window, setting minimum width to 350, maximum width to 650, and minimum height to 300. These size limits will make more sense once we have the app working. Essentially, we don't want it to be reduced to nothing, which is where the minimum width and height come in, and we also don't want it to get too wide, as the list of links the app will contain won't look right in a wide format. Then, with our window state configured, the final step is to tell this window state keeper instance which window to manage. State.manage main window. Save this, and as I've already done this before, my app is created at the last position and size I had it at. I'll separate this DevTools window. I can now move this into place for the remainder of this project section. And to persist this new size and position, I'll quit the app, as that's what will trigger a state update in the module. Okay, so our window state is now handled. Next, we can add the basic HTML structure of this main window. Now, I will be going a bit fast in adding the HTML structure, but remember, you can find the HTML for this lesson in the lesson resources. Otherwise, feel free to just add along with me. I'll start by replacing this h1 with a header tag. This will be the only small control area of the app. Add a button, which we'll use to add items to the app. The button text can be a plus character to indicate adding something. And remember, we'll be using vanilla JavaScript to select these elements. So assign an ID of show modal. This will again have a bit more meaning in a minute. Basically, clicking the add button will present a modal to input the link we want to save. Then, still in the header, the second and only other element being a text input with an ID of search, as this will be used to search saved items. Setting some placeholder text of search. Then on the main app content, being our saved items, I'll use a main tag. These semantic HTML5 tags won't really have any meaning in an Electron app, but it still provides a bit of structure and logic when reading the code. Add a container in this main tag to hold our items, ID items, and also in this main tag, separate from the items, set some text which will only be visible when no items exist. No items, giving this paragraph tag an ID of no items. As mentioned, when we click this plus sign, we'll want to present a simple modal overlay to input and add the item. So create that modal, a div with an ID of modal, giving this modal a text input for the item's URL, ID URL, with some placeholder text of enter URL, then a button to confirm or add the URL entered, ID add item, same for the button text, and lastly a second button with which to cancel or close this modal, ID close modal, with button text cancel. That's it for our app HTML, so save this, reload the main window, and there, no items at the moment, with a button to show this modal section here, and an input to search any saved items. We can add the styles for this next, In main.css, I'll start by setting 100% height on both the HTML and body tags. Then, styling the body tag alone, set the app font to match that of the operating system with font caption, remove any default margins on the body element, and set this body element to have a display of flex. This is of course referring to the CSS flexbox model, something we can comfortably use without any worry about browser support as we're running in the latest Chromium browser. If you're not familiar with Flexbox, I've linked to a small tutorial in the lesson resources. This will just allow us to dynamically arrange child nodes of this body element, a much better solution than using percentages or floats. Next, I'll set some default button styles, setting a background color of Dodger blue, text color white, border radius of 5 pixels, so just rounding our button corners off a bit, no actual border, font size of 20 pixels, and no outline, something Chromium will also add by default. Same default styles for inputs, with the same font size as buttons, 20 pixels, same border radius, but setting an actual border of 1 pixel solid silver. Padding to 0 top and bottom, and 10 pixels left and right. We can also style the placeholder text inside of our inputs using the placeholder modifier, giving that text a color of light gray. So that's some default styles. Then, to move on to specific elements, I'll start with the header tag. Background light gray. Display also flex, as we can use Flexbox for the button and the input inside of this header. Padding of 10 pixels. Font weight bold, with a bottom border to separate it slightly from the items in the main content, 1 pixel silver, and a bit of shadow, again to help with that separation from the main content. Then moving to the elements inside of this header, starting with the plus button or add button, ID show modal, this button here, set some padding, again pre-tested values here, nothing at the top, 12 pixels left and right, and 5 pixels on the bottom, 10 pixels of right margin, and slightly bigger font than the standard button font, at 30 pixels. Next, the search input in the header. This already has some styling from the input selector up here, but to have it take up the remainder of its parent element, this header, assign it a flex grow value of 1. Save this, reload the main window. I'll do the same for this items container, but instead of having it grow in width, I'll have it take up the remaining height under the header, meaning we'll have to make the parent container a flex column instead of a row. Setting on the body element, flex flow column. Save this, reload. There, we now have the header at the top, then the items, and right at the bottom this modal window, which we still need to style and hide. Before doing that, I'll improve this no items text a bit. ID no items, font weight bold, color silver, center align it with 100% width. And to make sure our items, once we add some, is on top of this message, so essentially hiding it, set this to have a position of absolute at 100 pixels from the top of its parent container, and a z-index of -1, setting it to always be at the back. Onto the modal then. We want this to overlay the entire app when opened, so set it to also be absolutely positioned, width 100%, height 100%, with a slightly transparent black background color, using RGBA of 000 or black, and a transparency of 0.85. Display flex, so we can use the flexbox on the elements inside of this modal. Align items to the center, being any flex items inside of this modal. Also align content to the center with flex wrap to wrap, meaning let items wrap to a new line when it gets too wide. We can check this, reload, getting there. The modal is fine, just need to finalize these elements. And of course, once we have this ready, we'll want the modal to be hidden, so display none, which I'll leave commented out for now so we can test it with this display flex property instead, which is what we'll apply when showing the modal. Style the URL input, ID URL, again flex grow to 1, meaning take up all the available space, which with this flex wrap set to wrap will be 100% of the modal container if available. Also set the width explicitly to 100%, some margins to space it out a bit, 0 top, 25 left and right, and 15 pixels bottom, with lastly some padding, 10 pixels. Then the modal buttons, both can get some padding, 10 pixels. Target the cancel button next, ID close modal, background white, with black text, and space it away from the add button on its left by 15 pixels. Lastly, the add button, I'll just offset this from the side of the modal by the same 25 pixels as the input. Save this, reload the app, and that's what our modal will look like when opened with the plus button in the app's header. We can now hide the modal, enable this display property, save and reload again. There. A simple message telling us we have no items at the moment and all the user interface ready for us to start connecting with some events in the next lesson. In the previous lesson, we created the user interface for our app, mainly HTML and CSS, with the very last step being hiding the modal window through which we'll submit a new item. So in this lesson, we'll connect the basic logic for showing and hiding this modal and submit a new item to the main process. I'll close this style sheet for now, as we'll be working in this app.js mainly, main.js as well. Keep main.html open for a reference, as we'll be selecting these nodes by ID, and open app.js, the script we're linking here. App.js then being responsible for everything that happens on the user interface, or the main window renderer process. Remove this, and start by referencing some of the DOM nodes we'll be adding event listeners to. Let showModal equal document.getElementById, this button here with an ID of showModal. I'll duplicate this to speed things up. This one setting closeModal, document.getElementById to closeModal, being our cancel button in the modal popover, and the modal itself, selecting element with ID of modal. Okay, that will do for now. We want to show the modal when showModal is clicked, and hide it again when closeModal is clicked. I'll add showModal first, listening on showModal, with add event listener for a click, so clicking the plus button in the app header, setting the modal's style.display property to flex, which, if we recall from main.css, is how we had it initially before hiding it. This JavaScript setting then will override any style sheet styles as it will be applied inline. That's all we need to show the modal. So duplicate this entire listener for closing or hiding it, listening on closeModal, the cancel button, for a click again, setting the modal's display style back to none. We can test this, save, the app reloads, click this plus button, and there we have the modal. Click cancel, gone. Okay, so that's our modal working, simple enough. The next step we can add is getting the value of this URL input when add item is clicked. As before, reference those HTML nodes, add item, selecting the button with ID add item, and item URL, the text input for the item URL, which has an ID of URL. Handle new items being added, setting a click listener on that add item button, add item.add event listener, click, with a callback, in which we'll first make sure a value is set in the text input. You can of course go further by checking if it's a valid URL as well, but this will suffice for now. If item URL.value, meaning it's truthy, log that value out for now. Save this to test. This window position isn't persisting as the app is forced to reload each time and not actually being quit. Open the modal, mydomain.com, click add item, and there, we see the value logged in the console. So the basic user interface of this modal is now hooked up, but we can improve this slightly. At the moment, after clicking add item, you still need to click into the text area before typing, an unnecessary step as opening the modal already implies the user wants to input a URL. We can easily fix this though. I'll quit the app this time to persist this window arrangement, adding immediately after showing the modal, item URL, focus. Save. The app window's position is correct this time. Try again, and there. The text input is focused as soon as the modal opens. A simple but significant improvement. Another such improvement would be to allow the user to submit an item by hitting enter. Right now, nothing happens when I press enter, saving a further manual click on the add item button. These small considerations for how users tend to interact with apps is very important to keep in mind. Back in app.js, we can listen for a key event on that input. Item URL being the input, add event listener, key up, being when the user releases the key. For a key such as enter, key down will be fine as well. This will fire on any key being released, so check for the enter key with if e.key, this event object, equals enter, in which case perform a click on the add item button, add item.click. Save, open the modal and enter something, my domain, enter, and there. We get the same log in the console as we essentially click this button for the user when they hit enter. We're now ready to start adding submitted items. So I'll remove this log message, and to make this a bit easier, let's build the HTML that will represent such an item. I'll just add a static item directly in the items container, a div, with a class of readItem, using a class this time as we'll have multiple items. And what we'll want from such an item is the title, so the HTML title of the page loaded by the item URL, and a thumbnail of the page, basically a screenshot. Start with the thumbnail on the left of the item, image, with a test source of HTTPS, placeholder it 500 by 500, and an h2 tag for the title of item added. That's it, really basic. We can add some styling to these items, open main.css. All the way at the end, add on the readItem class, display flex, align items center, same for flex content, center, a bottom border to separate these items, light gray 2 pixels solid, with a slightly off-white background, FA, and 10 pixels of padding. Size the item thumbnail, read item image, width 20%, with a 25 pixel margin on the right to separate it from the title. Check this so far, reload, and that looks about right. Make sure our app header remains static once we have more items in this window space. I'll duplicate them a few times. Save, reload, scroll, and there's a problem. This header should stay fixed at the top here, with the items container only taking the remaining space as a flex column. I set the body to have a display of flex column, meaning the flex grow property should be set on the main tag, not items. Find that, Here, I'll change this to main, being the sibling tag of the header, not items. And also give this an overflow of scroll. Save and try again. There, this time it works. The body element is a flex column. The header takes up its needed amount of space, and then the main tag containing the items and the no items message has a flex grow property of 1, meaning take up whatever remains of the body. I'll get rid of these items until we add a real item later, resetting items to an empty container. Then, back in app.js, we'll have to send the URL of the new item to the main process. The main process will fetch the item screenshot and title, returning it to the renderer where we can create an item out of it and add it to the app. To do this, we'll of course be using IPC messaging, or more specifically in the renderer process, IPC renderer send, require that module, const IPC renderer using destructured assignment equals require Electron. Set a channel name to send this over, new item, sending the URL of the new item, item URL.value. That's all there is to sending the item. So over to main.js where we can listen on that channel for a new item, first requiring IPC main, the main process equivalent of IPC renderer, listening in the global scope, not that this matters, for a new item request. IPC main on, this channel name the item URL is being sent over, new item, a callback providing the event object and the data being sent. Call it item URL in this case, which I'll again log out for now. Save. The app relaunches, so add a new item, mydomain.com, enter, check the terminal for the main process log, and there we have it. So we're successfully sending the item URL to the main process, where we can now get the new item and send it back to the renderer. The actual fetching of the new item we'll do in the next lesson. So for now, I'll just simulate the wait it'll take with a timeout of 2 seconds. Sending back to the sender of this message, e.sender, being the sender of this event, new item success, the channel name on which we'll be listening for the returned items in the renderer. New item from main process. A simple string for now until we implement this. Add the corresponding listener on the renderer. Listen for new item from main process. With IPC renderer on that response channel, new item success. Same callback as in the main process IPC module, event and data, or new item, being that simple string for now, so log it out. Save both these files, adding mydomain.com. Remember, this will now be sent to the main process, and after 2 seconds we'll get a response. Enter, and there, new item from main process. So that's all good. We now have two-way communication in place. But at the moment, during the time it takes the main process to fetch the item, or in our case for now during that 2-second timeout, this button can be clicked again and again, resulting in duplicate items, or even a lockup if the user clicks it enough times. So to communicate to the user that this item is being fetched and added, we'll have to provide some visual feedback, and disable the add button, re-enabling it only once the new item is back from the main process and everything is done. To do this, I'll create a reusable function, disable and enable modal buttons, a toggle so to speak, assign this function to toggle modal buttons, equals a function. First thing in toggling a button would be to know whether it's currently enabled or disabled, so check its state. If add item dot disabled equals true, meaning it's disabled and we have to toggle it back on. Else, meaning it's enabled and needs to be disabled. I'll start with this as the first will be reverting the button state back to what we currently have. Set add item dot disabled to true, Make the button slightly transparent to better show the state to the user. Style.opacity equals 0.5 or 50%. Change the button text to a more appropriate label. Inner text equals adding. Remember, this disabled state being when an item is being sent to the main process and is being waited on in the renderer. We can also hide the cancel button. No use having the user close the modal whilst an item is being fetched. Close modal.style.display equals none. I'll copy all these settings to the first condition where we'll revert them to their original state. Disabled false, opacity 1, button text back to add item, and show the cancel button with display inline, its default display property. Copy this function, calling it immediately after sending a new item request to the main process, which will disable the buttons, toggle modal buttons, and then again after receiving the new item back from the main process, which will of course re-enable the buttons. We can also at this point hide the modal and clear the input value, keeping it ready for another new item to be added. Same as clicking the cancel button, set the modal element's display to none, and item URL's value back to an empty string. Save. Click to add a new item, myitem.com. Notice the button now when I submit this. Enter and disabled, with the modal closing as soon as that new item is received back from the main process. Reopen it, and it's ready for a new item URL, with the button enabled and the URL input empty. In the next lesson, we'll implement the off-screen renderer to create that new item from its URL. In the last lesson, we added the process of submitting a new item URL, sending it to the main process, and listening for a reply with the item details. We also styled the items for when we eventually add them to the app. So in this lesson then, we'll remove this timeout in the main process, which was simulating the time it's going to take to get a new item's details, and add the actual logic for doing that. As mentioned before, we'll use an off-screen browser window to fetch the item details from the given URL. I'll also be separating the code for getting a new item into a separate module. So first thing, change this set timeout to a function called readItem. The function we'll create and import in a second, keeping the callback function with the response message, except that this callback will now hold the new item as its only argument, and pass to the readItem function the URL of the item to get as its first argument. Get rid of this time, sending to the renderer the new item provided by this function's callback. There. We get a request from the renderer for a new item, pass that item to readItem, which doesn't exist yet, readItem providing us a callback with that new item, which we send back to the renderer via IPC. We can now add the module from which to import the readItem function. So start with a require statement for that module before we create it. Const readItem, as this module will export this single function only, equals require readItem in the current directory. Could have named this readItem.js also. Create the module file in the project root as we're importing it here. New file, readItem.js. This module then exporting that readItem function will essentially create a new off-screen browser window. Load the item URL into that window and get from that a screenshot and the page title. So knowing that, require the browser window module from Electron. Then, as with any new browser window, create a global reference to hold that browser window instance and prevent it from being garbage collected. Call this off-screen window and export the single function provided by this module, setting module.exports, so overwriting all the module exports, equal to an anonymous function receiving a URL and a callback function to execute with the item retrieved from this URL. Exactly as we're passing it in here. Create the off-screen window, assigning to the global off-screen window variable a new browser window with a width of 500 and a height of 500. Remember, the screenshot we'll be getting from this browser window will be this size, so a 500 by 500 square should do the trick. Set show to false, with some web preferences, off screen to true. And the single most important setting here, unlike in our main window, we want node integration to be false. Remember, this browser window will be loading insecure remote content from this URL. So the last thing we want is for it to have access to our file system via node. That said, false is of course the default value since Electron version 5, so I can leave it out, but still a very important concept to understand and be aware of. Don't just set node integration to true everywhere. There's a very good reason it's been changed to have a default value of false. Okay, that's our off-screen window ready. So load the item URL into this browser window, or renderer, this time using load URL instead of load file, passing in the URL given to this function. Then we'll wait for this URL to finish loading before getting the item screenshot or title. So listen on off-screen windows, web contents, for the did finish load event. Passing a callback, where we can first get the page title, assigned to title, off-screen window.get title, and a screenshot or thumbnail of the fully loaded page. We can do this in a slightly different way than we've seen before, being remote content, calling on the Windows web contents, capture page. This function providing a callback only with the screenshot image, this image as always being of type native image. And the easiest way to use this image is going to be as a data URL. This way we can store the image data easily and not write out any files to the app, assigning to screenshot image.toDataURL. This being our final step of getting the item. We now have the item title, thumbnail, and of course the original URL. So pass all of this back to the caller of this function via the function callback. Executing callback, this callback function passed to the readItem function, with the new item object as this callback's only argument. Setting the item title to this title variable, which we can simply write like this, having the key and value names match. Screenshot, so setting on the screenshot key of this item object the screenshot variable. And lastly, the original URL of this item, a useful addition to complete the item object. I'll also clean up this off-screen window as we're done with it, just good practice. Closing the window with off-screen window.close and setting the global window reference to null. There. That's all we need this readItem function to do. We call the function with the item URL and a callback function, as we do here, get all of the item details in an off-screen window, and execute the callback with that new item object. That callback still sending the item to the main renderer, or main window, via IPC where we log it out. So let's test this. Save both files. I'll add a valid URL this time. electronjs.org. Enter, which disables our modal controls whilst we wait for this item to be fetched in the main process. And as soon as that item is done, the main process sends it back where we log it to the main window console. I'll expand this item object, screenshot with the image data as a data URL, title, the Electron JS homepage title, and URL, being the item URL we submitted. So that's our item ready to be added to the app. In the next lesson then we can finally add the items we've already styled in this container here and also add some basic storage. In the last lesson we implemented all the logic for getting a new item from the main process, such as this one logged in the console. And in the lesson prior to that we also created and styled the HTML that will represent such an item in our app. Meaning we can now go ahead and display items received back from the main process and furthermore persist them. All of this will of course be happening in the main window renderer, so over to app.js, where instead of logging this new item out, we can now add it to the items element. I'm once again going to separate all of the functions relating to items into a separate module. This way app.js can control the overall app function, things like user interface, etc., and items.js, the module we'll create, can be responsible for abstracting item logic. Meaning, to add an item, we'll call on the items module add item, passing it the new item received from the main process. Create the items module, starting with the require statement again. Const items equals require items locally, so referring to items.js. Add the file in the renderer directory, as that's where we're requiring it from. New file, items.js. So far, we are calling the add item function on this module. So start by creating that exported function, exports.addItem, not module.exports this time, as we'll be exporting multiple functions on this module. This being a function as we're calling it here, so taking the new item as its only argument, equals a function with the item parameter, being that new item. Then we can create a new HTML element as we styled it earlier. Let item node equal document.createElement, a div. Assign the class we styled as we have it in main.css, readItem, item node.setAttribute, class, read-item. Then we can add the inner HTML to this new div, being the thumbnail image and the title. Item node.innerHTML equals, using a template literal for better legibility, an image tag with a source attribute of item, this item here, dot screenshot, the data URL of this item screenshot. The h2 title tag with the title of the item, item.title. And finally, append this to the items container. We don't have a reference to the items node in this module, so create that. Let items equal document.getElementById items, same as in app.js. Appending the new item node to the items div with items.appendChild item node. We can test this, save, add a new item. I'll do electronjs.org again. Enter, and a second later that item is added to our app with our existing styles. Also note that the no items message is now no longer visible, as it's obscured by this item, a convenient solution to not have to show and hide it manually. I'll do another, say github.com, enter, and done. So we're now successfully adding items to our app, but when I reload the window, gone. So the next step then is to persist or store items in our app. For the sake of keeping this simple, I'll be using local storage, the built-in storage already available in every browser window instance. If you recall from the session lesson, local storage is stored in the default Electron session, so a perfectly reliable storage option for simple data such as this. Back in items.js, I'll create an array to hold all of the items. That way we have one variable to manage and persist. Exports.storage, storage being the name of the array to hold the items, equals an empty array for now. Next, add the module function for persisting the storage array, or items array. Exports.save equals a function in which we can save the entire storage array to local storage, calling localstorage.setItem. The setItem function either creates or overwrites a key in local storage, storing our items on readit items, the local storage key name. This .storage. But local storage only supports simple strings, not objects, so stringify this array object with json.stringify. There. Each time save is called, or items.save, we store this entire array of items as a string in local storage. Meaning each time the app starts, we'll also want to set the storage array to the value of the read items key in local storage. So loading back in all of our items. We can get that array from local storage immediately when this module is required with local storage items.getItem. Read it, items. This key we're saving our items to. Again, keeping in mind that we stored this as a string. So convert that back to an array with json.parse. If this entry doesn't exist, we'll want to still set storage to an empty array. So using a simple conditional, say or empty array. Then we'll have to make sure each time a new item is added, it goes into the storage array. So immediately after appending an item, we can add it to the storage array and persist that array to local storage. This.storage push item, the item object we added, calling immediately after this.save, updating the local storage entry. Test this. Of course, we have no items as the app relaunched, so add back github.com, meaning this item will now have been added to items.storage and written to local storage. We can check that in the DevTools, Application tab, Local Storage. There, we see the read items key, with its value automatically passed and logged in the relevant console, an array with one entry, being this one item object. Expand that, and we see the screenshot, title, and URL. Yet still, when we reload this window, our items are gone. We might have saved them, but we're not adding the stored items back when the window loads. So let's do that. Add items from storage, this array, when app loads. We can simply loop the storage array and manually add each item. This.storage.forEach, providing us the item in the loop function, calling this.addItem, this function here, with the current item in the loop. Only problem now is if we do this, we'll be pushing each existing item into the storage array a second time and saving it. Not what we want. So we're going to need a condition here. If isNew, a function argument we'll create now, add and save the item. Add that isNew argument to the function with a default value of false, so not a new item, meaning this will now work as expected and not add the items a second time, false being the default. But in app.js, when adding a new item, we can set the second argument to true, only having items fresh from the main process pushed to and persisted in the storage array. Test this again. I'll save all. And immediately our one existing item is shown when the app launches. Add another, electronjs.org. We now see two items in the local storage entry as this new item was stored. Reload, and both items is loaded. So that's our items done and persisted. In the next lesson, we can create the code to select, filter, and open items. With our items working, the next step is to add basic navigation for these items. This includes selecting an item for opening and filtering items with the search field here in the app header. We'll start with the search field. What we want here is to simply filter all the elements by title. For example, typing GitHub into the field should leave only this first item visible, as that's the only title containing the text GitHub. Back in app.js, as the search field is part of the user interface, add that selector search equals document.getElementById search, the ID of that search input. Then we can add the listener to filter items when this item receives text input. Listening on search for key up. Now we'll have to loop all of our items to check each of them. We can do this by class name, as all the items have a class of read item, but to convert that HTML collection to an array, we can say array.from, so create an array from, document.getElementsByClassName, read item. Just to clarify what's happening here, this getElementsByClassName selector returns an object of type HTML collection, very similar to a normal JavaScript array, but not quite, so we can't loop it directly. But passing it to JavaScript's array from method, we essentially just convert its type to a standard array, meaning we can now loop it. The elements in this array stay exactly the same, so we can still use them. We'll loop this array with for each, providing the item in the loop function. And all we want to do here is hide any items that don't match the search value. I'll assign the result of the match check to hasMatch, checking the item.innerText, the only text being that title, so this will work perfectly, to lowercase, no reason to check case-sensitive matches, includes search.value, the text value of the search input. hasMatch will now hold a Boolean value based on whether the item text matches the search field. So set the relevant item's display property with item.style.display equals, using a ternary operator, if hasMatch is true, set the display value to flex, flex being the current display value of the items, else meaning the search did not match the item, none, so hiding the item. Save this to test. I'll add a third item to have a bit more to search here, nodejs.org. Done. Check for that GitHub value again, and that works, with only Git being unique enough to filter down to that single item. JS leaves Node, and CSS leaves only Electron. Okay, that's our search done. Next up, we can implement the item selection. The reason we want to add item selection is that we might not always be interacting directly with items. Remember, this app will have a menu with which to open items, or even keyboard shortcuts, all things we'll implement later on. So, to open or delete an item isn't always as simple as clicking on it. That being the reason we always want a selected item. To indicate an item as being selected then, I'll add a simple left-hand border. Over to the style sheet, main.css, find the read item class, here, adding to all items border left, 10 pixels, solid, light gray, this being the unselected border color. We can also add a hover color to make the cursor interaction a bit better, read item hover, set the item background to EEE, a very light gray, with lastly read item.selected, so a read item with a selected class, make that left border color Dodger blue. We can test this, reload the window. Hovering now provides a bit of feedback, a small but useful improvement, and when we add a class of selected to one of these items, I'll just do it directly in the DevTools, selected, we see that blue border, indicating that this item is now selected. So let's add that selection logic then. I'll add this as a new exported function of the items module. So in items.js, set item as selected, calling the function select. This function will hold a possible event object when triggered with a click or something similar, with the first step being to unselect the currently selected item, or remove its selected class. Get that element with document.getElementsByClassName, read item selected, of which there can only be one, so array index 0, accessing the element's class list and removing selected. Then we can add the class to the newly selected item, or clicked item for now, getting that element from the click event object, this argument here, with e.currentTarget, being the element that was clicked, classlist.add selected. Okay, so we have this function now, which we can use when an item is clicked. But it's not as simple as adding a click listener on all of the items, as when new items get added, that listener won't be set on them. So instead, we can bind a click listener on each item as it gets added to the app interface. Easiest place to do this is going to be in the add function. Immediately after appending an item, say item node, the new item element we create and add event listener, click, this dot select. So when this element is clicked, call the select function with this click event as its one argument. Another useful addition will be pre-selecting the first item, be that when the app loads or once the first item gets added manually. We can simply check how many items exist in the items container if document.getElementsByClassName read item item.length, being the length of this HTML collection, which of course at this point, having already added this item, must be 1 or more, equals 1, so only this item has been added. Call on the first item classlist.add selected. Save and test this. Immediately the first item added from our stored items is already selected. Click to select a different item, and that works. Now, as mentioned, we want to also be able to navigate items using the keyboard. So using the up-down arrows, we should be able to select the previous or next item from the currently selected one. To do this, I'll switch back to app.js, keeping our user interface logic here. Navigate item selection with up or down arrows. This time we're not listening on a specific element. So add a global listener with document.addEventListener, key down, the event object, checking if event.key equals arrow up or event.key equals arrow down. Call items.changeSelection with the name of the key as the function argument, e.key. Add this function to the items module. Move to newly selected item. Export.changeSelection with that direction argument being either arrow up or arrow down. The first thing then to determine in this function is which item is currently selected. Let current item equal, we're already getting the current item in the select function, so copy this, paste. Then check if we're selecting the previous or next item by checking for up or down arrows. If direction, this event key argument, equals arrow up, and, very importantly, an item previous to the current item exists, which we can check with currentItem.previous_sibling. Remove the selected class from the current item with currentItem.classlist.remove, selected, and add it to the previous sibling, currentItem.previous_sibling.classlist.add, selected. Next, handle in the exact same way the down arrow, meaning select the next item if it exists, else if direction equals arrow down, and current item.next sibling. Remove selected from the current item as before, and add it to the next sibling. There, that should do. Save. The first item gets selected when the app launches, so press down, and the selection moves to the next item. Up, and back to the first. So we can now very easily select an item with either a mouse click or using the keyboard. And ultimately the reason for being able to select an item is so that we can open it for reading. So let's add the first version of that. Staying in items.js, export a new function for opening the selected item. Call it open. No arguments. With the very first thing to check here being whether we have items. Else we'll just stop trying. Performing this check will ensure we don't have problems later when using keyboard or menu shortcuts to open the selected item. If not this.storage.length, so no items in the storage array, return. If we do have storage items, however, proceed to getting the selected item. Let selected item equals, using the same selector again, I'll copy this, get the selected item's URL. This being so that we can open that item's saved URL for reading, assigning to content URL. Right now we don't have a way of getting the URL from the item, but an easy way to add it is as a data attribute on the item element. We can add that in a second, but the way we'll access this is through the item or selected items dataset.url, the name we'll give to the data attribute. Add that to all items when creating them. In the add function, set item URL as data attribute with item node.setAttribute data-URL. If you're not familiar with data attributes, I've linked to a short tutorial in the lesson resources. And setting that to item.url, the URL property from this item object. We can test this. Log out the item URL in the open function for now. Console.log, opening item, content URL. The URL we're getting from the selected item via this data attribute. We still need a trigger for this open function. Again, adding a listener in the add function when creating the item node. We're already using a single click, being to select an item, so to open an item we can use a double click instead. Item node.add event listener, double click or DBL click, calling this.open. Keeping in mind that what will happen here is that the first click of this double click will select the item, as per this single click listener, and the second click triggering the double click will call the open function, opening the newly selected item. Save all of this and test. I'll switch back to the console so we can see that open log. Double click this first item, and there, opening item github.com, and same for Electron JS, also selecting the item opened. Note however that using a double click now highlights the item text. Definitely not a good look for a desktop app. We've covered fixing this in an earlier lesson, so over to our style sheet, adding to our items, WebKit user select, none. Save, reload this window, and now it all works without any selection. Much better. In the next lesson we'll create the window to load this item's URL into. In the last section we added the ability to select an item and the action of double-clicking to open that item for reading, which at the moment simply logs out the URL to open. So to add the logic for our new open function, let's switch back to items.js, here, where we can now, instead of logging the item URL out, launch a new window in which to load the item URL. We can of course do this a number of ways, but the easiest for our purpose is going to be using a proxy browser window, a concept we've covered earlier in the course, using the window.open function to automatically create and reference a new browser window. Assign that window reference to reader when, creating the window with the item URL by calling window.open content URL. I'll leave the window title empty as that will default to the title from the content URL. Save this. Open the first item as before by double-clicking, and we get that window with the item URL loaded, essentially completing the ability to read saved items from our app. That said, we still have a number of issues and possible improvements here. First of all, the window is being created at the default window size, with its X and Y coordinates at the same point as the main window, so we can style that. And secondly, as the main window was responsible for creating this reader window, all of the reader window settings gets inherited from that main window, including node integration, meaning we're now loading remote content into this window with full access to node and essentially our file system. Same thing for minimum and maximum width and height, although this window was created at the default size, so when I resize, it snaps to the same size limits as the main window. Not ideal for reading. So let's fix all of this with some custom settings on the proxy window. If you recall from the browser window proxy lesson, we can pass any of the standard browser window options in string format, along with a few variations such as the node integration setting. I'll use backticks for a template literal string, just so I can write this across multiple lines for legibility. Start with those window dimensions. Max width equal 2000, this being purely to overwrite the inherited setting from the main window. Any large number will do. Same for max height, 2000. Initial width can be 1200 and height 800, with a slightly off-white window background color, DE. Then the all-important node integration. Remember, this is enabled in the window responsible for opening this reader window, here. So disable it by setting node integration with a capital I, 0. We don't use false in string form, but rather 1 or 0 for true and false. And for good measure, also set context isolation to 1 or true, meaning this window's JavaScript is executed in its own isolated context, without access to any other JavaScript, like that of our main window. The default here would have been true anyway, as that's the default value on main window, but better to set it anyway, just safeguards it a bit in case the main window settings change. Save this to test again. I'll open the Electron JS item this time. And there, a much better sized window with that off-white background, also being secured now. Okay, so having this item open in its own window is great, and we can close this once we're done with it by simply closing the window. But let's say we want to add our own controls to this window, for not only closing it when we're done, but also deleting the item at the same time. Back in the open function, immediately after creating this window, we can inject some of our own JavaScript to add what we need, calling on the reader when proxy window eval with a string of JavaScript. For example, alert hello from items.js. Save, open an item, and as soon as the content loads, we get that alert right in the remote content. So knowing this, let's create a button for handling the closing and removing of the open item. This is of course going to be too much JavaScript to write directly into the string. So instead, I'll add it to a separate file and load the content of that file into the eval method. Call it reader.js, copy this variable, to which we can assign the JavaScript we want to evaluate as soon as the app loads and requires this items.js file. I'll create that file to hold the reader window JavaScript in renderer reader.js. Test using an alert again, hello from reader.js this time. Back in items.js, define that reader.js variable, to which we now want to assign the content of reader.js. Not required as a module or anything, simply read its contents so we can pass it to eval as a string. I'll use the fs module to read the file content, fs.readFile, require fs, const fs equals require fs, passing the readFile function the path to the file, dir name, being this renderer directory, as both files is in the same directory, /reader.js, a callback in which we can use the file contents, providing us an error object should anything go wrong, and the data, or content. Assigning to that reader.js variable data.toString, as readFile returns a buffer by default. Okay, so as soon as the app loads, the main window gets created. That in turn requires this file, items.js, where we read the content of reader.js and assign it to reader.js, the variable, ready for injection once an item is opened. Here. Save both files. Open github.com again. And that works as before, except that we can now write JavaScript for this window in a completely separate JavaScript file. In the next lesson then we'll continue in that new file by creating a button in the reader window to both close and delete an item once we're done with it. Picking up from the last lesson, we are now able to open items for reading and close them. But as discussed, we want to add the ability to not only close an item, but also delete it at the same time. Starting back in reader.js, the script being evaluated in our remote item content, we can add the button to mark an item as done. Assign the new button element to a variable of readItClose, creating it with document.createElement, make the button a simple div, with a label of done, implying we're done with an item and it can also be removed. Add some styles to have this div element resemble a button, setting its position to fixed. Copy this style property, bottom to 15 pixels, so 15 pixels from the bottom of the parent container, being the body tag once we append this element to it, same 15 pixels from the right, some padding, 5 pixels top and bottom, and 10 pixels left and right. Font size can be 20 pixels, important to keep this font size as an absolute size, and not a relative or percentage value, as that will then vary depending on the remote content's font size. Something to keep in mind as we're adding this button to an essentially unknown environment. Font weight to bold, with a Dodger blue button background, white text on that blue button, a slight radius to the button corners, 5 pixels, make the cursor display an arrow when hovering over the button with cursor default, and lastly, separate the button from the content behind it by applying a slight shadow, 2 pixels by 2 pixels, with a 2 pixel blur and a very transparent black, 0.2% opaque. That's the button styled. So as mentioned, append this to the remote content's body element. Remember, this script is executed in the remote content scope. So select the body element as you'd normally do with document.getElementsByTagName, body, accessing the first element as there can only be one body tag, append child, read it close, this div button. Test this works and looks right. Open an item to have the script injected, and the button gets added. Of course, this doesn't do anything right now, so attach a click listener to the button, this time using the element's onClick attribute, equal to a function with the click event, in which we'll simply display an alert for now, done with item. Save to test again. Open an item as before, which gets the button added a moment later. Click, and the reader window shows that alert. So our button is now hooked up, meaning the next step is to communicate with the main window. Keep in mind that we don't have access to IPC messaging or the main window context from within the reader window. So instead, we can use HTML5's messaging API. This API allows us to send a message to any window instance, meaning as long as we can get a reference to the main window, we can securely send a message to it. And with this reader window being a proxy browser window, Electron provides us a reference to the window responsible for opening it. Accessing on window, the opener property. Opener being a safe reference to the main window. Send a message to that main window with post message, with a message of item done, to any target origin, indicated by the asterisk. We'll have to listen for this message in the main window, or items.js, as that's required by the main window. Right at the top here, listen for done message from reader window. Listening on the window object with the standard add event listener for message. Add a callback on this message listener, in which we can log out the message data by accessing it on the event object, data. Save both files. Open an item. I'll move this reader window out the way so we can observe the main window's console. Click Done, and we see the message sent from the reader window in our main app window, item done. Okay, so now being able to tell our app that we're done with the item, let's add the code to delete an item at a certain index. Remember, the main window has no way of knowing which item this message is referring to. So along with the message, we'll have to tell it. And the easiest way to do this is going to be giving it the item index. That said, the reader window itself doesn't know which item it's dealing with. At the moment, the reader window is simply created to load a given URL. So we'll have to inject the item index along with that button code. Step 1 being to get the actual index of an item. I'll create a new function for this. Exports.getSelectedItem, being that when an item is opened, that item is also selected. As before, get the selected node. Let current item equals document.getElementsByClassName. Read item selected, item 1, or index 0. Then, using a simple loop, we can determine the index of the selected item in its parent container. Start by setting item index 0, add child equal to current item, looping with while the child element equal to the previous sibling of itself. So attempting to set this child variable to its own previous sibling. And if it's not equal to null, meaning a previous sibling exists, increment the item index by 1. This might look a bit odd, but it's pretty straightforward. For example, if the selected item, this current item, is the first item, it won't have a previous sibling, setting child to null on the first loop iteration, which will leave the item index as 0, or position 1. If, however, it had one previous sibling, it would increment once and be at index 1, and so on. Then, having the selected item's index, we can finally return both the item index and the selected item node as an object. Return an object with key node equal to the selected item and key index equal to item index, the value we calculated here. We can also now use this function instead of all the references to the currently selected item, just to clean things up a bit. Copy. First selection here, where we simply remove the item selected class, replace this selector with this.getSelectedItem.node, being the selected item, just a bit cleaner. We have a few more of these, so copy this. Here in the change selection function, set current item to this.getSelectedItem, accessing in the function currentItem.node, like so. Same in our open function, selectedItem, selectedItem.node, and that's it. Okay, back in the message listener, now having a way to access an item's index, we can call in this function this.delete, a function we still have to create, passing in the reader window's item index from the message. Again, something we still have to add. I'll say e.data item index. Copy this property name so we can set it on our message. That message, of course, coming from this reader.js. So back to the reader.js script. Make this message an object instead of the simple string with an action property, delete reader item. This just being a simple way of identifying the message in items.js, as we're listening for all messages in there, and item index, which of course we don't have in the script, so we'll have to dynamically set it. I'll make this a unique tag that we can replace with the item index, double brackets, index. Then back in items.js, when opening an item, this reader.js content will now contain that index tag. So having access to the selected item index here, simply replace that tag in the reader.js string with the item index. Calling on reader.js, replace, the standard JavaScript string replace function, double brackets, index, that tag we just added, with the selected item's index, or the item being opened, selected item.index. So now when clicking the Done button, we'll get an object sent via the message event with the item index to delete. We can test this. In the message callback, temporarily replace this call to delete, as that doesn't exist yet, with console.log e.data, that message object we're sending from the remote content. Save both files. Open the first item, so index 0. I'll again resize this down so we can see the main Windows console. Click Done, and there. The action as we set it, and the item index of 0. Try an item at a different index. I'll close this. Open Node.js this time, so index 2. Click Done, and again this works as expected. So we now have our item index, meaning we can close and delete an item when receiving the message from the Done button. Back in items.js, undo this log to again call that delete function, which we can now implement. But before we do, let's also make sure this message event is in fact the correct message, just as a precaution. If e.data.action equals delete reader item. Call this delete function with the item index. After which, meaning the item has been deleted, close the reader window for the user. This of course means again that we need a reference to the proxy window, or the sender of this message, which we can access on the message event as source. I'll log that out to demonstrate. Save. Open an item. Done. And there, browser window proxy, which if we expand it contains the standard browser window close function. So to close the reader window after deleting the item, call e.source.close. Save and test. I'll do Electron this time. Click the button and the window is closed, but not yet deleted. So let's finally add that delete function now. I'll uncomment this again, create the function, delete item, export.delete, with a single argument being the item to delete's index. First thing being to remove the item from the DOM, calling on the item's container element, remove child. This takes the node to delete, so get all the items in the items div with items.childNodes. ChildNodes returns an array of elements or items, so item at index, item index, this argument. That visually removes the item from our app, but it's still present in the storage array. So to remove it completely, say this.storage, splice, item index, one element. This just saying cut from this array one element starting at this index. And lastly, persist the storage array to save those changes. This.save. That's the item removal done. But when we delete this item, we no longer have a selected item, so we'll have to select another. The most logical way to do this is going to be selecting either the previous item in the list, or if it was the first item in the list to be deleted, simply select the element now in the first place. There's also the possibility of the deleted item having been the last item, meaning there's nothing else to select. To avoid that, start by checking if we still have items left. If this.storage.length, meaning we have one or more items in the storage array, go ahead and select a new item based on the index of the deleted item. Let new selected item index equal, using a ternary operator to check if we deleted the first item or not. If item index equal to 0, meaning it was the first item, set the newly selected item index to now be 0 as well, as we want to select the item now at the top. Else, meaning we have one or more items previous to the now deleted item, set the new selected item index to item index -1, 1 up. Select the item at that new index, first getting all of the read items with document.getElements by class name, read items, setting on the item at the new selected item index with classlist.add, selected. That should do. I'll save this. Open an item, Electron. I'll move this over to the right this time so we can see the items when I click done. Click and gone. That Electron item is removed from both the app interface and from storage, with the previous item automatically selected. That completes all of the app's item logic. So in the next lesson, we'll finalize this app by adding system menus and keyboard shortcuts. Our app is now complete in that all of the essential functionality has been added. So in this final project lesson, we'll be adding platform-specific application menus, shortcuts, and any other finishing touches to make our app a truly native experience. Over to the project code. And this time around, unlike in the API section of the course, I'll implement the application menu from the renderer process and not the main process, despite the menu modules being main process modules. This is a very common scenario when creating app menus, but will depend on the specific application's needs. At the end of the lesson, it will make more sense why working in the renderer process is best for this app. I'll be separating all of the menu code into a new script, just to keep things a bit more organized. Create that file in the renderer directory, menu.js. And unlike modules we required in the previous lessons, this menu.js script won't actually be exporting any functions. Instead, it's a standalone script that runs once when the app is opened, same as app.js. So require the file in main.html, after app.js, menu, I'll get rid of this comment, and save. Then in menu.js, knowing this file will be required when the app loads, we can start adding our app menu. The menu and menu item modules being main process modules, so require remote first in order to access those main process modules. Next, we can define a menu template, const template equals an empty array. We'll populate this with menu items in a minute, but having this template, build the menu from it, assigning to menu remote.menu, accessing the main process menu module via the remote module here, build from template, passing in the template array. And lastly, having the application menu set it as the main app menu. Remote.menu set application menu, this new menu object. Save this. And there, we now have an empty app menu with only this one item added by Mac automatically. This first item being the name of the app on Mac, which we'll update in the next section to actually display the real name of the app. And this menu, of course, right now contains nothing. So the next step then, having our menu being built from this template, is to start adding menu items. In the first menu location, add a menu item object with a label of items, this being the menu to control all of our app's item functionality. I'll set a submenu on this menu item, being where we'll add the submenu items for this top-level item, to an array for now. This being as a top-level menu item without any content won't be shown. We'll fill this in later. Then the second top-level item I'll set as the edit menu. If you recall from the lesson on menus, this is something we can have Electron handle for us by either using individual edit menu item roles, or the simplest way, give this entire menu item a role of edit menu. This role instructs Electron to create the entire edit menu for us, with operating system specific items. Third item, the window menu, with a similar role configuration of window menu. And lastly, as per convention, the help menu with a role of help. This role is a bit less complete and we'll have to add a bit more to it in a minute. But again, to have it show up in the menu, assign it an empty submenu for now. There. Note, however, that this won't work on Mac now, as we've set the first menu item as a custom menu item object with a label of items. Remember, Mac requires the first element to be the name of the app. So to add that required item in the first position for Mac only, we'll have to check the platform the app is running on, which we can do with if process.platform, the platform property returning either Win32 or Win64 for Windows, depending on the specific version of Windows, Linux for any Linux operating system, or for Mac to add this first menu item, Darwin. Darwin being the original name for Apple's operating system and still forms the core of Mac OS. Okay, so when this menu is being created on Mac, we'll add that extra menu item to the start of the template array. Template.unshift, an object, with the label being the name of the app. We can automate this by getting it from the app instance, accessing via the remote module app.getName. Add a submenu with the standard format for this Mac-specific menu item, starting with a role item of about, preceded by a separator item, type separator, the Mac services role, another separator, the hide item, hiding an app window again being something we only do on Mac, same for hide others, unhide, the third and last separator, and the final item being a role of quit. So we're now creating this menu, but if the app is running on Mac, we're adding this object to the beginning of the template array before building the menu. This should now work, so save, and there, we see all the new menu items with that first item having the auto-generated role items. Items is still empty for now, a very detailed edit menu including all of the undo, redo and textual commands, window to manage the app windows, and help, which by default contains a Mac-specific search field and an empty submenu. That submenu is however required, so let's add a cross-platform menu item to it. In this array, add a new menu item object, label Learn More, with a click handler in which we'll simply open a URL with information about the app. This can be a website for your app or even a link to the App Store listing. Just note that if you're going to launch the App Store link to your app, it's probably best to again check the platform and link to the specific App Store for the user's operating system. In my case, I'll simply launch the app repo on GitHub, this URL here in package.json. We'll want to launch this in the user's default browser, so using the shell module, call shell.openExternal, that URL. Shell being a shared module, we can simply require it from Electron as normal. There. Save this to test. I'll bring an empty browser window into view. Open the help menu where we see that new item, click, and the URL to the app repo is launched, providing the user with some more info regarding the app. Close this, and as mentioned before, the help menu also has that default search field, which is perfectly integrated with our app for finding app functionality. For example, typing cut shows us that a menu item with that name exists, and links to several related help articles. Hover that menu item, and we're provided a pointer to where it can be found, so very helpful. Okay, that's essentially all of the standard menu items done. Next then, we can move on to adding our app item functionality to this empty items submenu. I'll start with the existing commands, making them accessible via the menu. Item 1 being add new, with a click handler. And as the name suggests, this should do the exact same thing as clicking the plus button to open the modal for adding a new item, like this. But we obviously don't want to recreate the logic for doing that in this separate menu script. So easiest is going to be to create a global reference to that function. Remember, app.js and menu.js shares the same JavaScript context, both being included in main.html. Meaning both scripts have access to the same global window object. So as this add new menu items click handler, pass in a global window function called new item. Create that function in app.js, right at the top here, a global function to open new item modal, assigning to window.newItem a function in which we'll simply click the plus button. Show modal, that button element, click. Save both files to test. Add new now showing under the items menu, click, and the new item modal is opened, directly from the menu. With this action now being a menu item, we can also very easily assign a keyboard shortcut to it. Back to the new item, set the accelerator property to Command or Control plus O, the standard open command. Save. The item now automatically showing us in the menu that it has a keyboard shortcut. Press it, Command being on a Mac, O, and the new item modal is shown, same as clicking the button or the menu item. Allowing users to now quickly switch to the app, open the modal from the keyboard, paste a link and hit enter, all done without any mouse clicks and a much better experience for users inclined to do so. The next item command then being to open an item, or more specifically open the selected item. Keep in mind we can already navigate items with the keyboard, but at the moment we still have to double click to actually open them. Add that item with a label of read item, set the accelerator immediately this time, I'll make it Command or Control plus Enter with a click handler to call the open logic. I'll again call a global reference for this, window.openItem. Over to app.js, where we already have this logic available. Items.open does exactly what we want here. It opens the selected item. So what I'll do is create a global reference to that items.open function, assigning to window.openItem. Our global function reference that we're calling in the menu item equals items.open. Save all. I'll select the second item, Node.js. The new item with its shortcut key is in the menu. Click it this time, and the selected item is opened in a reader window. Close this without deleting it. Navigate to the first item with the keyboard. Open it with Command Enter, and same. Then our third item action, we can add the ability to manually delete an item without having to click the Done button in the reader window. Label this Delete Item. Shortcut can be Command or Control plus backspace, with a click handler calling window.deleteItem. Again, a global function reference that we can create in app.js. Reference items.delete globally. We again have this functionality in place, but we need to pass items.delete the index of the item to delete. So in this function, get the selected item with items.getSelectedItem. This returns an object with the selected item element and its index. We're only interested in the index, so immediately after, delete that selected item with items.delete, passing in the selected item index, selecteditem.index. Test this, save all files. I'll delete the second item, select it first, click that new menu item, delete item, and gone. I'll add back Electron with Command O, electronjs.org, enter, and that's added. So having all functionality accessible directly from the keyboard. We can now also add extended functionality to the app via this items menu. For example, let's allow the user to open an item in their default browser, instead of a reader window within the app. Just a bit of flexibility. Add a fourth item, open in browser. Make this shortcut a variation of this open command. I'll just add an extra modifier key, Command or Control, as before, plus Shift plus O. So the normal open command with the addition of also holding the Shift key. Calling on click, window.openItemNative. Create that function in app.js. Open item in native browser. Window.openItemNative equals items.openNative, which doesn't exist yet, so let's create that. Over to items.js, declare a new function export. Same description of open item in native browser. Open native equals a function in which we'll again want to make sure we have items before attempting to open one. Same as in the normal open function. If not this.storage.length, meaning we have no items, return. Else, having moved past this, get the currently selected item. Let selected item equal this.getSelectedItem. Opening that item in the default browser using the shell module. Shell.openExternal. We need the URL of the selected item, so selecteditem.node, being the selected DOM element, dataset.url, that URL data attribute with the item's URL. Include the shell module also, const shell from Electron. Save all. I'll bring that browser window from earlier over into view again. Select the second item to open in my default browser. Click that new item, open in browser, and a new Chrome tab is opened with the Electron JS item URL loaded. Exactly the same as in our own reader window, with the exception of being able to mark the item as done. Again, just allowing the user some choice over how they use the app. Then finally, there's one last function of the app that we're still not able to access via the keyboard, that being the search field. The default command to enter a search is Command S on Mac, or Control S on Windows and Linux. So let's add that as the final items menu item. Label, search items, shortcut as mentioned being Command or Control plus S, and a click handler calling window.searchItems. Over to app.js to create that. Focus to search items, assigning to window.searchItems a function in which we'll focus the search input. Search, the selector here, focus. Save both files, Command S, and the focus is in the search, meaning I can just type. Add a new item with Command O, google.com. Search again. G, leaving us with both Google and GitHub. Add an O, and GitHub no longer matches, with only the Google item remaining. Clear that. Navigate to the last item using the keyboard, Command Enter, and it's opened, at which point, once the user is done with it, simply click Done. And it's closed and deleted. So that's our app done. Of course, there's going to be a lot of possible improvements and possibly some bugs, but for the most part, it's an extremely well integrated desktop app, regardless of the operating system. So in the next section of the course, we'll prepare this project for distribution and compile it using Electron Builder. Please note that whilst the API and project sections of this course have been updated for Electron version 5, the preceding section on app distribution is still in progress. That said, everything shown is still valid and applicable to the new project. You will, however, need to first add some app icons to the app, as that part of the project is now moving to the new distribution section. This update will be live in the next few weeks, so be sure to check for the announcement email I'll be sending out at such time. In this new section of the course, we are going to cover packaging and distributing our Electron app, but more so focus on creating an efficient way to release app updates to users. Previously, in the project section, we built a simple app and then packaged it using Electron Packager. But now, for a more robust and feature-rich solution, we'll see how to use the more popular Electron Builder along with auto updates. If you're at all familiar with the concept of publishing application updates outside of the official Windows and Mac app stores, you'll know that this often involves the need for a dedicated application update server. This can often be a bit of an unwanted complexity to configure and maintain, so in the upcoming lessons then, I'll show you how to achieve the same functionality provided by a dedicated update server using only GitHub releases together with the Electron Builder and Electron Updater modules. We'll also look at packaging our app into various formats, code signing it to have the end user's machine trust it, and finally integrate all the update logic into our Read It project app from the last section in this course. The first aspect of application distribution is our build process, and as mentioned, we'll be using the Electron Builder module for this. So first off, why Electron Builder? Well, in the previous lesson, we packaged our app using Electron Packager, which might be a simpler solution in many ways, but as the name suggests, Electron Builder is a much more fully featured tool and allows us to package, sign, and release our app as part of a highly configurable workflow. The main takeaway being the ability to publish or release new versions of our app automatically. Over to my editor, and here we have the Read It app in its final state from the previous lesson, including that Electron Packager build. This is linked in the resources should you want to download it now to follow along. I'll get rid of that previous build. Over to my terminal, where we're already in this app directory, rm rf readit darwin 64, that previous build. clear this. And of course, the very first step is going to be installing the Electron Builder module. Now, in order to have access to the command line tools, I'm going to install this globally. npm I with a G flag, Electron Builder. Wait for that to complete. All done, so go ahead and test that. Electron Builder with a help flag. And there we have it. Of course, having any global dependencies for a project isn't ideal. So as we go, we'll add the required build commands to our package.json file as npm run scripts, meaning we'll be able to use the module locally as a project dependency instead. To do that, I'll add it now as a project dependency, but important, we don't need Electron Builder bundled into the final package, so be sure to install it as a dev dependency. npm I Electron Builder save dev. All done. Check that in package.json. There we have it. Meaning, as long as we run any build commands as npm run scripts, this local module will be used. Just a better practice for development. If you're not sure what I mean with npm run scripts right now, bear with me and it will all make sense in a minute. Okay, let's try building our app as it is right now. In the docs, head over to the command line interface section, and here we see a few commands we can run. This build command being the one we'll use 99% of the time. We can also see down here some command line flags to further specify what exactly we want built. This is all universal across Mac and Windows, but whilst we can build for Windows, Mac and Linux on Mac, we can only build for Windows and Linux on Windows. Important to take note. Seeing as I'm demonstrating this from a Mac then, let's see how to build this for Mac as a zip file. Over to the terminal, in the project root, run Electron Builder build, passing a Mac flag, or shorthand like so, M, with the target being zip only. Enter. We see application icon not set, which we'll fix in a minute, and app is not signed, the topic of the next lesson. Fast forward through this a bit. Done. If I list the contents of this project, we see a new directory here, dist, or distribution. And inside, read it, version 1.0.0, Mac zip, which is the target we built. You'll also have this platform-specific directory after each build, this simply being the unpacked app. You can just ignore it. It's there in order to inspect the built app without digging into the target files. We can test this new build. I have the project open here, so navigate to that dist directory, extract the zip file, there we have it, albeit without our app icon, but we expected that as per the warning during the build. And it works. Now, as I mentioned, in order to simplify these individual build commands and make use of the bundled Electron Builder module instead of the global one, we can create npm run scripts for the command. The default development command being start. Make that Electron in the current directory. So just launching the app using the pre-built Electron module. Then, as per this last build we performed, add a Mac-only build command. I'll call this Mac, mapping to Electron Builder, Mac, or just an M flag. Remember, from the documentation, the build command is the default, so we don't have to include it. Okay, then for the remainder of our actual build configuration, the first point we have to address is the app icon. We can navigate to this icons section, where it states that any build resources, such as icons, needs to be placed in a directory called build. Meaning in our app's root, we can simply create a new directory called build and copy these app icons into it. Or alternatively, if we follow this build link, we see the options to simply specify a location of the build resources in the Electron Builder configuration. To specify configuration parameters for Electron Builder then, we can simply add a build property to our package.json file. This being an object which will contain individual Electron Builder options. For example, our app ID, commonly written in reverse domain notation. I'll make mine com.stackacademy.readit. And for that build directory, add the directories key, setting build resources to the current directory, the project root, as this is where we have those icons. We can also set platform-specific options here. For example, on the Mac property, any Mac-specific options. Navigate to this Mac configuration link, options such as the app category, the build targets, and even app entitlements for App Store submissions. I'll set a couple of these to demonstrate. Create a configuration for Mac builds, setting the app category to public.appCategory productivity. Each vendor having their own specifications for app categories, which you can also find links to in the Electron Builder docs. Then, to specify a specific build target for Mac, let's say a DMG or disk image, set target to DMG. Test all this with the npm mac command, npm run mac. We of course still get that code signing warning, but nothing relating to the app icons this time, with confirmation of only the DMG target being built here. Fast forward through this a bit, and done. In the distribution directory, we have that DMG only, as per the target option in our build configuration. Mount this, and there we have the app icon working as expected also. Again, as a result of configuring the build resources directory in package.json. We can do the same for Linux and Windows. Here, Linux having a few less options, but we can set the category still, with a link to all the available categories here. So in the build configuration then, I'll add a Windows property as well, and Linux, with that category setting it to network. Then a couple more npm scripts, add one for a Windows-only build, Electron Builder W, and to build a complete set for Mac, Windows, and Linux, Electron Builder MWL, Mac, Windows, Linux. An important note here, if you're following along on Mac, you can build for Windows, but if you're on Windows, you won't be able to build for Mac. There is a few third-party solutions for performing your Mac builds remotely, AppVeyor being the most popular, to which I've linked in the lesson resources. Okay, that pretty much sums up how the Electron Builder configuration works. But one last very important point to remember before we move on to releases is the Electron Builder versioning. Your app release version will be taken from this global version in the package.json file, meaning the last build we did was version 1. If, however, I update this version to 1.1.0, run a build for all platforms, and at this point, if you've never run this before, you might see Electron Builder download additional binaries. I'll fast forward again, all done, check in the distribution directory, and there we have it, version 1.1.0 of the Read It app for each Mac, Windows, and Linux. In the next lesson, we'll look at code signing and readying our app for release. Now that we've seen how to configure Electron Builder in our package.json file, let's address code signing our app. Now, you might be wondering whether this is really important, and the answer is absolutely. An unsigned application will not only be flagged by the operating system during installation, but the auto-updater module that we'll implement later on won't work at all. So this is essential. Again, Electron Builder makes this fairly straightforward. Before we continue, however, note that for the purposes of this lesson, I'll be using self-signed certificates. This is perfectly fine for developing, but in a real-world app, you'll want to get an official certificate from both Apple and an authorized certificate authority for Windows. I'll have the relevant links in the resources of this lesson. Okay, in the Electron Builder documentation, navigate to Code Signing here, where we can find some information on getting our app signed. These environment variables being one way to specify the certificate name, password, etc. We'll be using the package.json configuration again, but first we'll need to generate some certificates for testing. I'll start with Mac, and what we're looking for on Mac specifically is a code signing certificate. If you're enrolled in Apple's developer program, you might very well already have this installed on your machine and your app will be signed automatically. But for those who don't, go ahead and open the keychain access. Then, in the top menu, navigate to Certificate Assistant and select Create a Certificate. In the name field, set the certificate name. I'll just make it Read It, but if you're going to use this for multiple apps, a more generic name will do. Leave the identity type as self-signed root, and most important, set the certificate type to code signing. Create, confirm, and now you should be able to find this new certificate in the keychain by searching for that name you gave it, making sure you have all items or certificates selected here. There it is, Read It Certificate. Right-click that and Get Info. Expand this Trust section, changing the very first setting here to Always Trust. This is just in order to develop with this certificate as if it was an actual Apple certificate. You'll need to enter your user password to allow this change. And there we have it, all done for Mac. We'll do the same for Windows in a minute, but first let's test this. Over to the terminal, so when we build this now for Mac, the warning should no longer occur. Clear, run the Mac build, npm run Mac. We get this new message, signing up, and another password prompt. So enter that. I'll just say always allow to avoid having to enter this each time. Building the DMG. I'll fast forward a bit. Done. No warnings and this confirmation of the app being signed, meaning Electron Builder automatically found a valid code signing certificate in the Mac keychain and used it. With that working, we can also get rid of this target configuration as we'll want to build the default target for releases later on. Next then, we want to tackle the Windows build from Mac. We'll do the same on Windows in a minute as well, but the configuration stays exactly the same, so I'll demonstrate on Mac first. The documentation provides a good description of certificate options for Windows, but the main takeaway here is that unlike Mac, these certificates are more generic and will therefore not be auto-detectable by Electron Builder, meaning we'll have to tell the Electron Builder configuration where to look for the certificate. Navigate to the Windows section, and the setting we're looking for here is the certificate file. You'll notice here that Electron Builder prefers the use of an environment variable to specify the certificate location for Windows, but I'm going to stick to setting it in the package.json file. Feel free to choose whichever. Before we specify the location of the Windows certificate, however, we need to generate it. On Mac, this is as easy as exporting the Mac certificate for Windows. Back to Keychain Assistant, with the search still in place, switch to the Certificates tab. This changes the view state, allowing us to export the certificate. Right-click it, export, and this P12 format is the one we want to use. I'll name this Read It again. And at this point, you'll be prompted to create a certificate password. This is completely optional, however, and I'll just leave it blank, so not using a password. Enter your user password if prompted. And there we have it, a code signing certificate, or P12, for signing Windows apps. Move that into the project. And seeing as we'll be committing this app code to GitHub in the next lesson, we want to make sure the certificate doesn't end up in GitHub, especially if you're going to be using a public repo. To keep this private then, I'll create a new directory, call it private, and drop that certificate into it. Switch to the editor and create a new file, .gitignore, so to specify any files that Git should ignore and not include in the app source, I'll add .dsstore, which is Mac specific, all of our project's node modules, don't want those in the repo, the dist directory, again, no need to have compiled versions of the app in the repo, and of course private, that new directory. Save this, head over to package.json. We now have the certificate, so in the Windows configuration, set certificate file to private/readit.p12. Now, if you recall from when we created the Mac certificate, we had to manually set it to be trusted. Likewise then, as this is also a self-signed certificate, we have to set verify update code signature false. You can remove this setting or change it to true as soon as you have a valid certificate, but it is required for development when using a self-signed certificate. We can test this, perform a Windows build, npm run win. Password is not set, so an empty password is being used, which is fine. And then signing readit.exe. So our code signing is working for Windows also. I'll clear this distribution directory again. And now let's see how to generate a self-signed certificate on Windows. In the docs under command line interface, we see this create self-signed certificate command, which is what we'll use to generate the certificate on Windows. I'll copy that, add it to npm for convenience, make cert, also meaning again we don't have to have Electron Builder installed globally. Electron Builder create self-signed cert. Head over to Windows. I simply have my readit project shared to this Windows instance as drive Y, which I'll change to. So this being the exact same project I've been demonstrating with on Mac, that npm make cert command is ready to use. Enter missing argument publisher, this being a publisher name for the certificate being created. I'll add that to the command in package.json, a p flag, setting mine to Stack Academy. And also very importantly, in the Windows configuration, specify the expected publisher name to match that. Try again. This time we get a password prompt like on Mac. I'll leave it without a password again. Yes. And done, despite this error. This is nothing to worry about and simply refers to the operating system's inability to store the generated password. If you check your project directory, the certificate is there. stackacademy.pfx, which I'll move into that private directory also. Update the certificate file location to use that newly generated certificate. Run the Windows build to test. Signing readit.exe. So working as expected. Forward through this. Done. Both the app and the uninstaller being signed successfully. I'll install this. And it works without any issue. Try the uninstaller also. Settings. Uninstall. Yes. Done. In the next lesson, we'll set up a GitHub repo and configure the first release. Having configured Electron Builder to package our app and sign it for both Windows and Mac, we're finally ready to create a release version and publish it. For the purposes of this lesson, I'll be using GitHub to publish releases, as this is not only the default for Electron Builder, but also the easiest to get started with. Should you wish to use another provider, Electron Builder has built-in support for Bintray, a more traditional update server like Hazel, or even Amazon S3, all documented in the Publish section. You can even choose to publish your releases to multiple platforms like this. We'll of course just be setting this to GitHub in a minute. First though, let's create a repo on GitHub to host our app releases. If you don't have a GitHub account, now is probably as good a time as any to create one. I'm logged into my Stack Academy organization account here, so click New. I'll call my repo Readit and leave it as public. Now, of course, not everyone will want their app or their app releases to be public, and that's fine. Electron Builder supports private repos as well, but for now that's not really relevant. When we move on to the Updater module, I'll link to how you can configure your app to pull from a private repo. If you're not concerned with having your releases be public, but don't want to commit your app code to a public repo, then simply ignore your app code in gitignore, keeping only something like your README file in this repo. Choice is yours. Okay, I'll create this. Copy this remote address to add to the project. Then, in the app's root directory, initialize this as a Git repository with git init. We already have a gitignore file from the previous lesson, ignoring our dependencies, distribution directory, and that private directory with our certificate files. This being where you can now choose to also ignore your app code should you wish to not have it in the public repo. I'll just add everything. There, already. Add that GitHub repo as the origin remote from the command we copied. Commit the project as initial commit or init. And push it all to the origin remote onto the master branch. If you're not very familiar with Git or GitHub, just follow along with this as you won't be needing to do much more in terms of Git commands once this is set up. Right, all the app code should now be ready on GitHub. Refresh this, and there we have it, minus all the ignored directories. Next, we can create our first release. Navigate to the Releases tab here, and what this basically means is that we can create a release version of our app. For example, version 1 or 1.2, etc. And each time we create a new release, Electron Builder will check for that release and automatically upload the matching build targets to GitHub. This being why we ignored the distribution directory in our app. Electron Builder takes care of uploading those files with the correct naming conventions, etc. The reason we still need our project to be initialized as a Git repo then is that Electron Builder will check the project for the GitHub credentials, that way knowing where to upload the releases to. So all very automated and easy to use. I'll go ahead and create a new release, and the first thing we'll have to enter here is the tag version, this being the version of the app we're planning to release. The naming of this is important, so the format you want to use is small letter V for version, and then a 3-dot version. For now, version 1.00. Give this release a name, anything will do here, first release, and in the description, list what this release fixes, changes, etc., ideally in bullet point form. This again not being essential, but you will be able to display this to the user when your app updates. Then, don't publish this yet, simply save it as a draft. We don't want this published until we have it all done with the latest releases attached. We're nearly ready to publish to this new release, but first we have to provide Electron Builder with permissions to do so. What we need then is a reusable GitHub access token. To create one, navigate to your profile settings, developer settings, personal access tokens. I have a few already, but go ahead and generate a new token. GitHub password is required. Name this token, read it Electron Builder, something descriptive so you can remember what this is for, and very importantly, give this token repo permissions. Generate, and there we have it. We won't be able to see this token again for security reasons, so make 100% sure you copy it. What I'm going to do is simply write it to a text file in that private directory, as that's not part of our repo and won't be compromised. You can of course store this anywhere you like a password manager, etc. Echo my token to private gh_token.txt. The reason I named this gh_token is that that's the environment variable on which we'll have to set this token when publishing our app, so it just matches. Check that worked. There. We have the first release ready in draft mode also, and we should now be able to publish version 1 as per that draft release tag name. We still have to assign the provider to which we want to publish. In package.json on each of those platforms, set publish to an array with GitHub as the only provider. In order to tell Electron to both build and publish our app then, we'll use one of those build commands, adding only the publish flag, or P, giving that one of these values. On tag, meaning only publish the build if we're also pushing a new git tag. On tag or draft, which is what we'll do seeing as we have a draft release ready on GitHub. Always, simply meaning publish this build regardless, or never, which is simply don't publish. Clear this. Remember we have to provide our GitHub access token to Electron Builder, so copy that from the file in the private directory, setting the gh_token environment variable to that key, followed by the build and publish command. We don't have this as an npm run script yet, so I'll call Electron Builder build, which is the default anyway, for Mac. Of course, you can publish Mac, Windows, and Linux all in one go, but we'll do that later on. Just Mac for now will be a good demo. P for publish, setting that to on tag or draft, as we saw in the docs. Our draft release is tagged as version 1.0.0 though, so change the app to match that, this being our first release after all, and enter. Electron Builder goes through all the usual steps of building and signing, And finally, after an often lengthy upload to GitHub, which we'll skip through now, has all those new builds published to GitHub. This includes a DMG, a zip file with the Read It Mac app, and this latest mac.json file, which is what the app will check on GitHub to find new releases when we implement auto-updating later on. There's also 2 more files, but as you can see from this here, the Electron Builder upload process often gets a bit messy. Nothing to worry about, it's just the output. Back on GitHub then, navigate to Releases, and there we have it. Latest Mac in both JSON and YAML format, a block map file for this DMG, the DMG itself, and the Mac zip package, which is what the auto updater will actually use to update the app with. If for whatever reason you don't want Electron Builder to handle this upload process, you could have also uploaded these files manually on the release, but it's very important to check the build packages match the locations in these latest files, should you choose to upload them manually. The last thing left to do now is publish this release. Click Publish here. Done. This now being our latest release. Before we move on, there's a couple of minor technicalities to understand, or at least to be aware of, regarding this publishing process. In the dist directory, where we have the published builds, inspect the latest Mac YAML file. I mentioned that if you choose to upload your builds manually, you'll have to ensure the build names match the ones in this file. And here you can see that. Read it 1.0.0 Mac zip, which is exactly as we have it here. So this will be fine to upload manually as is, but this isn't always the case, in particular when building for Windows on Mac. So it's just best to be aware of where all this is and how to check it. The final important file to be aware of is the app update YAML file, which is built into the app files. This is hidden away a bit, but for Mac we can find it in Read It app, contents, resources, appupdate.yaml. This is auto-generated if your app is initialized as a Git repo and contains a remote source. But again, just be aware of where it is and that it is significant, as the auto-updater module that we'll cover in the next lesson will check this to know where to find new releases. In this lesson, we're finally going to start adding some code to our app in order to check for and apply any available updates from our GitHub releases. Before we start, however, it's important to have an understanding of the module we're going to use to achieve this. So, as you might have noticed from the Electron documentation, the Electron framework actually includes an auto-updater module already, but we're not going to use this one. Instead, we'll use the similarly named auto-updater that comes with the Electron updater module. The Electron Builder docs lists a number of reasons this is preferred over the built-in auto-updater, and they're all pretty significant. But the number one reason is that there's no need for a separate update server. Eliminating the need to configure and run a dedicated update server is a really big improvement, and for this reason, using the Electron Updater's auto-updater module is far superior. Let's implement this then. I'm going to be adding all the logic to a new local module called Updater, just to keep things nice and tidy here. So add a require for that module, which we'll create in a second. Const updater equals require locally updater. This module will export a single method to check for updates. So in the app ready event, move create window into the callback, which still creates the main window as before, and then check for any updates after a short delay. So set a timeout calling updater, that module will create to handle our updates, .check. I'll just make this 2 seconds. Okay, create the updater module, new file, updater.js. And the very first thing we're going to need here is the auto updater from the Electron updater module. Const, using destructured assignment, assign auto updater from the Electron updater module. This auto updater being bundled in Electron updater. We can go ahead and install that, this being a dependency for our app, so npm I save Electron Updater. That's done. So back in our Updater module, define the exported check method that we're calling in main.js 2 seconds into the app being ready. Exports.check equals a function. We can test this with a log message, checking for updates, save, and launch the app with npm start. Switch back to the console, and there we have it. So the app launches, and 2 seconds after being ready, the Updater module's check method is called. I'll kill this, get rid of this log message, and now in this check method we can implement the app update logic using the Auto Updater module. If we scroll down here in the docs, we see the Auto Updater provides a few methods, the most important being this check for updates, all events. This includes the update availability status, errors, and even in the event of a new update being downloaded, the download progress. I mentioned previously that this module will only work with signed apps, which means that building and running the app is required. So we don't have access to the terminal for debugging, making it a bit more difficult. But luckily, this module does provide us with a good alternative, which is logging to a file. So let's enable this before we start implementing the module code. Back at the top here, we have a 2-line implementation. And as you can see, the built-in logging is done via the very popular Electron log module. So in updater.js, enable logging on the Auto Updater module as per the example. Auto Updater logger equals require Electron log. Install that module. This could be a dev dependency or a production dependency, depending on whether you leave logging enabled in your final build. That's done. Set this logger to log at the info level, which is basically for debugging, meaning log all events. Then, back in the check function, start an update check, meaning a new release on GitHub, by calling autoupdater.check for updates. This will also automatically log the status of that check to our log, which we can monitor by reading the log file. The location of this log file will vary depending on your operating system. So in the Electron log documentation, we have a list of default paths for the log file: Linux, Mac, and Windows. Being on Mac, I'll watch this path, tail, so the last piece of this log file, with an F flag, meaning keep this file open. Library, logs, read it, log.log. And you see that stays open. Build the app with that new update code in order to be able to test it. I'll extract the zipped app, launch it, and in the terminal we see that file has already been written to, checking for update, with a moment later logging update for version 1 not available, this being as it's the same version as the app we're running right now. If however I rebuild this app now to be a lower version than the one we have on GitHub, first release, it should recognize the update as a newer version. I'll make this 0.9, build it again, fast forward, extract and launch this. We see the checking log, and a moment later found version 1, which by default then also starts downloading. In the next lesson we'll handle this download and update manually, and implement the user interface within the app. In the last lesson we finished by having our app check for and automatically start downloading the new release. But whilst having this run in the background works fine, we don't necessarily want to just go ahead and update the app without the user's consent. So in this lesson then we'll implement a basic interface to notify and prompt the user of any available updates, visually track the download progress of the new release, and finally prompt the user to install the downloaded update by quitting the app. I'm going to remove this last build, head back to the docs, and of course, in order to be able to prompt the user on whether they want the available update to be downloaded, we first have to stop the update from automatically downloading once it's found, as is the case at the moment. To do this, we can set the auto updater's auto download property to false. Back to updater.js. Right after enabling logging, I'll say auto updater.auto download equals false. Then in our check method, we still check for updates, but also listen for the update available event, meaning GitHub does contain a release with a newer version than the user's. Auto updater on update available, at which point we can prompt the user to check whether they want the update. I'm going to use a standard Electron dialog to do this. So include the dialog module from Electron, const dialog equals require Electron, showing a message box dialog, this being the one with multiple button options. Make its type info. The dialog title can be update available, and the message, a new version of Reddit is available. Do you want to update now? We also need two buttons, yes and no. Pass this an array, making the first button at index 0 update, and the second, index 1, no. Then, as the second argument of the show message box, pass a callback in which to handle the button click, this callback providing the button index the user selected. Check for this button index being 0, meaning update, else simply return and do nothing. If button index is not equal to 0, return. Otherwise, meaning we've passed the if statement and the button clicked was indeed update, start the download and show the user the download progress in a new window. To start the download then, we can call download update and immediately also start listening for the download progress. Auto updater on download progress, pass a callback with a single argument, make this D, containing all the download progress information, and in this listener's callback, I'll assign the download percentage to a value called download progress, which we'll define in a moment, d.percent, as per the docs. Define the download progress variable in the scope of the update available callback. We could have made this global also, but we simply needed to track the overall progress in order to present it to the client once the download starts, giving that an initial value of 0. We can test this by manually logging the download progress to a file, autoupdater.logger, calling info with the downloaded percentage. Rebuild the app. I'll just do Mac again. Fast forward. Extract the zip and launch the app. I'll immediately switch over to the terminal where we can observe the logger, checking for update, version 1 found, and this time we see that app icon being bounced in the dock as a result of the dialog. There we have it. I'll say update, starting the download, check the log again, where we see the download percentage being logged. I'll stop this, clean up these builds again, and head back to the code where we can now use this download percentage to display a progress bar to the user. We'll do this using a small browser window, so define that, let progress win, or progress window, equal a new browser window, which we'll need to require from Electron. We want this window to house only a simple progress bar, so we can keep it relatively small. Width 350, height 35, use content size, I'll set to true, so expanding for our content. Hide the menu bar on Windows. Mac won't show one as we're not directly adding it to this window. Remove the ability to maximize this window. No full screen, or the ability to make it full screen. and finally have its sized fixed, so no resizing. Next, we can load the HTML contents for this progress window. progressWin.loadURL, file, the current directory, /renderer, where we have all the other renderer files, progress.html, which we'll create in a second. And of course, handle this window's close event by unsetting it from the progress window variable. progressWin on closed, set progressWin equal to null. Create progress.html in the renderer directory, this being the HTML for the progress window. So with a snippet, I'll add a basic HTML5 structure, set the title to downloading read it update, and the only thing we're going to want displayed in this window's content is a progress bar. To do this then, we can very conveniently use a native HTML5 progress element. I'll add that, leave the default value at 0, being the current value of the progress bar, and the max at 100. Get rid of this text. We also have to make sure this spans the entire 350 pixels width of this window, so add an inline style attribute, setting width 100%. This being all the HTML we need in this window, we do still need a way of updating the progress element's value as the download progresses. Of course, the progress percentage is being tracked on the main process. So what we'll need then is IPC messaging to get the value from the main process, and a line or two of jQuery to update the value in the HTML. Add a script tag, require the IPC renderer module from Electron, const IPC renderer, using destructured assignment again, equals require Electron. And then with that IPC renderer module, message the main process every second to have the progress returned. If you're a bit hazy on how the IPC modules work, I'd suggest rewatching that section of the course. But basically, the reason we're sending the IPC message from the renderer and not from main.js is that it's easier to respond to a renderer than it is to message a renderer directly. Set an interval of 1 second, in which we'll send a synchronous message to the main process, IPC renderer.sendSync, and I'll call this channel download progress request. We're using a synchronous message here as there's really nothing to block on this renderer, and using sendSync makes it very easy to get a response as the return value. Set the return to progress. We'll implement this response in main.js in a second, but assuming this all goes well and progress contains a percentage, we can use jQuery to set it on the progress element. We still need to require jQuery, $equals, require jQuery. Selecting the progress element, no need to be specific, we only have the one, and setting its value to progress. I'll add a couple comments for good practice. Copy this IPC channel name so we can add it to the listener on the main process. Back to updater.js, where we also need to require the IPC module. IPC main this time though. And again, inside this dialog's callback scope, listen for messages on that progress request channel. IPC main on download progress request, that channel name we just copied. Pass a callback, not forgetting the event argument as we'll need this to set the return value, the message event, dot return value equals download progress, that variable we're assigning the download percentage to. Given there's no errors, this should be all we need to pass the percentage to progressWin then, where it will get set on the progress element. The final part of the update process then is handling the download being complete, meaning the app has to be closed for the update to be installed, which is taken care of by the auto updater module automatically, and then relaunched. Now, as with downloading the update, we can't just quit the app without the user's consent, so we'll need to ask again. First, listen for the download completed event, auto updater on, update downloaded, pass a callback, and the very first thing we have to do before prompting the user is close the progress window as the download is done. Check it actually exists, as the user might have closed it manually. If progress win dot close. Then a dialog to prompt the user to quit and install. We'll use a message box as before. Dialog.show message box. Type info. Title can be update ready with a longer description as the message. A new version of Read It is ready. Quit and install now. Add two buttons again. Yes, meaning quit the app and install the update, and later, as the update will still be installed once the user eventually closes the app. Pass the callback to this dialog with the button index, in which we can check yes was selected. If button index equals 0, call autoupdater.quit and install, this being the method that will quit the app, install the update, and relaunch the app automatically. That's essentially all we need, and this is ready to test. Of course, it's quite a bit of code, so be sure to download the final version from the lesson resources and take another look over it. I'll switch to my terminal to rebuild this, npm run mac, as I only need a build to demonstrate with. We're building version 0.9 again, so the version 1 release on GitHub will be used. Fast forward, extract the zip file and get the app from the zip target. Launch. 2 seconds later, we're prompted as an update was found. No, we'll just dismiss this entire process now, but I'll say update. We get the small progress window with that progress bar, and moments later the progress starts increasing as this window is communicating with the main process via IPC. I'll speed this download up a bit. The download completes, we get the dialog prompting us to quit and install, and I'll say later, keeping the app open with the downloaded release ready to take over the next time the app launches. We also have that log file with confirmation of all the update events up until the point of this download being ready. I intentionally skipped this final step in the update, as in the next and final lesson, we'll introduce a small flaw and build it as version 1. Then we'll go through the entire process of fixing the app and publishing it as version 1.1, with which we can update version 1 on both Mac and Windows then. In this final lesson, we'll take everything we've built in this section of the course, build and install version 1 of our app, and then release an update to version 1.1. So in essence, this is more of a practical walkthrough of what a typical production app's release cycle would look like. I've removed the old distribution directory, so let's build version 1. In package.json, change this to be version 1.0.0. And only to make the update more obvious, I'll introduce a visual change in the app which we can fix in the update. Open main.html and change the background color of the add button, the plus, to be red. Style, background, red. Save this and build the app for all platforms. npm run build. I'll forward through this as it might take a couple of minutes. Done. We have Mac, Linux, and Windows. Over to the dist directory. Extract the zip file with the Mac app. I'll move this to my desktop. Launch it, and there we have it with that red button. Move over to Windows. I'll run the Windows installer straight from dist. Done. So we now have version 1 installed on both Mac and Windows, ready for an update to fix that button color. Clear this build. Back to package.json. This will be a minor update, so version 1.1.0. And remove the background color in main.html, which is going to be the most obvious result of the update having worked. Now, before we build this, as this build will include a publish also, we have to create that release draft on GitHub. draft a new release, version 1.1.0. I'll just call this read it 1.1. And in the changelog or description, record that single fix to the UI. Fixes, add button background color. Save this as a draft. And there we have it, ready to publish to. If, like me, you have your app code in GitHub as well, now would be the time to commit your code, as the release automatically tags your latest commit. Add all. Commit as adds auto updating. And push. Clear this. We are now ready to build and publish our app. So get the GitHub access token from that file in the private directory, cat private gh_token, copy that, set the gh_token environment variable to that token, and execute npm run publish. Depending on your internet speed, this might take a very long time, so I'm again going to fast forward the uploads. As I've mentioned before, don't worry too much if this console output gets a bit confused. It's perfectly fine as long as it's running and not throwing any errors. Head back to GitHub and refresh this page. All there. We have our latest files to tell the updater which build to download, and builds for each platform with the correct file names. So the entire publish dealt with perfectly by Electron Builder. Edit this release. Publish, meaning we're ready to update. I'll do Mac first. Launch the app. 2 seconds later, we have the prompt, update. Speed through this download, and might as well close this. Do you want to quit and install, meaning the app should relaunch as version 1.1 and be back to the green button? Say yes, and almost immediately the app relaunches with the correct button color. Confirm the version from the About menu, 1.1. We can do the same on Windows. Launch. Update, this time with that native Windows dialog. This is also a separate browser window despite its flush appearance. Fast forward. Quit and install now. Yes. The app reinstalls itself. And update it. So seamless updates for your users without any extra update service or additional overhead. And really a must-have feature for any app. With the release of Mac's unique touch bar, Electron added support for this feature. And in this new section of the course, we'll cover the Electron touch bar API, looking at some different layout options and user interaction. This is of course Mac specific, so please keep in mind that if you're developing for Windows or Linux also, you'll have to use a platform condition as we saw in previous lessons. To demonstrate the touch bar, I'll be using this on-screen simulator. This is great not only for testing, but will also allow you to develop for the touch bar without actually having this feature on your machine. I've linked to it in the resources should you want to download it now to follow along. This of course hooking into the actual touch bar implementation of the operating system, so what you see here is what you'll get in your app. We have the native controls, brightness, expose, media, and volume, all behaving perfectly, including those multi-touch gestures, such as dragging the volume. And again, the simulator being native, you can also use it with other apps. I'll focus a text editor window, and immediately we get the autocomplete suggestions pop up. Right, I'll get rid of this, head over to my editor, and what we have here is essentially the same quick start project as in previous lessons, but an updated version. Not much has changed except there's some better path handling for loading index.html. I have the project start code linked in the resources, or alternatively you can clone the repo directly, also linked in the resources. I'll clean this up to my liking a bit, change this modules require to be destructured, app, and browser window. Get rid of these. I'll save this, test the app, run Electron in the current directory, and our app loads. Nothing new here, and of course right now that touch bar is empty with only the native elements visible. So let's start by adding a basic touch bar to this app. The touch bar API consists of a main module, touch bar, and then several sub-modules for different touch bar components. We'll cover a selection of these in this section. Require that main touch bar module from Electron. And the way this is going to work is we'll create a touch bar instance from this main module, which will then populate with components from the sub-modules. Assign our new touch bar to a constant, touch bar, new touch bar, and to populate this new touch bar, we'll pass it an array of components as its first and only argument. Add a new component to this array. I'll just demonstrate with a simple label, new touch bar, so that main module dot touch bar label being the label component module that we're accessing directly off this touch bar module. And to configure this, pass it an object with a label property of Electron touch bar. That's our touch bar created and containing a single label component, but we still have to add it to our app. To do this, we'll add it to the main window once main window has been created in this create window function. Main window dot set touch bar, passing it that new touch bar instance. Save this, launch the app, and we see that label in the touch bar. So very simple, but working. Our app now implements its own touch bar with a label. Back to the code, where before we move on to adding more components, we can improve this a bit by requiring these submodules separately. Add a new section for touch bar modules, and require from that main touch bar module the touch bar label that we're using at the moment, and a new component, touch bar button. I'll create a button, call it TB button, new touch bar button, give it a label property of update, we'll see why in a minute, and a green background color. We can also refactor this label to be assigned to a constant. I'll cut this, add that button whilst we're at it, assign this label to a constant of TB label, new, and add that to the touch bar array also. We can test this again, save, relaunch the app, and there we have it, our new green update button. This doesn't do anything at the moment though, so let's change that and implement a simple bit of logic to reload our app for us by means of the touch bar, instead of doing it manually via the command line each time. I'll remove that background color, so just have it as a default button, but give it an icon. I'll add the icon image to the project, again linked in the resources. And notice that this icon's name ends in @2by or @2x. Telling macOS to render this as half its size, or as a retina image. Specify the path to the icon file, using the path helper again, path.join, the current directory, and the name of the file, reload @2x.png. And then for the logic part of this button, give it a click property, which takes a function to execute when this button is clicked. In which case we'll simply want to relaunch our app. App.relaunch, which will spawn this same process, so also immediately kill the running instance before it gets recreated, with app.exit, and a status code of 0. Save all that, and restart the app manually for the last time, as we should be able to do it from the touch bar now. We get the new button, but notice that the default style for button icons is overlay, meaning centered, like these native buttons. But that obviously doesn't work with a label. So what we want to do is specify this icon's position as being to the left. Icon position, left. Save. The update button should work to reload the app now, so click that. And the app reloads successfully with that new icon position. The final component we'll look at in this intro lesson is the touchbar spacer. Notice how this label and the button is quite close together. Well, spacers allow us to do just that, space elements apart. Let's add a spacer between this label and the button. Create that spacer component, const tb spacer equals, include the module, touchbar spacer, setting tb spacer to new touchbar spacer. Add the spacer between tb label and tb button. Reload again. And we have a small space between these two elements. Small being the default size of touchbar spacers, but we can easily make this a large spacer by giving it a size property. Set that to large, save, reload, and the space increases. Or, lastly, make this a flexible spacer, meaning take up as much space as is available. Size, flexible, reload, and the update button goes all the way over to the right, with that spacer taking up all the available space between these two elements. That wraps up this first lesson on touchbar basics, and as you can see, Electron makes it really easy to work with the Mac touchbar. In the next lesson, we'll see some more advanced components and layouts. In the previous lesson, we added this convenient update button to reload our app via the touchbar, but we only used 3 of the most basic touchbar components: a label, a button, and a size adjustable spacer, which we have as flexible right now. Next then, let's implement some of the more advanced components and layouts that the touchbar API has to offer, which will then tie together in the third and final lesson to actually hook into our app. The first component we'll look at is the color picker. I'll begin by changing this label to be theme, so a simple label next to the color picker, and create the color picker component. Assign it to tbPicker, require the color picker module from the touchbar module, touchbar color picker, and create that new picker with new touchbar color picker. This component does provide some optional parameters, but I leave it in its default state for now. Add it to the main Windows touchbar next to the theme label, save, hit update on the touchbar, and we see that color picker button. This being a popover component, which we'll see how to implement in a minute, we can click it and the entire picker gets revealed in its own separate touchbar instance, allowing for various clever color selections. We'll see how to access these color selections in the next lesson. Next, let's try the slider, this being similar to the volume and brightness controls when dragged. Const tb slider, which will make a new instance of, include that also, touchbar slider, passing it an object with some configuration parameters, label, size, a minimum value being the numeric start value of the slider's range, and max value, the maximum value of the slider all the way to the right. Add that next to the color picker, and I'll space these two components apart slightly with a large spacer, tb large spacer. Create that spacer, const tb large spacer equals new touchbar spacer with a size property of large. Save all this, click update, and we get the slider. Now, as you can see, a slider component like this needs as much horizontal space on the touchbar as possible, which in some cases might work, but more often than not, you'll want it to behave like the color picker, revealing itself as a full width component from a button. To do this then, we can implement a popover component. A popover is essentially a button that reveals an entire new touchbar instance, one that can be closed again to return to the original main window touchbar. So let's add this slider to a new touchbar and pass that to a popover on our existing touchbar. Start with the popover, const tb popover equals new touchbar popover. Also require that module. And this popover constructor now takes an object with an items parameter. Items expects a touchbar instance, so call that popover touchbar. We'll create it in a minute with a label of size, same as the actual slider, as this is what the popover touchbar will implement. Create the touchbar for the popover, const popover touchbar equals new touchbar, exactly like we created it for our main touchbar, with an array of components, to which we can add the slider, tb slider. I'll refactor this slightly to make the code more legible. Just move this new touchbar straight into the popover, and that makes more sense. Finally, replace the slider in the main touchbar with that popover. Save, hit update. Our slider is no longer visible, but we now have this popover button, size, so click that, and our original slider component is revealed in its very own touchbar, giving us the full space of the touchbar for adjustment. We can of course also return to the original touchbar via this X provided by the popover, like so. In the next lesson, we'll hook up this slider and picker to our app and see a simple example of reading values from touchbar components. The final step to creating interactive touchbar integration is actually having the user's input on the touchbar integrated with your app. Continuing with what we have here, let's see how to read values from these two components, the color picker and the slider. We'll start with the picker, pass that constructor an object, and what we have to do is pass this component a function to call when a color selection happens. The property on which to set that function is change, so anytime the selected color is changed. Assign this a function with a single argument of color, being the hex string of the selected color, and to make use of this color, let's change the background color of the main window contents, as per this theme label. Remember, we define main window right at the beginning here, and at the point where the touchbar gets added to main window, it's obviously no longer null, as it has to exist. So using it here in this function is perfectly fine. Access the web contents of main window, calling insert CSS, so we can inject some custom CSS into those web contents, setting the body to have a background of that color variable, which is a simple hex string. Save, update the app, and now when I select any of these colors, the background changes to that color. This is not just for selections, however, but on the fly using the full palette. Drag, and the app changes along. We also have saturation, etc. So again, really simple to hook into these values. Let's do something similar for the slider also. We've already defined the minimum and maximum values of the slider's range, but we can also set the initially selected value. I'll just make it 500. So have the slider all the way to the left at its minimum value, with again a change property to handle the value changes from the slider. If you haven't already guessed it, we're simply going to resize main window using the slider. So get the slider value as the first argument and call main window.setSize, making both its width and its height the value of that slider, with the third parameter simply enabling resize animation, true. I'll also start main window off at that slider's minimum value for both its width and height, meaning the main window will now launch at the same width and height as the slider's initial value, and should then adjust in size as we move the slider. Update. We see the new size, a 500 by 500 square, so using the slider, adjust, and we see that window resize along. That's where we'll leave the touchbar API for now. And whilst there's a few more controls, you should now be comfortable working with this new hardware feature on Mac using Electron's intuitive touchbar API. Congratulations, that concludes this course for now. But be sure to look out for new content announcements, as I'm always working on adding your most requested topics and keeping the existing content up to date. so be sure to let me know any suggestions or feedback you might have. I really hope that you enjoyed the course and found the content valuable. If at this point you have any questions or need help with a particular section, please leave your question in the relevant lectures discussion and I'll help out as best I can. I've also linked to some of my other courses in the lesson's resources, and as an existing student, you can use the coupon code stack_student on any of those. I want to thank you for enrolling in this course, and I really look forward to helping you learn something new again soon. All the best, goodbye.